Welcome. I'm Bob Sedgwick, Professor of Computer Science at Princeton. This is our online course, Algorithms, developed by myself and Kevin Wayne here at Princeton. We're going to start with an overview, discussion of why you might want to study algorithms, and then a little bit of discussion about the resources that you need to take this course. So what is this course? It's an intermediate level survey course on algorithms. We're going to concentrate on programming and problem solving in the context of real applications. And our focus is going to be on two things: algorithms, which are methods for solving problems, and data structures, which store the information associated with the problem and go hands in hand with algorithms. These are the basic topics that we'll cover in Part 1 and Part 2 of the course. The first part is data types, sorting, and searching. We'll consider a number of data structures and algorithms that are basic to all the methods we consider, including stacks, queues, bags, and priority queues. Then we'll consider classic algorithms for sorting, putting things in order. That's quicksort, merge sort, heap sort, and radix sorts. And we'll consider classic methods for searching, including binary search trees, red-black binary search trees, and hash tables. The second part of the course is for more advanced algorithms, including graph algorithms, classic graph searching algorithms, minimum spanning tree and shortest paths algorithms, algorithms for processing strings, including regular expressions and data compression, and then some advanced algorithms that make use of the basic algorithms that we developed earlier in the course. So why should one study algorithms? Well, their impact is very broad and far-reaching. From the internet to biology to commercial computing, computer graphics, security, multimedia, social networks, and scientific applications, algorithms are all around us. They're used for movies and video games, for particle collision simulation. They're used to study the genome, and all manner of other applications. So that's one important reason to study algorithms. Their impact is broad and far-reaching. Algorithms are also interesting to study because they have ancient roots. The first algorithm we studied goes back to 300 BC, dating at least to Euclid. The concept of an algorithm was formalized actually here at Princeton by Church and Turing in the 1930s. But most algorithms that we consider were discovered in recent decades. In fact, some were discovered by undergraduates in a course like this. And there's plenty of other algorithms waiting to be discovered by students like you. The main reason that people study algorithms is to be able to solve problems that could not otherwise be addressed. For example, in the first lecture, we're going to talk about the network connectivity problem, where the problem is, given a large set of items that are connected together pairwise, is there a way to get from one to another with a path through the connections? As you can see from this example, it's not clear whether or not there's such a path. We need a computer program to do it. In fact, we need an efficient algorithm to do it. In this case, the answer is that there is such a path. Another reason to study algorithms is for intellectual stimulation. Algorithms are very interesting objects to study. Don Knuth, who wrote several books on algorithms and was a pioneer in the field, said that an algorithm must be seen to be believed. You can't just think about an algorithm, you have to work with it. Another quote from Francis Sullivan says, "The great algorithms are the poetry of computation. Just like verse, they can be terse, elusive, dense, and even mysterious. But once unlocked, they cast a brilliant new light on some aspect of computing." Algorithms are interesting for intellectual stimulation. Another reason many people study algorithms, and I suspect many of you, is it's necessary to understand good algorithms, efficient algorithms, and good data structures in order to be a proficient programmer. Linus Torvalds, who created Linux, says that the difference between a bad programmer and a good one is whether he considers his code or his data structures more important. Bad programmers worry about the code. Good programmers worry about data structures and their relationships, and I might add, the algorithms that process them. Nicholas Wirth, another pioneer in computer science, wrote a famous book called Algorithms plus Data Structures equals Programs. Another reason nowadays to study algorithms is that they have become a common language for understanding nature. Algorithms are computational models, and algorithmic models are replacing mathematical models in scientific inquiry. In the 20th century, scientists developed mathematical models to try to understand natural phenomena. It soon became clear that those mathematical models were difficult to solve. It was difficult to create solutions to be able to test hypotheses against natural phenomena. So more and more and more nowadays, people are developing computational models where they attempt to simulate what might be happening in nature in order to try to better understand it. Algorithms play an extremely important role in this process, and we'll see some examples of this in this course. Another important reason is that if you know how to effectively use algorithms and data structures, you're going to have a much better chance at interviewing for a job in the technology industry than if you don't. So here's a bunch of reasons that I just went through for studying algorithms. Their impact's broad and far-reaching. They have old roots and present new opportunities. They allow us to solve problems that could not otherwise be addressed. You can use them for intellectual stimulation to become a proficient programmer. They might unlock the secrets of life in the universe, and they're good for fun and profit. In fact, a programmer might ask, why study anything else? Well, there's plenty of good reasons to study other things, but I'll submit there's no good reason not to study algorithms. So for this course, we have two resources that I want to talk about and make sure that people are familiar with before entering into the content. This is a publishing model that Kevin Wayne and I developed and have been using for many years, and we think it's a very effective way to support the kinds of lectures that we're going to be giving in this course. Down at the bottom, and it's optional for this course, we have a textbook. It's a traditional textbook that extensively covers the topics in the course. In fact, many more topics than we can present in lecture. And then supporting that textbook is free online material that we call the book site. You can go to the book site to see the lecture slides, but more important, there's code, there's exercises, there's a great deal of information there. In fact, maybe 10 times what's in the book, including a summary of the content. So during this course, you'll be referring to the book site frequently while working online. People often ask about prerequisites. We're assuming that people who take this course know how to program. They know the basics of loops, arrays, functions. They have some exposure to object-oriented programming and recursion. We use the Java language, but we don't dwell on details of Java. We mostly use it as an expository language. We do some math, but not advanced math. If you want to review the material that we think is prerequisite to the material in this course, you can do a quick review by looking at sections 1.1 and 1.2 of the book, either at the book site or in the textbook. If you want an in-depth review, we have a full textbook called An Introduction to Programming in Java, an Interdisciplinary Approach. There's a book site and a textbook as well. But the bottom line is you should be able to program. And the quick exercise to get ready is to write a Java program on your computer, perhaps using our programming model as described on the book site. We'll provide much more detailed information on that as we get into the assignments. You can use your own programming environment if you're comfortable with one, or you can download ours. We have instructions on the web about how to do that. Welcome back to Algorithms. Today we're going to talk about the union find problem, a set of algorithms for solving the so-called dynamic connectivity problem. We'll look at two classic algorithms, quick find and quick union, and some applications and improvements of those algorithms. The subtext of today's lecture really is to go through the steps that we'll follow over and over again to develop a useful algorithm. The first step is to model the problem. Try to understand basically what are the main elements of the problem that needs to be solved. Then we'll find some algorithm to solve the problem. In many cases, the first algorithm we come up with would be fast enough, maybe fits in memory, and we'd go ahead and use it and be off and running. But in many other cases, maybe it's not fast enough or there's not enough memory. So what we do is try to figure out why, find a way to address whatever is causing that problem, find a new algorithm, and iterate until we're satisfied. This is a scientific approach to designing and analyzing algorithms, where we build mathematical models to try to understand what's going on, and then we do experiments to validate those models and help us improve things. So first we'll talk about the dynamic connectivity problem, a model of the problem for union find. So here's the idea. There's going to have a set of n objects. It doesn't really matter what they are. We're going to use the numbers 0 through n to model our objects. And then we have the idea of a connection between two objects. And we'll postulate that there's going to be a command that says connect two objects. Given two objects, provide a connection between them. And then the key part of the problem is the find query, or the connected query, which just asks, is there a path connecting the two objects? So for example, in this set of 10 objects, we've performed already a bunch of union commands, connecting 4 and 3, and 3 and 8, and 6 and 5, 9 and 4, and 2 and 1. And now we might have a connected query that says, is 0 connected to 7? Well, in this case, there's no connection, so we say no. But if we ask, is 8 connected to 9, we're going to say yes. Even though we don't have a direct connection between 8 and 9, there's a path from 8 to 3 to 4 to 9. So that's our problem, to be able to efficiently support these two commands for a given set of objects. Now let's say we add a union 5, 0. So that creates a connection between 5 and 0. 7 and 2 creates a connection between 7 and 2. And 6 and 1 between 6 and 1. So now if we ask, are 0 connected to 7? Well, 1 and 0, we can do that too, and that's a redundant connection. And now if we ask, is 0 connected to 7? We're going to answer yes. So that's our problem, intermix union commands and connected queries, and we need to be able to efficiently support those commands for a large number of objects. So here's a much bigger example. And you can see that we're going to need efficient algorithms for this. First of all, you can see we're going to need a computer for this. It would take quite some time for a human to figure out whether there's a connection. In this case, there is a connection. Now, the algorithms that we're looking at today are not going to actually give the path connecting the two objects. It's just going to be able to answer the question, is there a path? In part 2 of the course, we'll consider algorithms that explicitly find paths. They're not as efficient as union find because they have more work to do. Now, applications of these algorithms involve objects of all types. These are used for digital photos where the objects are pixels. They're used for networks where the objects are computers. Social networks where it's people, or computer chips where it's circuit elements, or abstract things like variable names in a program, or elements in a mathematical set, or physical things like metallic sites in a composite system. So all different types of objects. But for programming, we're going to associate each object with a name, and we'll just name the objects with the integers from 0 to n minus 1. That's a very convenient initial starting point for our programs because we can use integers as an index into an array then, and then quickly access information relevant to each object. And it also just suppresses a lot of details that are not relevant to union find. In fact, to make this mapping from an object name to the integers 0 through n minus 1 is a fine application of a symbol table or searching algorithm, which is one of the things that we'll be studying later in this course, algorithms and data structures for solving that problem. Now the connections, well, we need a few abstract properties that these connections have to satisfy, and they're all quite natural and intuitive. So we assume that is connected to is an equivalence relation. That is, every object's connected to itself. It's symmetric. If P is connected to Q, then Q is connected to P. And it's transitive. If P is connected to Q and Q is connected to R, then P is connected to R. Now these properties are very intuitive, but it's worthwhile to state them explicitly and make sure that our algorithms maintain them. When we have an equivalence relation, a set of objects and connections divide into subsets called connected components. A connected component is a maximal set of objects that's mutually connected. For example, in this small example here, there's 3 connected components. One consisting of just object 0, second one objects 1, 4, and 5, and third one the other 4 objects. And these components have the property that if any 2 objects in them are connected, and there's no object outside that's connected to those objects, those connected components, our algorithms will gain efficiency by maintaining connected components and using that knowledge to efficiently answer the query that they're presented with. Okay, so to implement the operations, we have the find query and the union command. And so we're going to maintain the connected components. The find is going to have to check if 2 objects are in the same component. And the union command is going to have to replace components containing 2 objects with their union. So for example, if we have these components and we get the command to connect 2 and 5, essentially we need to merge the connected components containing the one containing 2 with the one containing 5 to get a big connected component. So now we have only 2 connected components. All of that leads up to, in a programming world, to specifying a data type, which is simply a specification of the methods that we're going to want to implement in order to solve this problem. So in our typical Java model, what we'll do is create a class called UF that contains 2 methods, one to implement union, the other one to implement connected, which returns a Boolean. The constructor takes as argument the number of objects, so it can build data structures based on that number of objects. And we have to bear in mind, as we're building our algorithms, that both the number of objects can be huge, but also the number of operations. We can have a very large number of union and connected operations, and our algorithms are going to have to be efficient under those conditions. One of the practices that we'll follow often in this course is to check our API design before getting too far into dealing with the problem by building a client that is going to use the data type that we develop. So for this example, we've got a client that will read information from standard input. First, an integer, which is the number of objects that are going to be processed, and then a series of pairs of object names. And what the client does is it'll first read the integer from standard input and create a UF object. And then as long as standard input is not empty, it's going to read 2 integers from the input. And if they're not connected, then it'll connect them and print them out. If they are connected, it'll ignore them. So that's our test client, and that's a fine test client to make sure that any implementation does what we expect that it will. So that's the setup. We've described the operations we want to implement all the way down to code, and we have client code that we're going to have to be able to service with our implementations. Now we'll look at our first implementation of an algorithm for solving the dynamic connectivity problem called Quick Find. This is a so-called eager algorithm for solving connectivity problem. The data structure that we're going to use to support the algorithm is simply an integer array indexed by object. The interpretation is that two objects, P and Q, are connected if and only if their entries in the array are the same. So, for example, in this example with our 10 objects, the ID array that describes the situation after 7 connections is illustrated in the middle of the slide, so that at this point 0, 5, and 6 are all in the same connected component because they have the same array entry 0. 1, 2, and 7 all have entry 1, and 3, 4, 8, and 9 all have entry 8. So that representation shows that they're connected. And clearly that's going to support a quick implementation of the find operation. We just check the array entries to see if they're equal. Check if P and Q have the same ID. So 6 and 1 have different IDs. 1 has ID 1, 6 has ID 0. They're not in the same connected component. Union is more difficult. In order to merge the components containing two given objects, we have to change all the entries whose ID is equal to one of them to the other one. And arbitrarily, we choose to change the ones that are the same as P to the ones that are the same as Q. So if we're going to union 6 and 1, then we have to change entries 0, 5, and 6, everybody in the same connected component as 6, from 0 to 1. And this is, as we'll see, this is a bit of a problem when we have a huge number of objects because there's a lot of values that can change. But still, it's easy to implement, so that'll be our starting point. So we'll start with a demo of how this works. So initially, we set up the ID array with each entry equal to its index. And so all that says is that all the objects are independent, they're in their own connected component. Now when we get a union operation, so say 4 is supposed to be union with 3, then we're going to change all entries whose ID is equal to the first ID to the second one. So in this case, we'll change the connect 3 and 4 means that we need to change the 4 to a 3. And we'll continue and do a few more so you'll get an idea of how it works. So 3 and 8 now. So to connect 3 and 8, now 3 and 4 have to be connected to 8, so both of those entries have to change to 8. Okay, so now what about 6 and 5? So again, we change the first one to match the second one. So to connect 6 and 5, we change the 6 to a 5. What about 9 and 4? So now we have to change to connect 9 and 4, we have to change 9's entry to be the same as 4's. So now we have 3, 4, 8, and 9 all have entries 8. They're all in the same connected component. 2 and 1 means that we connect 2 and 1 by changing the 2 to a 1. 8 and 9 are already connected. They have the same entries in the ID array, so that connected query, that find, says true, they're already connected. And 5 and 0 have different entries. They're not connected, so we'd return false in that case, not connected. And then if we want to connect 5 and 0, then, as usual, we'll connect the entry corresponding to both 5 and 6 to 0. 7 and 2, union 7 and 2, that's an easy one. And union 6 and 1, so now there's 3 entries that have to get changed. All those zeros have to get changed to 1s. So that's a quick demo of Quick Find. Now next we'll look at the code for implementing that. Okay, with this concrete demo in mind, then moving to coding up this algorithm is pretty straightforward. although it's an interesting programming exercise that a lot of us would get wrong the first time. So let's start with the constructor. Well, we have a private integer array, that's our ID array, that's the data structure that's going to support this implementation. The constructor has to create the array and then go through and set the value corresponding to each index I to I. That's straightforward. The find operation or connected operation, that's the easy one. This is the quick find algorithm. So it simply takes its two arguments, P and Q, and checks whether their ID entries are equal and returns that value. If they're equal, it returns true. If they're not equal, it returns false. The more complicated operation to implement is union. And there we find first the ID corresponding with the first argument, and then the ID corresponding to the second argument. And then we go through the whole array and looking for the entries whose IDs are equal to the ID of the first argument and set those to the ID of the second argument. That's a pretty straightforward implementation. And I mentioned that a lot of us would get us wrong. The mistake we might make is to put ID of P here rather than first picking out that value. And you can think about the implications of that. That's an insidious bug. So that's a fine implementation of quick find. Now the next thing is to decide how effective or efficient that algorithm is going to be. And we'll talk in some detail about how to do that, but for this it's sufficient to just think about the number of times the code has to access the array. As we saw when doing the implementation, both the initialize and the union operations involved a for loop that go through the entire array. So they have to touch in a constant proportional to n times they have to touch an array entry. Find operation is quick, it just has to a constant number of times check array entries. And this is problematic because the union operation is too expensive. In particular, if you just have n union commands on n objects, which is not unreasonable, they're either connected or not, then that'll take quadratic time, n squared time. And one of the themes that we'll go through over and over in this course is that quadratic time is much too slow, and we can't accept quadratic time algorithms for large problems. The reason is they don't scale. As computers get faster and bigger, quadratic algorithms actually get slower. And let's just talk roughly about what I mean by that. A very rough standard, say, for now, is that people have computers that can run billions of operations per second, and they have billions of entries in main memory. So that means that you could touch everything in the main memory in about a second. It's kind of an amazing fact that this rough standard is really held for 50 or 60 years. The computers get bigger, but they get faster. So to touch everything in the memory is going to take a few seconds. And that was true when computers only had a few thousand words of memory, and it's true now that they have billions or more. So let's accept that as what computers are like. Now, what that means is that with that huge memory, we can address huge problems. So we could have billions of objects and hope to do billions of union commands on them. But the problem with that quick find algorithm is that that would take 10 to the 18th operations, or say array accesses or touching memory. And if you do the math, that works out to 30-some years of computer time. Obviously, not practical to address such a problem on today's computer. And the reason is, and the problem is, that quadratic algorithms don't scale with technology. You might have a new computer that's 10 times as fast, but you can address a problem that's 10 times as big. And with a quadratic algorithm, when you do that, it's going to be 10 times as slow. That's the kind of situation we're going to try to avoid by developing more efficient algorithms for solving problems like this. All right, so quick find is too slow for huge problems. So how are we going to do better? Our first attempt is an alternative called quick union. This is a so-called lazy approach to algorithm design, where we try to avoid doing work until we have to. It uses the same data structure, our array ID with size n, but now it has a different interpretation. We're going to think of that array as representing a set of trees, it's called a forest, as depicted at right. So each entry in the array is going to contain a reference to its parent in the tree. So for example, 3's parent is 4, 4's parent is 9, so 3's entry is 4, and 4's entry is 9 in the array. Now, each entry in the array has associated with it a root. That's the root of its tree. Elements that are all by themselves in their own connected component point to themselves, so 1 points to itself, but also 9 points to itself. It's the root of the tree containing 2, 4, and 3. So from this data structure, we can associate with each item a root, which is representative, say, of its connected component. So that's a root of 3 is 9 going up that root. Now, once we can calculate these roots, then we can implement the find operation just by checking whether the two items that we're supposed to check whether they're connected, whether they have the same root. That's equivalent to saying, are they in the same connected component? So that's some work going to find the roots of each item, but the union operation is very easy. To merge components containing two different items, two items that are in different components, all we do is set the ID of P's root to the ID of Q's root. That's make P's tree point to Q. So in this case, we would change the entry of 9 to be 6 to merge 3 and 5, the components containing 3 and 5. And with just changing one value in the array, we get the two large components merged together. That's the quick union algorithm, because the union operation only involves changing one entry in the array. Find operation requires a little more work. So let's look at the implementation, a demo of that one in operation first. So again, we start out the same way, but now the ID array entry really means that every one of these things is a little tree with one node each, every one pointing to itself. It's the root of its own tree. So now if we have to put 4 and 3 in the same component, then all we do is we take the root of the component containing the first item and make that a child of the root of the component containing the second item. In this case, we just make 4 as parent 3. So now 3 and 8. So again, we take the first item and make it a child of the root of the tree containing the second item. So now 3, 4, and 8 are in the same component. 6 and 5, 6 goes below 5. 9 and 4, so now 4's, the root of the tree containing 4 is 8. And the root of the tree containing 9 is 9, and so we make 9 a child of 8. 2 and 1, that's an easy one. Now, if we get our 8 and 9 connected, we just check, do they have the same root? And they both have the same root, 8, and so they're connected. 5 and 4, 4's root is 8, 5's root is 5. They're different, they're not connected. 5 and 0, 5 goes to be a child of 0. 7 and 2, 7 goes to be a child of 2's root, which is 1. 6 and 1. 6's root is 0. 1's its own root, so 0 becomes a child of 1. Each one of these union operations just involves changing one entry in the array. And finally, 7 and 3. So 7's root is 1, 3's root is 8, 1 becomes a child of 8. Okay, and now we have one connected component with all the items together. All right, so now let's look at the code for implementing quick union. The constructor is the same as the other one. We create the array and then set each element to be its own root. Now we have a private method that implements this process of finding the root by chasing parent pointers until we get to the point where I is equal to ID of I. And if it's not equal, we just move I up one level in the tree, set I equals ID of I, and return it. So starting at any node, you just follow ID equals ID of I until they're equal, and then you're at a root. And that's a private method that we can use to implement the find operation or the connected operation. You just find the root of P and the root of Q, and if you check if they're equal. And then the union operation is simply find the two roots and then set the ID of the first one to be the second one. Actually, less code than for quick find. No for loops. There's this one while loop that we have to worry about a little bit, but that's a quick and elegant implementation of code to solve the dynamic connectivity problem called quick union. So now we're going to have to look at can this code be effective for large problems? Unfortunately, quick union is faster, but it's also too slow. And it's a little different kind of too slow than for quick find. There's times when it could be fast, but there's also times when it could be too slow. And the defect for quick union is that the trees can get too tall, which would mean that the find operation would be too expensive. You could wind up with a long skinny tree of each object just pointing to a next, and then to do a find operation for object at the bottom would involve going all the way through the tree, involving n array accesses just to do the find operation. And that's going to be too slow if you have a lot of operations. Okay, so we've looked at the quick union and quick find algorithms, both of which are easy to implement, but simply can't support huge dynamic commutativity problems. So how are we going to do better? That's what we'll look at next. A very effective improvement is called weighting, and it might have occurred to you while we were looking at these algorithms. The idea is to, when implementing the quick union algorithm, take steps to avoid having tall trees. If you've got a large tree and a small tree to combine together, what you want to try to do is avoid putting the large tree lower. That's going to lead to long, tall trees. And there's a relatively easy way to do that. What we'll do is we'll keep track of the number of objects in each tree, and then we'll maintain balance by always making sure that we link the root of the smaller tree to the root of the larger tree. So we avoid this first situation here where we put the larger tree lower. In the weighted algorithm, we always put the smaller tree lower. Let's see how we implement that. Let's see a demo first. Okay, so again, we start out in our normal starting position where everybody's in their own tree. And when there's only two items to link, it works the same way as before. But now when we have 8 to merge with 4 and 3, we put the 8 as the child, no matter which order the arguments came, because it's the smaller tree. So 6 and 5 doesn't matter. Whichever one goes down doesn't matter. 9 and 4. So now 9's the small one, 4's the big one, so 9's going to be the one that goes down below. 2 and 1. 5 and 0. So now 5 and 0, 5's in the bigger tree, so 0 goes below. 7 and 2. 2's in the bigger tree, so 7 goes below. 6 and 1, they're in equal size trees. And 7 and 3, 3's in the smaller tree, so it goes below. So the weighted algorithm always makes sure that the smaller tree goes below. And again, we wind up with a single tree representing all the objects, but this time we have some guarantee that no item is too far from the root, and we'll talk about that explicitly in a second. So here's an example that shows the effect of doing the weighted quick union, where we always put the smaller tree down below for the same set of union commands. This is with 100 sites and 88 union operations. You can see in the top, the big tree has some trees, some nodes, a fair distance from the root. In the bottom, for the weighted algorithm, all the nodes are within distance 4 from the root. The average distance to the root is much, much lower. Let's look at the Java implementation, and then we'll look in more detail at that quantitative information. So we use the same data structure, except now we need an extra array that for each item gives the number of objects in the tree rooted at that item that we'll maintain in the union operation. Find implementation is identical to for quick union. You're just checking whether the roots are equal. For the union implementation, we're going to modify the code to check the sizes and link the root of the smaller tree to the root of the larger tree in each case. And then after changing the ID link, we also change the size array. If we make I a child of j, then we have to increment the size of j's tree by the size of i's tree. Or if we do the other way around, then we have to increment the size of i's tree by the size of j's tree. So that's the full code in white for implementing quick union. So not very much code, but much, much better performance. In fact, we can analyze the running time mathematically and show that the find operation, it takes time proportional to how far down the trees are in the node, the nodes are in the tree, but we can show that it's guaranteed that the depth of any node in the tree is at most the logarithm to the base 2 of n. We use the notation LG always for logarithm to the base 2. And so for if n is 1,000, that's going to be 10. If n is 1,000,000, that's 20. If n is 1 billion, that's 30. It's a very small number compared to n. So let's look at the proof of that. We do some mathematical proofs in this course when they're critical, such as this one. And why is it true that the depth of any node x is at most log base 2 of n? Well, the key to understanding that is to take a look at exactly when does the depth of any node increase. When does it go down further in the tree? Well, the x's depth will increase by 1 when its tree, T1 in this diagram, is merged into some other tree, T2 in this diagram. Well, at that point, we said we'd only do that if the size of T2 was bigger than or equal to the size of T1. So when the depth of x increases, the size of its tree at least doubles. So that's the key, because that means that the size of the tree containing x can double at most log n times, because if you start with 1 and double log n times, you get n, and there's only n nodes in the tree. So that's a sketch of a proof that the depth of any node x is at most log base 2 of n, and that has profound impact on the performance of this algorithm. Now, instead of the initialization always takes time proportional to n, but now both the union and the connected or find operation takes time proportional to log base 2 of n. And that is an algorithm that scales. If n grows from a million to a billion, that cost goes from 20 to 30, which is quite acceptable. Now, this was very easy to implement, and we could stop, but usually what happens in the design of algorithms is now that we understand what it is that gains performance, we take a look and see, well, could we improve it even further? And in this case, it's very easy to improve it much more. And that's the idea of path compression. And this idea is that, well, when we're trying to find the root of the tree containing a given node, we're touching all the nodes on the path from that node to the root. While we're doing that, we might as well make each one of those just point to the root. There's no reason not to. So when we're trying to find the root of p, after we find it, we might as well just go back and make every node on that path just point to the root. That's going to be a constant extra cost. We went up the path once to find the root. Now we'll go up again to just flatten the tree out. And the reason would be no reason not to do that. We had one line of code to flatten the tree amazingly. Actually, to make a one line of code, we use a simple variant where we make every other node in the path point to its grandparent on the way up the tree. That's not quite as good as totally flattening. Actually, in practice, it actually is just about as good. So with one line of code, we can keep the trees almost completely flat. Now, this algorithm people discovered rather early on after figuring out the weighting, and it turns out to be fascinating to analyze, quite beyond our scope, but mention this example to illustrate how even a simple algorithm can have interesting and complex analysis. And what was proved by Hopcroft and Ullman and Tarjan was that if you have n objects, any sequence of m union and find operations will touch the array at most a constant of n plus m log star n times. Now log star n is kind of a funny function. It's the number of times you have to take the log of n to get 1. And it's called the iterated log function. And in the real world, it's best to think of that as a number less than 5. Because log star of 2 to the 65536 power is 5. So that means that the running time of weighted quith union with path compression is going to be linear in the real world. And actually can be improved to even a more interesting function called the Ackermann function, which is even more slowly growing than log star. And another point about this is it seems this is so close to being linear, that is time proportional to n, instead of time proportional to n times a slowly growing function in n. Is there a simple algorithm that is linear? And people look for a long time for that, and actually it works out to be the case that we can prove that there is no such algorithm. So there's a lot of theory that goes behind the algorithms that we use, and it's important for us to know that theory, and that'll help us decide how to choose which algorithms we're going to use in practice and where to concentrate our effort in trying to find better algorithms. It's an amazing fact that was eventually proved by Fredman and Sachs that there is no linear time algorithm for the union find problem. But weighted quick reunion with path compression in practice is close enough that it's going to enable the solution of huge problems. So that's our summary for algorithms for solving the dynamic connectivity problem. With using weighted quick union and with path compression, we can solve problems that could not otherwise be addressed. For example, if you have a billion operations on a billion objects, I said before it might take 30 years, we can do it in 6 seconds. And what's most important to recognize about this is that it's the algorithm design that enables the solution of the problem. Faster computer wouldn't help much. You could spend millions on a supercomputer and maybe you could get it done in 6 years instead of 30 or in 2 months. But with a fast algorithm, you can do it in seconds on your own PC. All right, now that we've seen efficient implementations of algorithms that can solve the union find problem for huge problem instances, let's look to see how that might be applied. There's a huge number of applications of union find. We talked about dynamic connectivity in networks. There's many other examples in our computational infrastructure. Down at the bottom, one is important one is in image processing for understanding how to label areas in images. We'll see later Kruskal's minimum spanning tree algorithm, which is a graph processing algorithm which uses union find as a subroutine. There's algorithms in physics for understanding physical phenomena that we'll look at an example, and many others on this list. So the one we're going to talk about now is called percolation. That's a model for many physical systems. I'll give an abstract model and then just talk briefly about how it applies to physical systems. So let's think of an n by n grid of squares that we call sites. And we'll say that each site is open, and that's white in the diagram, with probability p, or blocked, that's black in the diagram, with probability 1 minus p. And we define a system to, we say that a system is percolated if the top and the bottom are connected by open sites. So the system at the left, you can find a way to get from the top to the bottom through white squares. But the system on the right does not percolate. There's no way to get from the top to the bottom through white squares. So that's a model for many systems. You can think of, for electricity, you could think of a vacant site as being a conductor and a block site as being insulated. And so if there's a conductor from top to bottom, then the thing conducts electricity. Or you could think of it as water flowing through a porous substance of some kind, where a vacant site is just empty and a block site has got some material, and either the water flows through from top to bottom or not. Or you could think of a social network where it's people connected, and either there's a connection between two people or not, and is there a way to get from one group of people to another, communicating through that social network. That's just a few examples of the percolation model. So if we're talking about a randomized model where the sites are vacant with a given probability. And so it's pretty clear that if the probability that a site is vacant is low, as on the left, two examples on the left in this diagram, it's not going to percolate. There's not enough open sites for there to be a connection from the top to the bottom. if the probability is high and there's a lot of open sites, it definitely is going to percolate. There'll be lots of ways to get from the top to the bottom. But in the middle, when it's medium, it's questionable whether it percolates or not. So the scientific question, or the mathematical question from this model, is how do we know whether it's going to percolate or not? In this problem and in many similar problems, there's what's called a phase transition, which says that when it's low, it's not going to percolate. When it's high, it is going to percolate. And actually, the threshold between when it percolates and when it doesn't percolate is very sharp. And actually, there's a value as n gets large that if you're less than that value, it almost certainly will not percolate. If you're greater, it almost certainly will. The question is, what is that value? This is an example of a mathematical model where the problem is very well articulated. What's that threshold value? But nobody knows the solution to that mathematical problem. The only solution we have comes from a computational model where we run simulations to try to determine the value of that probability. And those simulations are only enabled by fast union find algorithms. That's our motivating example for why we might need fast union find algorithms. So let's look at that. So what we're going to run is called a so-called Monte Carlo simulation, where we initialize the whole grid to be blocked, all black, and then we randomly fill in open sites. And we keep going, and every time we add an open site, we check to see if it makes the system percolate. And we keep going until we get to a point where the system percolates. And we can show that the vacancy percentage at the time that it percolates is an estimate of this threshold value. So what we want to do is run this experiment millions of times, which we can do in a computer, as long as we can efficiently do the calculation of does it percolate or not. That's a Monte Carlo simulation, a computational problem that gives us a solution to this scientific problem where mathematical models nobody knows how to solve yet. So let's look in a little bit more detail of how we're going to use our dynamic connectivity model to do this. So it's clear that we'll create an object corresponding to each site, and we'll give them a name from 0 to n squared minus 1 as indicated here. And then we'll connect them together if they're connected by open sites. So the percolation model on the left corresponds to the connection model on the right, according to what we've been doing. Now, you might say, well, what we want to do is check whether any site in the bottom row is connected to any site in the top row and use union find for that. Problem with that is that would be a brute force algorithm, would be quadratic right on the face of it, because it would have n squared calls to find, to check whether they're connected. For each site on the top, not check each site on the bottom. Much too slow. Instead, what we do is create a virtual site on the top and on the bottom, and then when we want to know whether this system percolates, we just check whether the virtual top site is connected to the virtual bottom site. So how do we model opening a new site? Well, to open a site, we just connect it to all its adjacent open sites. So that's a few calls to union. But that's easy to implement. And then with that simple relationship, we can use exactly the code that we developed to go ahead and run a simulation for this connectivity problem. And that's where we get the result that by running enough simulations for big enough n, that this percolation threshold is about 0.592746. With this fast algorithm, we can get an accurate answer to this scientific question. If we use a slow union find algorithm, we won't be able to run it for very big problems, and we won't get a very accurate answer. So in summary, we took an important problem, the dynamic connectivity problem, We modeled the problem to try to understand precisely what kinds of data structures and algorithms we'd need to solve it. We saw a few easy algorithms for solving the problem and quickly saw that they were inadequate for addressing huge problems. But then we saw how to improve them to get efficient algorithms. And then left us with applications that could not be solved without these efficient algorithms. All of this involves the scientific method for algorithm design, where we try to develop mathematical models that help us understand the properties of the algorithms that we're developing. And then we test those models through experimentation, enabling us to improve algorithms, iterating, developing better algorithms and more refined models until we get what we need to solve the practical problems that we have of interest. That's going to be the overall architecture for studying algorithms that we're going to use throughout the course. Welcome back. Today we're going to do some math and some science. Not a lot, but we need to have a scientific basis for understanding the performance of our algorithms to properly deploy them in practice. So today we're going to talk about how to observe performance characteristics of algorithms. We're going to look at how to make mathematical models and how to classify algorithms according to the order of growth of their running time. We'll talk a bit about the theory of algorithms and also how to analyze memory usage. So to put this all in perspective, we're going to think about these issues from the point of view of different types of characters. So the first one is a programmer who needs to solve a problem and get it working and get it deployed. Second one is the client who wants to use whatever the program did to get the job done. Third one is a theoretician. That's somebody who really wants to understand what's going on. And the last one is kind of the team, this basic blocking and tackling sometimes necessary to get all these things done. So there's a little bit of each one of these in today's lecture. And actually, when you're a student, you have to think that you might be playing any or all of these roles someday. So it's pretty important to understand the different points of view. So the key that we'll focus on is running time. And actually, the idea of understanding the running time of a computation goes way back even to Babbage and probably before. Here's a quote from Babbage. As soon as an analytic engine exists, it will necessarily guide the future of the course of the science. Whenever any result is sought by its aid, the question will arise, by what course of calculation can these results be arrived at by the machine in the shortest time? If you look at Babbage's machine called the analytic engine, it's got a crank on it. And literally, the concern that Babbage had in knowing how long a computation would take is how many times do we have to turn the crank? It's not that different in today's world. The crank may be something electronic that's happening a billion times a second, but still we're looking for how many times does some discrete operation have to be performed in order to get a computation done. So there's a lot of reasons to analyze algorithms. In the context of this course, we're mainly interested in performance prediction. We also want to compare the performance of different algorithms for the same task and to be able to provide some guarantees on how well they perform. Along with this is understanding some theoretical basis for how algorithms perform. But primarily, the practical reason that we want to be analyzing algorithms and understanding them is to avoid performance bugs. We want to have some confidence that our algorithm is going to complete the job in the amount of time that we think it will. And it's very, very frequent to see in today's computational infrastructure a situation where the client gets bad performance because the programmer did not understand the performance characteristics of the algorithm. And today's lecture is about trying to avoid that. Now, we're going to focus on performance and comparing algorithms in this course. There's later courses in typical computer science curricula that have more information about the theoretical basis of algorithms, and I'll mention a little bit about that later on. But our focus is on being able to predict performance and comparing algorithms. Now, there's a long list of success stories in designing algorithms with better performance and enabling the solution of problems that would otherwise not be solved. And I'll just give a couple of examples. One of the first and most famous is the so-called FFT algorithm. That's an algorithm for breaking down the waveform of n samples of a signal into periodic components. And that's at the basis for DVDs and JPEGs and many other applications. There's an easy way to do it that takes time proportional to n squared, but the FFT algorithm takes only n log n steps. And the difference between n log n and n squared is the difference between being able to solve a large problem and not being able to solve it. A lot of the digital technology, digital media technology that we have today is enabled by that fast algorithm. Another example was actually developed by Andrew Appel, who's now the chair of computer science here at Princeton, and it was developed when he was an undergraduate for his senior thesis. It's a fast algorithm for the n-body simulation problem. The easy algorithm takes time proportional to n squared, but Appel's algorithm was an n log n algorithm that again meant that scientists can do n-body simulation for huge values of n, and that enables new research. So the challenge is that we usually face is, will my program be able to solve a large practical input? Actually, the working programmer is actually faced with that all the time. Why is my program running so slowly? Why does it run out of memory? And that's faced programmers for a really long time. And the insight to address this, due to Knuth in the 1970s, was that we really can use the scientific method to understand the performance of algorithms in operation. Maybe we're not unlocking new secrets of the universe, but we can use the scientific method and treat the computer as something to be studied in that way and come to an understanding of how our programs are going to perform. And let's take a look at that in more detail. So this is just a quick summary of what we mean by the scientific method, which has been successful for a couple of centuries now. So what we're going to do is observe from some feature of the natural world. In this case, it's going to be the running time of our program on a computer. Then we're going to develop a hypothesis, some model that's consistent with the observations. And we're going to hope that that hypothesis is good enough that it'll allow us to predict something, usually predict the running time for larger problem size or on a different computer. And then we'll verify the predictions by making more observations and validate until we're comfortable that our model, hypothesis, and observations all agree. That's a way to get comfort that we understand the performance of our programs. Within the scientific method, there's some basic principles. And the first is that if you're going to run experiments, you should expect that somebody else should be able to run experiments and get the same result. And also, the hypotheses have to have a specific property that the experiment can show the hypothesis to be wrong. So it has to be carefully crafted, and we'll be sure to try to do that. And again, the feature of the natural world that we're studying is some particular computer that exists in the natural world. It changes the algorithm from an abstraction to some kind of actual physical thing happening, like electrons racing around inside the computer. Okay, so the first step is to be able to make some observations about the running time of the programs. And for analysis of algorithms, that's easier than in a lot of scientific disciplines, as we'll see. For an running example, we're going to use the so-called three-sum problem. And it's an easy-to-state problem. If you've got n distinct integers, how many triples sum to exactly 0? For example, in this file, 8ints.txt, which has 8 integers in it, there's 4 triples that sum to 0. 30 minus 40, 10, 30 minus 20 minus 10, and so forth. And so our goal is to write a program that can compute this quantity for any input file, any set of n integers. This is actually an extremely important computation that's deeply related to many problems in computational geometry, which is a branch of computer science that covers the algorithms and underlying science related to graphics and movies and geometric models of all sorts. So this is actually an important practical problem. But it's a simple one to write code for. Any of you could write down this program without much effort. It's got a static method count that is going to go ahead and take an integer array as argument. N is that's the number of integers, that's the length of the array. We'll start with a variable count equals 0, and then a triple for loop that checks each triple I, j, k. We go I from 1 to n, j from I plus 1 to n, and k from j plus 1 to n, so that we get each triple just once. And then if I plus j, ai plus aj plus ak equals 0, we increment the count. And after that triple for loop, we return the count. And then the main method in this simple class just reads in all the integers and prints out the count. So that's a brute force algorithm that is a fine method for solving the three-sum problem. Now what we're interested in is how much time does this take as a function of n? Well, one way to time a program is to just look at the watch. If you have a stopwatch, or look at the clock, or your phone, whatever you might need, you can just go ahead and time it if you want. We have Java has as part of its standard library a stopwatch class that will go ahead and compute elapsed time. Anytime you run a program, if it's set up to easily take input of different sizes, a natural thing to do is just run it for bigger sizes. So for 8 ints, this program takes not too much time. For 1,000 ints, it takes half a second. For 2,000, it takes more time. That's 3.7 seconds. Run it again, still takes 3.7 seconds. For 4,000, so each time we're doubling the size of the input, and it's definitely taking more time each time. And actually, as we'll see, if programmers who get in the habit of testing the running time of their program in this way can get so that you can actually pretty easily and quickly evaluate when it's going to finish. In fact, while you're waiting for it to finish, you can often figure it out. So that one took 30 seconds for 4K, and definitely we could figure out how long it's going to take for 8K before it finishes. And you'll see how in just a second. I'm not going to wait right now. You can think about what you think. Okay, so that's empirical analysis. Run it for various input sizes and measure the running time. Now, if this were some scientific problem where we were counting something that happened in the natural world, the number of ants on an anthill or whatever, then we'd have only a few data points, and we would try to understand what's going on by doing a plot of our running time, the quantity we're interested in on the y-axis, and the problem size on the x-axis. We get a curve like this. And actually, what scientists usually do, because so many problems fall into this class, is do the plot as a log-log plot. If you do it as a log-log plot, very often you'll get a straight line. And the slope of the straight line is the key to what's going on. In this case, the slope of the straight line is 3. And so you can run what's called a regression to fit the straight line through the data points. And then it's not difficult to show, to do the math to show that if you get a straight line and the slope is b, then your function is proportional to n to the b. That's called a power law. And that's true of many, many scientific problems, including most algorithms. So here's a little bit of the math for that. So the straight line means that since we did a log-log plot with powers of 2, that log base 2 of t of n equals b log of n plus c. And we have our empirical values of b and c. And then if you raise both sides of that equation to 2 to that power, then you get t of n equals a constant times n to the b. So right away, just from observation, we have a pretty good model for the running time of our program. We can do the math and figure out that it seems as though the running time is about 10 to the minus 10 times n cubed seconds. And we can use that hypothesis to go ahead and make predictions. Just plug in for different values of n, and it says it ought to take us 400 seconds for 16,000. And 400 seconds is plenty of time, but now we can go ahead and invest and run that experiment, and sure enough, we're pretty close to that 408 seconds when we run it. And now we can make a prediction for 32,000 or for whatever else we might be interested in. The model helps us do predictions without investing the expense to run the experiments. In fact, in this situation, if there is a power law, and again, in very great majority of computer algorithm running times, it's going to be a power law. What we can do is just double the size of the input each time, the way we were, and then take the ratio of the running times for n and 2n. And if you do that, that ratio is going to converge to a constant. And in fact, the log of the ratio is going to converge to that constant, which is the exponent of n in the running time. And just need a little math to check that one, but that's a very easy and natural way to go ahead and predict running times. So that's what I said before is, so we have this quick way to estimate B in the power law relationship. How do we estimate A? Well, we can just run it and solve for A. So once we've decided that that exponent is 3, let's run it for some big N, and we get a pretty close model to the one we had from plotting things. So it's almost identical hypothesis, and we just got it by running the program doubling n each time. Okay, so there's a lot of effects in trying to understand the running time of a program on your machine. So key effects are independent of what computer it is, and that's the algorithm you're using and what's the data. And that's going to really determine the exponent in the power law. And then there's a lot of system-dependent effects. What kind of hardware do you have? Do you have a fast computer or a slow one? What kind of software? What's going on in your computer? All of those things really determine the constant A in the power law. So in modern systems, there's so much going on in the hardware and software, it's sometimes difficult to get really precise measurements. But on the other hand, we don't have to sacrifice animals or fly to another planet the way they do in other sciences. We can just run a huge number of experiments and usually take care of understanding these kinds of effects. Observing what's happening, as we did in the last section, gives us a way to predict performance, but it really doesn't help us understand what the algorithm's doing. So next we're going to look at mathematical model, a way to get a better concept of what's really happening. Again, this concept was really developed and popularized by Don Knuth starting in the late 60s. At that time, computer systems were really becoming complicated for the first time, and computer scientists were concerned about whether we really were going to be able to understand what's going on. And Knuth was very direct in saying that this is something that we certainly can do. We can calculate the total running time of a program by identifying all the basic operations, figuring out the cost, figuring out the frequency of execution, and summing up the cost times frequency for all the operations. You have to analyze the program to determine what set of operations, and the cost depends on the machine and the computer in the system, is what we talked about before. The frequency leads us to mathematics because it depends on the algorithm and the input data. Knuth has written a series of books that give very detailed and exact analyses within a particular computer model for a wide range of algorithms. So from Knuth, we know that in principle we can get accurate mathematical models for the performance of algorithms or programs in operation. All right, so what does this process look like? You can, if you want, run experiments. In ancient times, we would actually look at the computer manual, and every computer came with a manual that said precisely how long each instruction would take. Nowadays, it's a little more complicated, so we run experiments. And you can go ahead and do 1 billion ads and figure out that maybe on your computer an ad takes 2.1 nanoseconds. Or you can do more complicated functions like compute a sine or an arctangent, although that's already getting close to the analysis of algorithms. So there's some way to determine the cost of the basic operations. So we'll just, in most of the cases, we'll just postulate that it's some constant, and you can figure out what the constant is. Although when we're working with a collection of objects, of n objects, there's some things that take time proportional to n. Like if you're going to allocate an array of size n, it takes time proportional to n because in Java the default is that all the elements in the array are initialized to 0. In other operations, it depends on the system implementation. And an important one is string concatenation. If you concatenate 2 strings, the running time is proportional to the length of the string. And many novices programming in Java make the mistake of assuming that that's a constant time operation when it's not. All right, so that's the cost of each operation. More interesting is the frequency of operation, of execution of the operations. So this is a very simple variant of the 3-sum problem. That's the 1-sum problem. That's how many numbers are actually equal to 0, how many single numbers add up to 0. So that one is just one for loop, and we go through and we test if the number is 0 and increment our count. And by analyzing that code, you can see that I and count have to be declared, and they have to be assigned to 0. There's compares of I against n, and there's n plus 1 of them. There's compares of a of I against 0. There's n of those, n array accesses. And the number incremented is, number of times as an increment is variable. I is incremented n times, but count could be incremented any number from 0 to n times. And so that frequency is dependent on the input data. We might need a model for describing that, or maybe there's other operations that are more expensive and we won't need to worry about that. So let's look at next more complicated problem is what about the frequency of execution of instructions in this program, which is the 2-sum problem. How many pairs of integers sum to 0? Well, in this case, you have to do a little bit of math to see that when I goes from 0 to n and j goes from I plus 1 to n, the number of compares that we do, or let's say array accesses that we do, is 2 for each time the if statement is executed for ai and aj, and that time thing is executed n minus 1 times the first time through the loop, and n minus 2 the second, and so forth. It's the sum of the integers from 0 up to n minus 1, which is a simple discrete sum, 1/2 n times n minus 1, and since we're doing it twice, the number of array accesses is n minus 1. So we can go ahead and get these actual exact counts, but already it's getting a little bit tedious to do that. As far back as Turing, who also knew that, as well as Babbage did, that we want to have a measure of the amount of work involved in the process, he recognized that you didn't want to necessarily go through and do it in full detail. It's still helpful to have a crude estimate. So you could count up the number of times that every operation is applied, give it weights, and count this abstract and so forth. But maybe we should just count the ones that are most expensive. That's what Turing said in 1947. And realistically, that's what we do nowadays. So rather than going in and counting every little detail, we take some basic operation that's maybe the most expensive and or the one that's executed the most often, the one that cost times frequency is the highest, and use that as a proxy for the running time. Essentially making the hypothesis that the running time is going to grow like a constant times that. So in this case, we're going to pick array accesses. So that's the first simplification. And the second simplification is that we're going to ignore low-order terms in the formulas that we derive. And there's an easy way to do that. It's called the tilde notation. And the idea is when n is large in a formula like this, the n cubed term is much, much higher than the n term, or 16. In fact, so much so that we wouldn't even would hardly notice these low order terms. So all of these formulas are tilde 1/6 n cubed. And that's a fine representative or approximation to these quantities. And it greatly simplifies the calculations to throw away the low order terms like this. So by focusing on one operation and throwing away the tildes, the low order terms, and this is the technical definition of tilde, it just, f of n tilde g of n means the limit as f n or g n equals 1, and you can check that that's going to hold in these kinds of situations. So that greatly simplifies the frequency counts, and if we're only picking one thing, we're just talking about tilde n squared and maybe another tilde n squared for the increment for the two-sum problem, say. So again, when n is large, the terms are negligible. When n is really small, they're not negligible, but we don't really care because we're trying to estimate running times for large n, and running times for small n are going to be small no matter what. All right, so now we're using both the cost model and the tilde notation, and then we can simply say that this program uses tilde n squared array accesses and have implicit the hypothesis that we think the running time is going to be tilde a constant times n squared. Okay, well now what about three-sum? Let's do our real problem. So now we have the triple loop, and then we have to do a more complicated combinatorial problem. And it's not that big a deal, really. We're looking at the distinct number of ways you can choose three things out of n, and that's the binomial coefficient. And again, doing the math and using the tilde, it's just tilde 1/6 n cubed. 3 array accesses for each triple, so we can say half n cubed. We're not computing and summing the costs of all operations. That's too much work. We're picking the most expensive in terms of cost times frequency and approximating that and trying to get a good model for the running time. Now, we're not going to do a full discrete mathematics in this course, but there's some basic things that we'll want to use and are not that difficult to understand. So a lot of times we find out that we need to come up with an estimate of a discrete sum, like we did for 1 plus 2 up to n, or some of the squares, or other things like the three-sum triple loop. And so actually, if you've had basic calculus, one way to think of it is to just replace the sum with an integral. That usually works, or we can do the math and use the so-called Euler-Maclaurin summation formula to get a true approximation. But if you think of it this way, you'll believe us when we say that that thing is tilde half n squared, or sum of 1 plus 1/2 plus 1/3 up to 1 over n. That's like integral from x equals 1 to n 1 over x, and that's natural log of n. Even the three-sum triple loop, if you're used to multiple integrals, will quickly give you the 1/6 n cubed. There's many more and other techniques that we could use for this, and we're not going to teach all that, but we'll sometimes refer to results of this type. All right, so in principle, Knuth tells us that accurate mathematical models are available. In practice, we can get really complicated formulas. We also might need some advanced mathematics that the theoretician will revel in, but that maybe people learning algorithms for the first time might not be expected to know. In the end, careful, exact models are best left for experts. There's really a lot of things that can go on. On the other hand, approximate models are definitely worthwhile. And for all the algorithms that we consider, we'll try to communicate a reasonable approximate model that can be used to describe the running time. Sometimes we'll give the mathematical proofs, and other times we'll have to just cite the work of some expert. Now, fortunately, when we analyze algorithms, actually not too many different functions arise. And actually, that property allows us to really classify algorithms according to their performance as the problem size grows. So that's what we'll talk about next. So the good news is there's only these few functions turn up about the algorithms that we're interested in. We can craft things that have other functions, and there are counterexamples to this. But really, a great number of the algorithms that we consider are described by these few functions that are plotted here. When we're talking about order of growth, we're not talking about the leading constant. Normally we'll say the running time of the algorithm is proportional to n log n. That means we think that our hypothesis is that the running time is tilde c log n, n log n, where c is some constant. And in these plots, these are log-log plots that really give a good idea of what's going on. If an order of growth is logarithmic or constant, it doesn't matter how big the thing is, it's going to be fast. If the running time is t for, say, 1,000, then for 500,000, it'll be pretty close to t. If it's linear, if its order of growth is proportional to n, then as the running time, as the size increases, the running time increases correspondingly. And the same is true almost if it's n log n. So those are the algorithms that we strive for. They scale with the input size. As the input grows, so grows the running time, and that's a reasonable situation to be in. As we talked about when we talked about union find, if it's quadratic, the running time grows much faster than the input size, and it's not feasible to use such an algorithm for large inputs. And cubic is even worse. So what we find is for many algorithms, our first task is really simply make sure it's not quadratic or cubic. And these order of growth classifications actually come from kind of simple patterns in terms of the code that we write. So if our code has no loops in it, then the order of growth is going to be constant. If our code has some kind of loop where the input's divided in half, and so binary search algorithm is an example of that, then our order growth will be logarithmic, and we'll take a look at that analysis. But if you do the doubling test, it grows almost linearly. If you have a huge input and you double the size, it's still going to be, I'm sorry, not linearly, constant, just like if it's constant. You'll hardly notice that log n. If you have a loop where you touch everything in your input, then the running time is linear, proportional to n. So a typical example of that would be find the maximum or count the number of zeros, our one-sum problem. A very interesting category is the so-called n log n algorithms or linear arithmetic algorithms. And those are the ones that arise from a particular algorithm design technique called divide and conquer. And the merge sort algorithm, which we'll talk about in a couple of weeks, is a prime example of that. And then if you have double for loops, like our two-sum algorithm, that's going to be time proportional to n squared, as we saw. That's quadratic. Or triple for loop, like our three-sum algorithm, that's going to be cubic or time proportional to n cubed. For a quadratic algorithm or a cubic algorithm, the doubling factor is 4 or 8. As the input size doubles for a cubic algorithm, the running time goes up by a factor of 8. And that's the kind of calculation you can do in your head while waiting for a program to finish. There's also a category of algorithms whose running time is exponential. And in those algorithms, n doesn't get very large at all. And we'll talk about those at the end of part 2 of the course. So these are some practical implications of the order of growth. And I won't really dwell on this too much, except to come back to the point that the algorithms that we're really interested in that can solve huge problems are the linear and n log n algorithms. Because even now, a quadratic algorithm on a typical fast computer could only solve problems in the tens of thousands, and a cubic algorithm only in the size of thousands. And nowadays, those are just not useful because the amount of data that we have is more like the millions, billions, or trillions. That fact is becoming more and more evident as time wears on. In ancient times, we'd have some discussion about whether a quadratic algorithm might be useful, but the situation gets worse as time gets on, so we need better algorithms. To illustrate the process of developing a mathematical model for describing the performance of an algorithm, we'll look at a familiar algorithm called binary search. The goal is that you have a sorted array of integers, say, and you're given a key, and you want to know, is that key in the array? And if it is, what's its index? And a fast algorithm for doing this is known as binary search, where we compare the key against the middle entry. In this case, if we're looking for 33, we compare it against 53. If it's smaller, we know it's in the left half of the array. If it's larger, we know it's in the right half of the array. If it's equal, we found it. And then we apply the same algorithm recursively. So let's quickly look at a demo. So we're looking for 33 in this array. We compare it against the middle entry in the array, 53, and it's less, so we go left. So now we can concentrate just on the left half of the array. Now we look in the middle of this half, that's 25. 33 is bigger, so we go right. Now we concentrate on the right half of the left half, and we have a smaller subarray. Look at the middle. 33 is less, so we go left. And now we have only the one element to look at, and we found our key 33 in the array, and we return that index 4. If we're looking for something that's not in the array, we do the same process. So say we're looking for 34, it's going to be the same. Look in the left half, look in the right half, look to the left of the 43. Now there's only one key to look at, and it's not 34, so we say it's not there. So that's binary search. So here's the code for binary search. Binary search, although it's a simple algorithm, it's notoriously tricky to get every detail right. In fact, one paper claimed that the first bug-free binary search wasn't published until 1962. And even in 2006, a bug was found in Java's implementation of binary search. Just an indication of the care that we have to take in developing algorithms, especially for libraries that are going to be used by millions of people. So here's an implementation. It's not recursive, although often we can implement this recursively. And it's just reflects in code what I described in words. If we have to find whether keys in an array, we use two pointers, low and high, to indicate the part of the array that we're interested in. As long as low is less than or equal to high, we compute the middle, and then we compare our key against the middle. Actually, it's a three-way compare. It's either less or it's greater, or if it's equal, we return that mid-index. If it's less, we reset the high pointer. If it's greater, we reset the low pointer, and we keep going until the pointers are equal. If they're equal and we haven't found it, then we return -1. And it's easy to persuade ourselves that this program works as advertised by thinking about this invariant. If the key is in the array, then it's between low and high in the array. All right, so that's a program that you're probably familiar with. Let's look at the mathematical analysis of that program. And this is a theorem that we're going to prove. We won't do a lot of proofs, but this one's worth doing. So it says that binary search uses at most 1 plus log base 2 of n compares to complete a search in a sorted array of size n. So we do that, set up the problem by defining a variable t of n, which is the number of compares that binary search is going to need for an array of size n. And then we write down a recurrence relation that reflects the code. And what the code does is it divides the problem size in half so that t of n is less than or equal to t of n over 2, plus, depending on how you count what the compare is, think of it as really a two-way compare. So divide it in half by doing one compare. And that's true as long as n's bigger than 1. If n's equal to 1, the solution is 1. So that's a recurrence relation describing the computation. And so we can go ahead and solve this recurrence by applying the recurrence itself to the first term on the right. That's called telescoping. So if this is true, then we can apply the same thing to t of n over 2 and throw out another 1. And if this is true, we can apply the same thing to n over 4 and throw another 1, and so forth, until we get down to just 1, in which case we have log n 1s left. Now, this is a proof sketch. You might have noticed that this proof actually only holds if n is a power of 2, because we didn't really specify in this recurrence what we mean if n is odd. But it's possible to go ahead and, take care of that detail as well and show that binary search running time is logarithmic always. All right, so given that fact, we can develop a faster algorithm for 3-sum. It's a sorting-based algorithm. And so what we're going to do is we're going to take the numbers that we have as input and sort them. We'll talk about sorting algorithms next week. And we can get that done in time proportional to n log n, but that's not the main part of the computation. The main part of the computation is after the numbers are sorted, we'll go through and for each pair of numbers, AI and AJ, we'll do a binary search for minus AI plus IJ. If we find it, then we have three numbers that sum to 0. So we sort our numbers and then go through for each pair, do a binary search to see if it's there. So minus 40, 0, minus that is 40. We do a binary search that's in there. So we have one solution to the three-sum problem. And do that for all pairs of numbers. Then a quick analysis says the order of growth of the running time is going to be n squared log n. You don't even need a good sort. You could use the elementary insertion sort, the first one we talk about. But the running time of the binary search for each of the pairs, each of the n squared pairs, or n squared over 2 pairs, we're going to do a binary search, so we get an n squared log n running time. So it's a quick example of how we can improve the performance. We can find an improved algorithm to solve a problem. N squared log n is much less than n cubed for large n. And so we're implicitly making the hypothesis that if we do this sort-based thing and use binary search, we're going to have a faster program. And sure enough, we can go ahead and run some experiments and find that whereas it took us 50 seconds to solve the problem for 8,000 numbers before, it's taking less than a second now. In 50 seconds, we can solve up to 64,000. So typically, we expect that better order of growth means faster in practice. But when it comes to examining the algorithms in detail, we can go ahead and do the tests and figure out which algorithm is faster. Certainly, going from n cubed to n squared log n, we're going to expect that we're going to have a much better algorithm. In fact, order of growth classifications are so important, they've led to an enormous amount of research in recent years, and we'll just talk briefly about that now. Life is a little bit more complicated than pointed out in the last example. And one problem is that the inputs can cause the performance of the algorithm to vary widely. So often we have to think about different ways of analyzing the algorithm depending on the input. So the running time is going to be somewhere between the best case and the worst case. Best case is a lower bound on costs. It provides something that the running time is going to be bigger than that always, or not less than that. And then there's the worst case, which is the most difficult input. If we analyze that, then we can guarantee that the running time of the algorithm's not going to be bigger than that. And then in a lot of situations, we might consider our input to be random. Well, we need some way to model what we mean by random for the problem that we're solving. But there's a lot of situations where we can do that, and then we have a way to predict performance. Even when the input might vary widely. So, for example, for three-sum, it's kind of always the same. With the tilde notation, the only variability in that algorithm is the number of times the counter is incremented, and that's in low-order terms, so it doesn't even show up in our analysis. For binary search, you might find the thing right away, in which case it's constant time, and we can show that the average in the worst case are both log base 2 of n. And there's in other examples there'd be much more variability even. we have these different types of analyses depending on the input. But the question is, what about the actual problem that the client's trying to solve? So we have to understand that too in order to be able to understand performance of the algorithm. And there's two approaches that are successful in this. One is to design for the worst case. Just make sure your algorithm always runs quickly, and that's definitely ideal. Another is to, if you can't do that, is to randomize and then depend on some kind of probabilistic guarantee. We'll see examples of both of these as we go through the course. Now, those kinds of considerations and the idea of order of growth leads to a discussion of what I call the theory of algorithms. And here our goals are, we have a problem to solve, like solve the three-sum problem, and we want to know how difficult it is. We want to find the best algorithm for solving that problem. Now, the approach that computer scientists use for this is to try to suppress as many details as possible in the analysis. And so just analyze the running time to within a constant factor. That's what order of growth is getting at. And also, we want to not worry about the input model at all. And so we focus on worst case design. Then we can talk about performance of algorithms just in terms of the order of growth. And it's actually possible to do that in a very rigorous way that has taught us a lot about the difficulty of solving problems. And our goal is to find an optimal algorithm where we can guarantee to within a constant factor certain performance for any input, because we discovered worst case. But we also can have a proof that no algorithm can provide a better performance guarantee. I'll give a couple of easy examples of this. Now, in order to do this, there are these commonly used notations called the big theta, big O, and big omega notations. And those definitions are given here. So the big theta notation is just a way to describe the order of growth. Theta of n squared is kind of shorthand for anything times n squared. It's bounded above and below by constant times n squared. And that's what we really use to classify algorithms. And then there's big O notation, which is upper bounds on performance. When we say big O of n squared, we mean that it's less than some constant times n squared as n grows. And big omega is used for lower bounds, which means it's greater than some constant times n squared as n grows. So those three notations we're able to use to classify algorithms, and I'll show in the following. So the examples are from our one-sum, two-sum, and three-sum are easy to articulate. So our goals are to establish the difficulty of the problem and develop an optimal algorithm. So the one-sum problem, is there a zero in the array? Well, an upper bound on the difficulty of the problem is some specific algorithm. So, for example, the brute force algorithm that looks at every array entry is a specific algorithm. And it means that, and that takes O of n time. You have to look at it's less than a constant times n for some constant. So the running time of the optimal algorithm has to be O of n. That is, that specific algorithm provides an upper bound on the running time of the optimal algorithm. But in this case, it's also easy to develop a lower bound. That's a proof that no algorithm can do better. Well, for one sum, you have to examine all entries in the array. If you miss one, then that one might be zero. So that means that the optimal algorithm has to have a running time at least some constant times n, or we say the running time is omega of n. Now in this case, the upper bound and the lower bound match. So to within a constant factor, so that's a proof that the brute force algorithm for one sum is optimal. Its running time is theta of n. It's both omega n and O of n. That's, for that simple problem, it was okay to get the optimal algorithm. For more complicated problems, it's going to be more difficult to get upper bounds and lower bounds, and particularly upper bounds and lower bounds that match. For example, let's look at threesum. So upper bound for threesum, say our first brute force algorithm said that the proof was a proof that the running time of the optimal algorithm is O of n cubed. But we found a better improved algorithm whose running time is O of n squared log n. So that's a better upper bound. Lower bound, well, we have to examine all entries because, again, we might miss one that makes threesum equal 0. And that's a proof that the running time of the optimal algorithm is omega of n. But nobody knows a higher or lower bound for threesum. So there's a gap between the upper bound and the lower bound in open problems. Is there an optimal algorithm for threesum? We don't know what it is. We don't even know if there's a algorithm whose running time is less than O of n squared, or we don't know a higher or lower bound than linear. So that's an example of an open problem in the theory of algorithms. We don't know how difficult it is to solve the threesum problem. Now, this point of view has been extremely successful in recent decades. We have a new problem, develop some algorithm, prove some lower bound. If there's a gap, we look for a new algorithm that will lower the upper bound, or we try to find a way to raise the lower bound. Usually it's very difficult to prove non-trivial lower bounds. Trivial lower bound, like look at every input item, is not so hard. Non-trivial lower bounds, like for example, the proof that we talked about for the union find problem, are much more difficult. And in the last several decades, people have learned about the computational difficulty of problems by examining steadily decreasing upper bounds. So algorithms with better worst case running times for lots and lots of important problems, and plenty of optimal algorithms, and plenty of gaps still remain. It's a fascinating field of research that many people are engaged in. Now, there's a couple of caveats on this in the context of this course. And the first one is maybe it's overly pessimistic to be focusing on the worst case. We've got data out there, we've got problems to solve, maybe it's not worst case data. In lots of fields of engineering and science, we don't focus on the worst case. The worst case for this course would be for lightning to strike and it would be over. So we don't plan for that. And similar is true for algorithms. Maybe we should be focusing on understanding properties of the input and finding algorithms that are efficient for that input. And the other thing is, in order to really predict performance and compare algorithms, we need to do a closer analysis than to within a constant factor. We talked about the tilde notation in the big theta, big O, and big omega that are used in the theory of algorithms. And really, there's so much published research in the theory of algorithms that a lot of people make the mistake of interpreting the big O results that are supposed to give improved upper bounds on the difficulty of the problem as approximate models for the running time, and that's really a mistake. So in this course, we're going to focus on approximate models by making sure that we use the tilde notation. And we'll try to give specific results for certain quantities of interest, and the constant, any unspecified constant in the running time will have to do with properties of the machine and the system, so that we'll be able to use these results to predict performance and to compare algorithms. So far we've been talking about running time. Now we have to talk about the memory requirements of our programs as well. Well, the basics are we want to know how many bits the program uses, or bytes, 8 bits at a time. And actually we'll be talking in terms of millions of bits or billions of bits. And actually, surprisingly, there's controversy about even these basic definitions. Computer scientists think of 1 million bits as 2 to the 20th and 1 billion as 2 to the 30th. Because that's the number of possible things that you can fit into the 30 bits, and everything is consistent with our calculations. Other scientists stick to 1 million and 1 billion for lots of reasons. We'll usually use 2 to the 20th to mean a megabyte. Now, on old computers, we used to, for many years, use a 32-bit machine so that pointers were 4 bytes. Just in recent years, we've mostly switched to a model where machines are 64 bits and pointers are 8 bytes. That allows us to address much more memory, but pointers use much more space. And actually, this transition caused a lot of problems initially because programs were using way more space than people thought they should. You're not going to have to go through this kind of transition the way that we did because 64 bits is definitely enough to address anything that you might need to address. 2 to the 64th is really a huge number. So in terms of bytes, we have to start out with typical memory usage. Now again, this is very dependent on machine and implementation, but these numbers are reasonable and are found on typical implementations. So a Boolean, it would be nice if a Boolean just took a bit because it's just true or false, but actually usually we have to count for a byte for a Boolean. Well, a byte is a byte. Character nowadays is 2 bytes, 16-bit characters. Not that long ago, we used 8 bits for chars. Integer, regular int is 4 bytes or 32 bits, and float is also 4 bytes. Long int is 8 and a double is 8. Usually we use doubles for floating point and ints for integers in most applications. So that's for primitive types. And then for arrays, there's a certain amount of overhead for making an array, and then if there's n items, it's whatever the cost of the primitive type times n. So an array of doubles is, say, 8n plus 24. And two-dimensional array, then, well, we can go ahead and compute the exact thing, but now it's time to use the tilde notation. Even for arrays, we could say a double is tilde 8n for one-dimensional. For two-dimensional, two-dimensional array of doubles is tilde 8mn. And there's extra terms for the overhead, but for large m and n, that's going to be pretty accurate. So that's our basic usage for primitive types and arrays in a typical Java implementation. Now, a lot of our programs use objects like linked lists and so forth, so we have to also factor in object overhead, cost of a reference, and also there's padding built in typical implementations to make it so that each object has to use a multiple of 8 bytes. So, for example, if you had a date object that had 3 int instance variables, then that object would take a total of 32 bytes. Each int takes 4 bytes. Object overhead is 16 bytes. You need 4 bytes for padding, so it's a total of 32 bytes. And the other one that often comes up is a string, and a string is a little bit more complicated than an array, but the typical implementation of a string in Java has a reference out to an array of characters, and then it's got int values for offset, count, and a hash value, and then some padding. And adding it all together, the cost of a string is about 2n plus 64 bytes. So these are the basics that we need to analyze the memory usage for a typical Java program. So for data type value, if it's a primitive type, it's 4 for an int, 8 for a double, and so forth. If it's a reference, it's going to be 8 bytes. That's what a pointer takes. Array, 24 bytes plus the memory for each entry, and an object, 16 bytes plus the memory for the instance variable. Plus, if there's an inner class, it's another 8 bytes, as we talked about with nodes for linked lists. And then there's the padding. Then we have to think about who's responsible for referenced objects in some cases. And we'll take care of that when we get to these situations. So as an example, a simple example of memory use analysis, let's take a look at how much memory our weighted quick union UF function from a few lectures ago uses as a function of n. And there's only a couple of memory elements, and each one of them are easily analyzed using the basics that we just gave. It's an object, so there's 16 bytes of object overhead. There's 2 int arrays. Each one of them have array overhead of 24 plus, and then 4n for the n entries. Each n of the n entries takes 4 bytes. And then there's 4 bytes for the count, and there's 4 bytes for the padding, and if you add it all together, it's 8n plus 88, which is tilde 8n. And again, all that's saying is when n is large, all we are going to care about in terms of analyzing the memory is that we've got 2 n integers, 2 arrays of size n, each one of which takes 4 bytes for a grand total of 8n bytes. Okay, so in summary, we really can figure out how many times we have to turn the crank on modern computers. We can do it with empirical analysis, where we actually execute the program to do experiments and assume a power law, formulate a hypothesis, and make predictions. But we can do more. We can do mathematical analysis, where we can identify the most costly operations, analyze the frequency of execution of those operations, and using the tilde notation to simplify analysis, we can actually explain the behavior, not just predict it. And this is a fine example of the use of the scientific method to understand the artifacts that we're studying, the algorithms. Our mathematical models are usually independent of a particular computer system and even applied to machines that are not yet built. But we always validate our mathematical models by running experiments on real machines so that we can be confident when we're making predictions and analyzing algorithms. Welcome back. Today we're going to talk about algorithms and data structures for implementing some fundamental data types called bags, queues, and stacks. You may be somewhat familiar with these, but today we're going to take a careful and close look at them. The idea is that in many applications we have collections of objects that we want to maintain, and the operations are very simple. We want to add something to the collection, maybe remove something from the collection, and iterate through the objects in a collection, performing some operation on them, and of course test if it's empty. Now for most of these, the intent is very clear. The key is, when it comes to removing an item, which item do we remove? The 2 fundamental classic data structures for this, the stack and the queue, differ in the way in which the item to be removed is chosen. For the stack, we take out the item that was most recently added. For the terminology that we use is push to insert an item and pop to remove the item most recently added. That's also called the LIFO discipline, last in, first out. For queue, we examine the item least recently added. In those operations, to distinguish them, we call NQ to insert an item and DQ to remove an item. And that's also called the FIFO discipline, first in, first out. So now we're going to take a look today at how to implement these things. Our subtext today is all about modular programming. And that's going to be a discipline that we're going to follow carefully throughout this course. The idea is to completely separate the interface and the implementation. So when we have these types of data structures and data types that are precisely defined, like stacks and queues and so forth, what we want to do is completely separate the details of the implementation from the client. The client can have many different implementations from which to choose, but the client code should only perform the basic operations. The implementation, on the other hand, can't know the details of the client needs. All it's supposed to do is implement those operations. In that way, many clients can reuse the same implementation. So this allows us to create modular, reusable libraries of algorithms and data structures that we can use to build more complicated algorithms and data structures. It also allows us to focus on performance when appropriate. Again, this is a modular programming style that's enabled by object-oriented programming languages such as Java, and we'll be very disciplined in our use of this style. All right, so to begin, we'll talk about stacks. Stacks are familiar. Many of you probably implemented stacks in an introductory programming course, but we'll do a thorough introduction to implementations right now. As a warm-up, let's suppose that we have a collection of strings. And they might be short, they might be long, and what we want to have is the ability to save away a collection of strings and remove and return the most recently added string periodically, and also test if it's empty. So that's our API. We have a constructor to create an empty stack. We have for insert, we have a method called push that takes a string as argument. And for remove, we have a method pop that returns the string most recently added. And we have an isEmpty test which returns a Boolean. Also in some applications, we would include the size as well. So again, as always, we'll first write a client and then look at implementations. And our client, simple client, is to take some strings on standard input and some pop commands which are indicated with hyphens. And so this client reads strings from standard input. If the string is equal to the hyphen character, it'll pop the string at the top of the stack and print it. Otherwise, if it's a string that's not equal to the hyphen character, it'll just push it onto the stack. So in the example down below here, if we have this file called tob.txt, then what the client will do is push to, be, or not to all on the stack. Then when it comes to this hyphen, it'll pop the most recently inserted item, which is 2 in this case. Then it'll put B on the top of the stack, and then pop the top item on the stack, which is now B, and then pop the item most recently added. B's gone, 2's gone, so the next is not, and so forth. So this is a simple test client that we can use to test our implementations. So now let's look at the code for implementing a stack. The first implementation that we'll look at uses linked lists. If you're not familiar with linked lists, you'll need to review that in section 1.1 through 1.3 of the book, or in our Introduction to Programming in Java book. Even if you are familiar with linked lists, it's worth taking a look at this code because it's the style of coding that we'll use throughout the course for much more complicated data structures. So the idea is to keep a linked list which consists of nodes that have strings in them and references to the next item in the linked list. And to implement a stack, when we do a push operation, we insert a new node at the beginning of the linked list. And we do a pop operation, we remove the first node from the beginning of the linked list. That's the most recently added item. So let's look at what that code looks like. We use to implement linked lists in all linked data structures throughout the course, we use what's called an inner class in Java. And that's just a way to describe that we're going to be manipulating node objects that each consists of a string and a reference to another node. So the pop operation for linked lists is very easy to implement. First, we're going to need to return the first item on the list, So we save that away. Take first.item and save that in the variable item. Then to get rid of the first node, we just advance our pointer to the first item on the list to point to the next item. And then that first node is ready to be reclaimed by the garbage collector. And then the last thing we need to do is just return the item that we saved away. Okay, so that's the pop operation. What about the push operation? Push operation, we want to add a new node at the beginning of the linked list. So first thing we do is save away the pointer to the beginning of the list. That's old first equals first. Then we create a new node that's going to be the new node that we put at the beginning of the list. That's first equals new node. And then we set its instance variables. Its item is the string that we want to put at the beginning of the list, in this case not. And its next is the old first item of the list, which is now the second item of the list. So after this operation, we have first pointing to the beginning of the list, and we have the items on the list in decreasing order of when they were put onto the stack. So that also is a four-liner to implement the stack push operation. So this is a complete linked list implementation of all the code to implement a linked list for a stack of strings in Java. It's a class. The constructor doesn't have to do anything. There's no constructor. We have this inner class that we use to build the items in the linked lists, and we make it an inner class so we can directly refer to those instance variables. And then the only instance variable of a stack is a reference to the first node on the list, and it starts out being null. Then is empty is just testing whether the first node on the list is null. And then push is the 4 lines of code that I gave on the previous slide, and pop is the 3 lines of code that I gave on the slide before that. That's a complete implementation for linked lists that'll work with as a fine push-down stack implementation for any client. So now we can analyze the performance of that so that we can provide clients with information on how well the algorithm data structure will perform. In this case, it's easy to see that every operation takes constant time in the worst case. There's only a few instructions for each one of the operations. There's no loops. So that's obviously a very desirable characteristic. Then how about space usage? Well, that depends very much on the implementation in the machine. So this is a typical Java implementation that we do the analysis for and can test this out for different types of environments easily. And it's representative. So in Java, an inner class, there's for every object, there's 16 bytes of overhead. There's some extra overhead, 8 bytes, because it's an inner class. And then there's 2 references that we built in our class node, one to a string and another one to a node, and those are each 8 bytes. So we have 40 bytes per stack node. If we have a stack of size n, we have about 40 n bytes. There's a little extra for first, but that's about an overhead for the whole stack. But when n is large, 40n is a very close estimate to the amount of space needed. This does not include the space for the strings themselves, which are owned by the client. But with that, we can properly assess the resource usage of this implementation for different client programs. Now, it's constant time, but there's faster implementations of stack. And since stack is used in an inner loop of some algorithms, it's important to think about even faster implementations. And another natural way to implement a stack is to use an array to store the items on a stack. So let's take a look at that. This alternative of choosing between linked structures and arrays is fundamental, and it's going to come up again and again when we consider more complicated data structures and algorithms. So we want to be sure to analyze it in this simple case for stacks to set the stage for more complicated applications later on. All right, so to use an array, we just keep the n items on the stack in the array. And the array location with index n is the place, the top of the stack, where the next item is going to go. So to push, we just add a new item at s of n, and to pop, we remove the item that's at s of n minus 1 and decrement n. Now there's a fundamental defect in using an array, and that is that you have to declare the size of the array ahead of time, and so the stack has a certain capacity. And if there's more items on the stack than the capacity, we have to deal with that problem. And that's a fundamental problem that we have to deal with in array implementations in all sorts of algorithms and data structures. So again, considering it for this simple case will pay off later on. All right, so here's the full implementation of stack for using an array to represent the stack. So now we have an instance variable, which is an array of strings, and our variable n, which is both the size of the stack and the index of the next open position on the stack. This one has a constructor, and the constructor creates the array. Now, we're cheating in this implementation to keep it simple, and we'll take care of this cheat in a little while, by requiring the client to provide the capacity of the stack. In a few applications, this might be fine, but in many, many applications, that's too onerous a requirement. The client really can't know how big the stack is. The client might have a lot of stacks that need to be maintained simultaneously, and maybe they reach their maximum capacities at different times, and various other things. So we need to remove this cheat, and we will. But the code is nearly trivial if we have the capacity. To check if it's empty, we check if n is 0. To push an item, we use n to index into the array, put the item there, and then increment n. That's the shortcut in many programming languages nowadays for use the index and then increment it. And to pop, we decrement the index and then use it to return the item in the array. So each of the operations is a one-liner. And this is a fine implementation for some clients. That's array implementations of stack, but it breaks the API by requiring the client to provide the capacity. So what are we going to do about that? Well, there are a couple of things that we didn't consider. We didn't put in code to throw an exception if the client pops from an empty stack. Probably should do that. And for overflow, what happens when the client does too much? Well, we're going to talk about an approach called resizing that will allow us to avoid overflow for clients. There's another issue about whether clients can insert null items into the data structure. In this case, we do allow the client to insert null items. But we do have to worry about, in Java, about a problem called loitering, and that is the idea that we have references to an object in our array implementation in the stack array when we're not really using it. So when we decrement that value in, there's still a pointer to the thing that we took off the stack in that array, even though we know we're not using it. The Java system doesn't know that. So to avoid that and really allow most efficient use of memory, it's best to set that removed item entry to null, so there's no reference to the old item left there, and then the garbage collector can reclaim the memory since there's no outstanding references. So that's a detail, but an important one that we have to take care of in our implementations to make sure that we're getting most efficient use of memory. Okay, our basic array implementation of stacks had a defect where we required clients to provide the maximum capacity of the stack ahead of time. Now we're going to look at a technique for resolving that problem. How do we're not implementing the API. The API says we should just be able to create a stack and it should be able to grow and shrink to any size. So how are we going to grow and shrink the array? Well, first thing you might think of is when the client pushes the new item onto the stack, increase the size of the array by 1, and when it pops, decrease the size of the array by 1. That's easy to code up, but not worth it because it's much too expensive to do that. The reason is that you have to create a new array, size 1 bigger, and copy all the items to that new array. So inserting the first n items would take time proportional. If the stack's of size n minus 1, it's going to take time n minus 2 time n minus 1. So first n items would take the sum of the first n integers, which we know is about n squared over 2. Quadratic time to insert n items into a stack, that kind of performance is unacceptable for large problems as we've seen, as we will see many times. So the challenge is to do the resizing, but somehow ensure that it happens infrequently. So the well-known technique for doing that, called repeated doubling, is to, when the array fills up, create a new array of twice the size and copy all the items over. Then we don't create new arrays all that often. So here's an implementation of that. We start with an array of size 1. If we have a full stack, which we know by testing n, which is the number of items in the stack, versus the array length, then we just resize the array into one of twice the length before inserting the item. And how do we resize to a new capacity? We create a new array of that capacity and just go ahead and copy our current stack into the first half of that, and then return it. And that will reset our instance variable, which is our stack, to this new bigger array. So the idea and the consequence of this is if you insert n items into an array, into a stack with this array representation, the time will be proportional to n, not n squared. And the reason is that you only create a new array every time it doubles. But by the time that it doubles, you've inserted that many items into the stack. So on average, it's like adding one operation to cost of 1 to each operation. So if you just calculate the cost of inserting the first n items, you're going to have, instead of the sum of the integers from 1 to n, you're going to have the sum of the powers of 2 from 1 to n. And that'll give a total cost of about 3n. So that's array accesses. So for the copy, there's 2 array accesses. So to insert n items, it's about 3 array accesses. This plot is another way of looking at it, which is the number of array accesses taken as you implement push operations. Every time you hit a power of 2, you take that many array accesses, but in a sense, you've already paid for them by putting those items on the stack. So that's called amortized analysis, where we consider the total cost averaged over all operations. And this is a fine example and useful example of amortized analysis to get efficiency in a stack implementation. Now, what about the pop? We have to think about how to shrink the array. So you might think, well, we doubled it when it was full. Why don't we cut it in half when it gets to be half full? We don't want the array to get too empty. Well, that one doesn't exactly work because of a phenomenon called thrashing. If the client happens to do push pop, alternating when the array is full, then it's going to be doubling, halving, doubling, halving, doubling, halving, creating new arrays on every operation, take time proportional to n for every operation, and therefore quadratic time for everything. So I don't want to do that. The efficient solution is to wait until the array gets 1/4 full before you have it. And that's very easy to implement. We just test if the array is 1/4 full. If it is, we resize it to half full. And so then at that point, it's half full. And it can either grow by adding stuff or shrink by subtracting stuff, but there won't be another resizing array operation until it either gets totally full or half again full. So the invariant of that is that the array is always between 25% and 100% full, number one, and number two, that every time you resize, you've already paid for it in an amortized sense by inserting, pushing or popping. So here's just what happens to the array for our small client example. And you can see at the beginning it doubles from 1 to 2 to 4, but once it gets to 4, it stays, once it gets to 8, it stays at that size for a while, even though there's some operations. And it doesn't shrink back to 4 until after there's only 2 items in there, and then it shrinks and so forth. So array resizing doesn't happen that often, but it's a very effective way of implementing the Stack API with an array where the client does not have to provide this maximum capacity of the stack, but still we're guaranteed that the amount of memory that we use is always only a constant multiple of the number of items actually on the stack. So the analysis now says that the average running time per operation for whatever the sequence of operations is, the average running time is going to be proportional to a constant. Now, there is a worst case, that is at the point when the stack doubles, it takes time proportional to n. So it's not quite as good performance as we might like, but it's what the advantage that we get is very fast pushes and pops, just access array and increment it, and very efficient for most operations. And for many, many clients, that's an effective trade-off to make. So what about memory usage? Well, this is the analysis of memory usage for stacks, and it's actually less memory than for strings. The amount used is between 8n and 32n, depending on how full the array is, and just a quick analysis of the amount of space that arrays take in Java. So again, this analysis is just for the stack itself, not for the strings, which the client owns. So what are the trade-offs between using a resizing array versus a linked list? Those are two different implementations of the same API, and the client can use them interchangeably. Which one is better? In many situations, we're going to have multiple implementations of APIs, and depending on properties of the client program, we're going to have to choose which one is the better one to use. So for linked lists, every operation takes constant time in the worst case. That's a guarantee, but we have to use a little extra time and space to deal with the links. So it's going to be slower. Resizing array implementation, we have a good amortized time, so total averaged over the whole process is good. We have less wasted space and probably faster implementation of each operation. And so for some clients, maybe that makes a difference. Perhaps you wouldn't want to use a resizing array implementation at the moment that your plane's coming in for a landing. You wouldn't want it to all of a sudden not implement some operation quickly. If you need that kind of, or maybe in an internet switch where packets are coming through at a great rate, you wouldn't want to be in a situation where you're missing some data because something got slow all of a sudden. So that's a trade-off that the client can make. If I want that guarantee, if I want to be sure that every operation is going to be fast, I'll use a linked list. And if I don't need that guarantee, if I'm just care about the total amount of time, I'll probably use the resizing array because the total will be much less because individual operations are fast. So even with these simple data structures, we have really important trade-offs that actually make a difference in lots of practical situations. Okay, next we'll briefly consider queue implementations using the same basic underlying data structures. So here's the corresponding API for queue of strings. Actually, it's the same API as for stacks, just the names are different. Instead of push, we have enqueue. Instead of pop, we have bqueue. And the semantics is different. For NQ, we add an item, say, at the end of the queue, and for DQ, we remove an item from the beginning. It's as if you're waiting in line to buy a ticket. When you NQ, you go at the end, and when the one that's been in there the longest is the one that comes off. So let's look at how we implement those, first using linked lists and then arrays. So now our representation of a queue with a linked list, we need to maintain 2 pointers, references, one to the first item in the list and the other to the last item in the list. When we insert, we're going to add the item at the end of the list instead of at the beginning, and when we remove, we'll do the same, we'll take it off the front. So here's the implementation of DQ. It's identical to the code for POP for a stack. We save away the item, we delete the first node by advancing the reference, and then we return the item. So identical. To add a node, or NQ, add a new node to a linked list, we want to put it at the end, so that'll be the last one returned. To add it at the end, so first thing we need to do is save a link to the last node. We're going to need that because we need to change its reference from null to point to the new node. Then we'll create a new node for the end of the list. We'll populate its fields, and then that old link will change that from null to a pointer to the new node. So again, just a few lines of code. That's basic linked list processing. Actually, years ago when we taught courses in algorithms and data structures, much of the course would be about this kind of pointer manipulation. But nowadays, that's restricted to just a few implementations like stack and queue and a few other fundamental data structures. So we don't need so much anymore general programs for manipulating linked lists. We encapsulate them in basic data types like these. All right, so let's go back to our full implementation. And this is just taking care of collecting the code from the previous slides, but also taking care of special cases when the queue is empty. To make sure that if the queue is empty after we remove an item, we have to set last to null. Make sure that both first and last always are what we want them to be. So those are details that are easy to check. Okay, what about arrays? Well, we won't do the details, but it's not difficult to implement queues with resizing arrays as well. Not difficult, but definitely a tricky programming exercise that people are welcome to try. So we'll maintain 2 pointers, the first item in the queue and the tail, which is the position for the next item to appear. So for NQ, you add a new item at tail, and for DQ, you remove an item for head. And the trick is that once you get past the capacity, you have to reset back to 0. So that's a little extra code. And then you have to add the resizing capability as well to implement the data structure the same as for stack. And we'll leave that as an exercise. Next, we're going to consider addressing another fundamental defect in the implementations we've considered so far, that those implementations are only good for strings. What if we want to have queues and stacks of other types of data? And that brings us to the topic of generics. All right, so we implemented stack of strings, but in applications, we have all different types of data that we might want to implement, like stack of ints, say, or URLs, or cars, or vans, or whatever data that we might be processing. So how are we going to implement stacks and queues for that types of data? Well, the first thing that we might consider, and actually we're forced to consider this one in lots of programming environments, is to implement a separate stack class for each type of data that we're using. That really seems unsatisfactory. We have our carefully crafted code that does array resizing and so forth, and we're going to copy that code and change the data type string to the data type van or int everywhere. And what if we have hundreds of different types of data that we're processing? We're going to have hundreds of different implementations. Unfortunately, that situation at the beginning of Java, we were stuck with that, and there are plenty of programming languages where basically we're stuck with that. So what we want to look at is a modern approach to avoiding having multiple implementations for each type of data. A quick hack that is widely used is to use casting to implement to reuse the code for different data types. So we make our implementation with type object. So everything in Java is a subtype of object. And then the client, when the client comes to use it, will simply cast the result to the corresponding type. I don't want to spend a lot of time on this because I think this is an unsatisfactory solution. So in this example, we have two types, we have two stacks, one of apples and one of oranges, and then it's up to the client when it pops something off the apple stack to cast it to apple to keep the type checking system happy. The problem with this is that the client code has to do this casting, and it's kind of an insidious bug if it doesn't quite get it. So the third attempt that we're going to talk about uses generics. And that way, the client code doesn't do casting. We can discover mistakes in type mismatches at compile time instead of at runtime. So in this case, we put, with generics, we can have a type parameter on our class, and that's inside angle brackets in this code. And then we can if we have a stack of apples and we try to push an orange onto a stack of apples, then we're going to get a compile time error because that stack was declared to only consist of apples. And just the guiding principle in good modular programming is that we should welcome compile time errors and avoid runtime errors. Because if we can detect an error at compile time, then we can ship our product or deploy our implementation of an API and have some confidence that it's going to work for any client. Whereas if the error is not going to get discovered until runtime, it might occur with some client development years after we have deployed our software and be extremely difficult on everyone. Okay, so actually with a good generic implementation, it's not difficult to simply take every place that we use string and replace it with a generic type name, as in this code here. On the left is our implementation of a stack of strings using linked lists. On the right is a generic implementation. So every place that we use string type on the left, we use the word item on the right. And at the top, in the class declaration, we declare in angle brackets that item is the generic type that we're going to use. The implementation could hardly be more straightforward, and it's an excellent way to solve the problem of handling multiple types of data with one implementation. With arrays, it doesn't quite work, and again, all programming languages, or many programming languages nowadays have difficulties with this, and Java's got a particular difficulty. So what we would like to do is just declare a new array using our generic type name item, as in the highlighted line here. Otherwise, it's the same. Unfortunately, Java does not allow generic array creation. So there's various technical reasons for that, and you can read extensive debates about this on the web. That's going to go beyond our scope. For now, what we need to do is put a cast in to make this work. So we create an array of objects, and then we cast it down to an array of items. Now, in my view, good code has 0 casts. So we want to avoid casts as much as possible because it really is declaring some kind of weakness in what we're doing. But in this case, we have to put in this one cast, and so we'll refer to that as the ugly cast. It doesn't make you feel good about the code. It's not something that you'd come up with on your own, and that's an undesirable feature, I think, for code so simple as this. But fortunately, we can get through pretty much everything that we're going to do in this course with just knowing about this one ugly cast. So now when we compile this program, we get a warning message from Java that says that we're using unchecked or unsafe operations, and we should recompile with -xlint equals unchecked for details. So we can go ahead and do that, and it says that you have put in your code an unchecked cast, and we're warning you about that because you shouldn't be putting in unchecked casts. And okay, that's fine, and you're going to see that when you do compiles using code like this. I think maybe they might have added to this warning statement, we apologize for making you do this. It's not our fault that we had to do that. We had to do that because of your requirement about not allowing us to declare generic arrays. So with that note, please don't think there's something wrong with your code if you follow our prescriptive and get this warning message. Okay, there's one other detail that Java takes care of, and that's what about primitive types. The generic type that we're using is for objects, and we're casting down from array of objects. In order to handle generic types, we have to use Java's wrapper object types. Integer with a capital I is wrapper type for int, and so forth. Many of you are probably familiar with that. And there's a process called autoboxing, which automatically casts between primitive types and wrappers. So all of that handles the problem of dealing with primitive types kind of behind the scenes. And the bottom line is that we can articulate an API for generic stacks that works for any type of data, and we've got 2 implementations, linked lists and arrays, that perform very well for any type of data using the resizing or linked lists as we've described. Okay, there's another facility that Java provides that leads to very elegant and compact client code that's definitely worthwhile to add to our basic data types, and that's iteration. That's what we're going to talk about now. So what we want to do is to allow the client to iterate through the items in the collection. But we don't want the client to know whether we're using an array or a linked list or whatever internal representation we might have in mind. It's not relevant to the client. In a lot of clients, all they want to do is just iterate through the stuff in the collection. Now, Java does provide a nice solution to this called iteration. So what we're going to do is look at how to make our stack and queue and other data structures that we consider later on implement the so-called iterable interface. And it'll work for client code no matter which implementation we use. So let's take a look at the details of that. So what's an iterable? In Java lingo, what an iterable is, it's a class that has a method that returns an iterator. What's an iterator? An iterator is a class that has methods has next and next. The Java also allows remove. We think that one is bad news, so we don't use it. It can lead to insidious debugging problems. So has next and next. And so to make a data structure iterable, we're going to implement those things. And it seems like a lot of baggage to carry around. And the reason that we do it, why we go to the trouble of doing it, is that we can, if we have a data structure that's iterable, we can use a very compact and elegant client code in Java, the so-called for each statement. So if we have a stack, we can say for string s colon stack, it means for each string in the stack, print it out. And if we didn't have that, we would, if we're using iterators, we could go ahead and write this longhand code, but nobody would ever do that because it's equivalent to this shorthand. Or we might have to write client code that does a lot of unnecessary pushes and pops just to do this iteration. So that's the key, is to be able to have client code that is so compact for iterating through items in the data structure. So we're going to provide iteration for all our basic data structures. And it's not too hard to do. Definitely worthwhile, the effort. So here's what it looks like for linked lists. It's got to implement iterable. So what does that mean, implement iterable? It's got to have a method, iterator, that returns an iterator. What's an iterator? So we're going to use an iter class. In this case, we'll call it list iterator, that implements iterator, and it's generic. And basically what this thing has to do is implement these methods has, next, and next. And the semantics is clear from the names. Has next is supposed to, if we're done, it's supposed to return false. If we're not done, it's supposed to return true. And the next is supposed to give the next item in the iteration. So if the thing is a linked list, we're going to start out at first. That's our first item in the list, and we're going to maintain an instance variable current inside this iterator, which is the current thing that we're iterating. So to get the next one, just like when we remove the first, we pull out the current item and then advance the current reference and return item, moving current to the next place. The client is always going to be testing has next, as I showed in that stub code before. When it gets to null, it'll return false, and the iteration will stop. But for our iteration, we just have to worry about implementing next and has next, and perhaps using a local instance variable to get it done. We have to probably, to make bulletproof code, throw exceptions if a client tries to call next with no items there, or tries to call remove at all. We're not going to support remove. And for array, it's even simpler. Now the iterator, we have control over which order we go through the items, and so that's going to go along with the semantics of the data structure. So probably in a stack, you want to get the things in stack order, like the order that come out of the stack, so that's reverse order in the array. In this case, then, next is just decrement and return the next one, and our instance variable is an index in the array, and then has next is okay as long as that thing is positive. A little Java code to provide this iteration facility, but actually within this framework, not too much to do, and you can see how to implement this for your own data types, and we'll use this paradigm for every basic data type that we that involves collections of objects that we'll encounter. All right, and in fact, that leads us to actually, for a lot of clients, it doesn't really matter what order we get the items. Really, often what we're doing is just inserting items into a collection and then later on iterating through the items that we have. That data structure is called a bag. So let's look at what that API looks like. The order doesn't matter, so all we're going to do is add an item. Maybe we want to know the size, and we want to iterate through all the items in the bag. So this is a simpler, narrower API, but still it expresses an important little collection of operations, and we'll use this one. We've already seen the implementations. You just take stack and remove the pop, or queue and remove the dequeue, and you have a fine implementation of a useful data structure. Okay, what are the rules that we're going to follow? Well, here, let's start with looking at a typical basic sorting problem. Say a university has student records. And for every student, there's a certain amount of information. Maybe there's a class number, there's a grade, there's a phone number, maybe an address. So we refer to an item as a record, or the information that we're going to sort. But in particular, there's a piece of a record called a key. And what we want to do is put the records into order according to the key. That's the sort problem. Rearrange an array of n items into ascending order according to a defined key, which is part of the item. Now, our goal is to be able to sort any type of data. So let's look at a couple of client programs. First example is to just sort some random real numbers into ascending order. So here's a client that calls our insertion sort method, and all it does is read numbers from standard input, then into an array A, then calls insertion sort, and then prints them out. And you can see on the right that the numbers are printed out in sorted order. This seems like an artificial kind of input, but actually we'll look at an application even in this lecture. And there are many applications where random inputs are a fine model. Here's maybe a more familiar sort client that sorts strings. And in this case, it reads the strings from a file using our read strings method in our in class, which takes a file as argument. So we take the file name as the first command line argument, read in an array of strings from that file separated by blanks, call our insertion sort method again. So insertion.sort is a method that takes an array A as its parameter and it as its first argument, and it rearranges the strings in that array to be in sorted order. So in this case, words3.text has a certain number of three-letter words, and this client program will result in those three-letter words being rearranged into alphabetical order. Here's another client that we could use our sort program for if we achieve the goal of sorting any type of data. In this one, we're going to sort the file names in a given directory. So again, we use the file class from Java, and we go and use the list files method from that class to get an array that contains all the file names in the given directory. That's an array with file names in it, and insertion sort takes that array as its first argument, and again sorts them, and then we go ahead and go through them one by one and print them out, and they come out in order of file name. So that's three different clients, three completely different types of data. And the first rule of the game that we have to think about is, how can we make it so that we can implement one sort program that can be used by these three different clients to implement three different types of data? And the way that that happens is a mechanism known as a callback. So that's our basic question. How can sort know how to compare data of all these different types without being given any information about the type of an item's key? And the answer is that we set up a mechanism known as a callback, or a reference to executable code, where the client, by passing an array of objects to the sort function, in Java there's an implicit mechanism that says that any such array of objects is going to have a compare to method. Then the sort function calls back the compare to method associated with the objects in the array whenever it needs to compare two items. There's a lot of different ways to implement callbacks, and that's programming language specific. Different languages have different mechanisms. It's all about the idea of passing functions as arguments to other functions, which is a deep area that gets us into functional programming and thinking all the way back to Turing and Church. For Java, because of the desire to check types at compile time, they use a specific method called an interface. And we'll look at the details of how to implement callbacks with Java interfaces now. It's a little bit of programming language detail, but it's really worthwhile because it allows us to use the sorts that we develop for any type of data in a type-safe manner. So we already looked at some clients. This is the example of the client program that sorts the files in a given directory by file name. So it just calls our sort method with an array of some type of object as first argument. Now, built into Java is the so-called comparable interface. And all the comparable interface is a specification that a data type that implements comparable will have a compare to method. And it's generic. It'll be compared to against a certain type of item. Now, when we implement objects that are to be sorted, we'll implement the comparable method. That's up in the top. Class file implements comparable file. And since sorting is an operation that's used in so many situations, many of the standard Java types that you would expect to involve sorts will implement comparable. And all that means is that that data type has an instance method that will implement the compare to method. It'll compare this object against the object given as argument, and depending on some complicated test, it'll return -1 meaning less, +1 meaning greater, or 0 meaning equal. Now that compare to method is really all that the sort implementation needs. First, it says that it's going to take as argument an array of type comparable. So that means the objects in the array are going to implement the comparable interface, or that they'll have a compare to method. And then the sort code can just use that compare to method invoked on an instance of the object like an entry in the array, and as argument another instance in the object like another entry in the array, to test whether the first is less than the second, as in this example. The key point is that the sort implementation has no dependence on the type of data. That's handled by the comparable interface. And a different comparable array will be sorted in the same way. They'll eventually, because of the interface mechanism, be a call back to the actual compare to code that goes with the type of object being sorted. Now, there's a few rules, and they're natural rules, but they're worth talking about and paying attention to, that the compare to method has to implement. And it's so-called a total order. And all that's saying is really that it must be possible to put items in order in a sort. So there's three properties. First one says that if v is less than or equal to w and w is less than or equal to v, then the only way for that to be true is if they're equal. And then there's transitivity. If v is less than w, w is less than x, then v must be less than or equal to x. And totality is that either v is less than or equal to w, or w is less than or equal to v, or both, they're equal. And there's plenty of natural total orders in the types of data that we normally want to consider for sort keys, like integers or natural numbers or real numbers, or alphabetical order for strings, chronological order for dates or times, and so forth. The cartoon on the right shows that not all orders are necessarily total orders. So rock, paper, scissors is intransitive. If you know that V is less than W, W is less than V, you don't know that V is less than or equal to V. I'm sorry, V is less than W, W is less than or equal to X, then you don't necessarily know that V is less than or equal to X. All right, so the comparable API, then by convention in Java, we always need to implement compare to such that v.compare to w is a total order. And also by convention, it returns a negative integer if it's less, 0 if it's equal, positive if it's greater. If this object's greater than the object given as argument. If the types are incompatible or if either one is null, compare to should throw an exception. Now, again, many of Java's standard types for numbers and dates and file and so forth implement compare to by convention. Now, if we're going to implement our own type, then we have to go ahead and implement the comparable interface according to these rules. And usually that's fairly straightforward. So here's an example. It's a simplified version of the date class that's implemented within Java, just to show the idea of implementing comparable. So after the class declaration, we write implements comparable, and then we fill in the generic with the same type because we're only going to compare dates to other dates. In this implementation, the date class has 3 instance variables, the month, the day, and the year. And the constructor fills those in from the arguments, as you can see. So now if you want to compare 2 different dates, then the first thing to do is to check if this year is less than that year, and where that is the year given, the date given in the argument. If that's true, then it's less, return -1. And if the year is greater, return +1. Otherwise, the years must be equal, so we have to look at the months to do the compare, and so forth down to do the days. Only if they're all equal do we return 0. So that's an example of an implementation of comparable by implementing the compare to method to put dates in order, as you might expect. So the Java language helps us with this comparable mechanism so that we can sort data of any type. But when we come to implement sorting algorithms, we're actually even going to hide that beneath our own implementations so that our sorting algorithms actually, the actual code, can be used to implement sorting in many other languages. And the way we do that is to take the 2 primary operations, compares and exchanges, that we use to refer to data and encapsulate them just as static methods. So we're going to use a method less that takes 2 comparable objects as arguments, and it just returns v.compare to w less than 0. And then the other thing that we do when we sort items that are in an array is to swap or exchange the item at a given index I with the one at a given index j. And that's every programmer's first introduction to assignment statements. We save A of I in a variable swap, put A of j in A of I, and then put swap back in A of j. So now our sort methods to refer to data will just use these 2 static methods. And there's a good reason for that. Here's an example. Suppose we want to test if an array is sorted. So this is a static method that is supposed to return true if the array is sorted and false if it's not. And all it does is just go through the array from 1 to the length of the array and test if each item is less than the one before it. If you have an item that's less than the one before it, then it's not sorted, you return false. If you get all the way through the array without that happening, then you say the array is true. That's pretty simple code. The question is, if you have a sorting algorithm that passes that test, are you sure that it correctly sorted the array? Well, the answer to that question is yes, if you used only the less than exchange methods to refer to data. Because then you know, because you use the exchange method, that the data in the array after the sort is the same data as was in the array before the sort. If you have a sort method that can store any values in an array, it could, for example, store zeros in every array entry. That method would pass this test, but it didn't really correctly sort the array because it overwrote all the values. So we use less than exchange to be sure that we can test that our methods work with a method like this. The first elementary sorting method that we're going to take a look at is an easy method known as selection sort. The idea of selection sort is to start out with an unsorted array, and we'll use these playing cards as an example. In the ith iteration, we go through the array to try to find the smallest remaining entry. In this case, the 2 is the smallest remaining entry. And then we'll swap that with the first entry in the array, and then we know we've got one step done. Selection sort is based on iterating that idea. Okay, so the basic selection sort method is to, in the ith iteration, find the smallest remaining entry to the right of I, or bigger index than I, and then swap that with I. So when we start out, I is at the left end, and then all the remaining entries are to the right. We scan through, and the smallest one is the 2, 3 entries from the right. So we swap that. So that's the first step. Now that part of the array to the left of I is in its final order, and we simply continue. So now the smallest is the 3, swap that with I, increment I. So now we have the 2 and 3 in order, and continue in that way. Find the smallest, it's the 4, swap that one with I, increment I. Find the smallest, it's 5, swap that with I, increment I. Find the smallest, swap that with I, increment I. Each time we have to scan through all the remaining entries in order to find the smallest, but then once we found it, we only have to swap 2 cards. Those are both key properties of selection sort. Now the 8's the smallest, and we swap. And now we know they're in order, but the program doesn't, so it has to look and decide that I and min are the same, and then it swaps it with itself and does the same thing for the last. And so after that process, then we know that the entire array is in its final order, all sorted. All right, so one way to understand the way that an algorithm works is to think about invariance. So for selection sort, we have a pointer, that was our variable I, that scans from left to right. That's indicated by a little red arrow in this representation. The invariants are that the entries on and to the left of the arrow never change, and they're in ascending order. No entry to the right of the arrow is smaller than any entry to the left of it. That's the way that we set it up. And the algorithm maintains those invariants by finding the smallest entry to the right and exchanging it with the next one. So the code implements the invariants. So to move the pointer to the right, we increment I. So now the invariant might be violated. So we have to fix it. It might be violated because you might have an element to the right of the pointer that is smaller than the element on the pointer. So what we have to do is identify the index of that minimum entry and exchange it. Then once we've exchanged it, again, we've preserved our invariant. After that point, no element to the left of the pointer is going to change, and there's no smaller element to the right. And that gives us immediately our code for the selection sort implementation. We identify the length of the array, that's in n. Then we have a for loop that goes through every element in the array. We keep a variable min, that is the index of going to be the index of the smallest element to the right of pointer I. We have an inner for loop that for j, if it finds a smaller one, resets min. And then once we've looked at all the elements to the right of I, we exchange the smallest one with I. That's a complete implementation of selection sort. Now, it's easy to develop a mathematical model for the cost of selection sort, and here's the proposition that describes that. Selection sort uses about n squared over 2 compares and exactly n exchanges. And just looking at this trace of selection sort in operation really is a visual proof of this proposition. In this diagram, the entries in black are the ones that are examined in order to find the minimum each time, with the minimum in red. Entries in gray are not touched. They're in their final position. Well, you can see that this is going to be, in general, an n by n square, and about half of the elements in the square are black, or about n squared over 2. And you can see also the exact formula, n minus 1 plus n minus 2 and so forth, is the total number of compares used. And then on each of the n values of the variable I, there's an exchange. So that's the cost in terms of the number of exchanges. Now, what's interesting about this proposition about selection sort is that it doesn't matter what order the input is, selection sort's going to use quadratic time because it always has to go through the whole thing to look for the minimum. Another property is that you can't sort moving less data because selection sort does just a linear number of exchanges. Every item is put into its final position with just one exchange. Let's look at an animation of selection sort in operation. You can see our pointer moving from right to left, and every time it finds the smallest element to the right, it exchanges it into position. Now, if the array is partially sorted, doesn't matter to selection sort. Still has to go through, even if it's totally sorted, still has to go through to decide where that minimum element is. That's selection sort, our first elementary sorting method. Now we'll look at insertion sort, which is another elementary method that, interestingly, has quite different performance characteristics than selection sort. Let's look at a demo of insertion sort. For insertion sort, what we're going to do is we'll move an index I from left to right as before, but now in the ith iteration, we're going to move AI into position among the elements to its left. Let's look at how that works on our example with cards. So now we start by initializing I at the first card. And we take the idea that everything from I to its left is going to be sorted, and everything from the right we're not going to look at all. So everything to the left of I is in ascending order. Everything to the right we haven't seen at all yet. So now when we increment I, well, in this case it's already in order. We don't have anything else to do. In the third case now, when I is at the third entry in the array, now we start a index j and we move that starting at I to the left, and what we need to do is just exchange the 5 with every element to its left that's greater. So first we exchange it with the 10. It's still not in place, so we exchange it with the 7. Now we get to the beginning of the array, and once we've done that, or we've hit a smaller element, then we have everybody to the left of I in order. So now we increment I again and we come to the 3. Again, we exchange as long as the card immediately to the left is greater. And once we've done that, then we have everything to the left of I in ascending order. Now in this case we have the 8, we only have to exchange 1, and now it's got the 7 to its left, and everything is in order. So we've achieved putting it in order with less work in this case. We don't always have to go all the way back to the beginning. 4, exchange it with everybody to its left that's greater until we find a smaller element, and then it's in ascending order. 2 has to go all the way back to the beginning. But then the very next one, the 9, has to only go back 1 position. And the 6 has to go about halfway back. And then we have the entire array sorted. Again, we can look at insertion sort in terms of invariance. Our pointer still scans from left to right, but now the elements of the left of the pointer, including it, are in order, but the elements to the right have not yet been seen at all. So we have to look at the code that's going to maintain that invariant as the pointer increments. Move the pointer to the right, it's incremented again. Now the invariant's broken because the element on the pointer is not in sorted order. To put it in sorted order, we have to move from right to left, exchanging it with every larger elements to its left. And that's what the code at the bottom does. It starts J at I and decrements J, exchanging J with the elements to its left, A of J with the element to its left, A of J minus 1, as long as A of J is less than A of J minus 1, or J is bigger than 0. And that immediately gives this code for insertion sort, which is similar to our code for selection sort and just as simple. It's got 2 nested for loops. Selection sort had 2 nested for loops, a test, a comparison, and an exchange inside the for loop. And that's a fine implementation of an elementary sorting method. What about the analysis of insertion sort? It's more complicated. Our proposition says that insertion sort, to sort randomly ordered array with distinct keys, it'll use about 1/4 n squared compares and about the same number, 1/4 n squared exchanges on the average. This is more complicated to prove. It depends on the array being randomly ordered. And again, you can get a feeling for where the proposition comes from by looking at this n by n trace. Again, the black elements are the ones that we compare, and actually they're also the exchanges. And the red one is the one that's finally put into place. And you can see that for a large array that's randomly ordered, the element that we put into place is going to go about halfway back on the average. So that means about half of the elements below the diagonal are going to be black on the average. There's n squared over 2 below the diagonal. Half of that is n squared over 4. The analysis, exact analysis, is not much more detailed than that. This is a bigger trace that shows, again, about half the elements below the diagonal are involved in the sort. Let's look at an animation. Since n squared over 4 versus n squared over 2, insertion sorts are going to be about twice as fast as selection sort. So we can do about twice as many items in the trace in the same amount of time. It grabs an element, brings it back into position every time. So that's an animation for randomly ordered items. Now, insertion sort does depend on the initial order of the data. Let's look at the best case and the worst case, which are certainly outliers. If the array happens to be already sorted, all insertion sort does is really validate that. Each element has got a smaller elements to its left, so it does no exchanges. It gets the sorting job done with just n minus 1 compares. On the other hand, if the array is in descending order and it's no duplicates, then every element goes all the way back. It makes n squared over 2 compares and n squared over 2 exchanges. So in the first case, it's much, much faster than selection sort, linear instead of quadratic. In the second case, it's slower than a selection sort because it uses about the same number of compares, but it uses many more exchanges. So let's see that in the animation. So this is when the items come in reverse order. Now, every time it gets a new item, it has to exchange it all the way back to the beginning. Same kind of dynamic characteristic as selection sort, except for every step, it's not just comparing, it's also exchanging, which makes it even slower in practice. So this is a bad case that we wouldn't like to see in a practical application. But there's also a good case that actually we take advantage of in plenty of practical applications. And that has to do with when the array is partially sorted. To talk about this in a quantitative way, we define what's called an inversion. An inversion is just a pair of keys that are out of order in the array. So this array has 6 inversions. T and R are out of order because R should go before T. T and P are out of order, and so forth. This array has 6 inversions. And we define an array to be partially sorted if its number of inversions is linear, if it's less than some constant times n. And partially sorted arrays appear often in practice. For example, if you have a large array with just a few that's sorted except for just a few unsorted elements appended at the end, it's going to be partially sorted. Or another case is if you only have a few entries out of place, the array is going to be partially sorted. These types of things arise often in practical applications. And what's interesting about insertion sort is that it runs in linear time for partially sorted arrays. And the proof is the number of comparisons and the number of exchanges is equal to the number of inversions. Number of exchanges equal to the number of inversions, and then there's an extra compare for every element except the first. So let's look at how that looks in the animation. Here's a partially sorted array, and you can see that insertion sort quickly gets the job done. We're going to take advantage of this a little bit later in this lecture. That's insertion sort, our second elementary sorting method. Now we'll look at shell sort, which is a bit elementary on the face of it, but it's not at all elementary, as you'll see. The idea of shell sort is that insertion sort is inefficient because elements really move only one position at a time, even when we kind of know that they have a long way to go. So the idea behind shell sort is that we'll move entries several positions at a time. And the way we're going to do it is called H-sorting the array. So an H-sorted array is H different interleaved sorted subsequences. So in this case, with H equals 4, if we start at L and look at every fourth element, M, P, T, then it's sorted. If we start in the second place at E and look at every fourth element, it's sorted. So this is 4 interleaved sequences. That's a 4-sorted array. And what we're going to do is implement a sorting method that H sorts for decreasing sequences of values of H. This is one of the oldest sorting methods invented by Shell in 1959. So in this case, it starts out with the input example shown, and then a 13 sort, a few items are moved, a 4 sort, a few more are moved, and then finally a 1 sort. And the idea is that each of these sorts can be implemented with only a few exchanges, given that the previous ones happened. So first thing is, how do we get an array H sorted? That's actually pretty easy. We just use insertion sort, but instead of going 1 back every time we come with a new item, we go H back. So for example, when we come to this A in the insertion sort, then we look at the array before that, and there was M and E in the positions 3 back. So we exchange the A with the larger one to its left, that's M, and then the other larger one to its left, that's E, and then put it into position. So the code is the same as for insertion sort, except that when we go backwards through the array, we skip by H instead of just by 1. That's how we H-sort an array. And the idea is we're going to use insertion sort because for two reasons based on our understanding of how insertion sort works. Well, the first thing is if the increments are big, then the size of the subarrays that we're sorting are pretty small, so any sorting method, including insertion sort, is going to work well. But the other thing is, if the increments are small, because we've done previous H-sorts for bigger values of H, the array is partially sorted. And so insertion sort is going to be fast. It wouldn't work to use shell sort as the basis for H-sorting because that always takes quadratic time no matter what order there is in the array. So let's look at an example of shell sort with increments 7, 3, and 1. So we start with the sort example, and then 7 sorting it just involves doing insertion sort, but just reaching back 7 each time. In this case, the 4 subfiles stretched out at 7 each only have 2 elements in them. And then we 3 sort. Now, because it's 7 sorted, in the 3 sort, elements are either already in place or only go back a few strides. In this case, it's only the A that goes back 2. And then we 1 sort. And again, because of the fact that it's been 7 sorted and 3 sorted, the array is almost in order when it comes time to do the 1 sort, and most of the items only go back 1 or 2 positions. So we have to do a few extra passes to do the higher sorts, but each element moves only a little bit on each pass, and that's how shell sort gains its efficiency. Actually, once you 1 sort, that's insertion sort, so you're going to always get a sorted result. The only difference is how efficient is that. Now, the intuition behind shell sort, and actually the mathematical fact, is that if you've got an array that's H sorted and then you K sort it for another value K different from H, it's still H sorted. This is one of those mathematical facts that seems obvious, but then if you try to prove it, maybe it's a little more subtle than you think. So if you think of all this as trivial and easy, go ahead and try to write down a proof that a G-sorted array remains G-sorted even after it's H-sorted. But most people will accept that, and it's a fact, and that's how shell sort gains its efficiency. Now there's another problem, is what increment sequence should we use for shell sort? One of the first things you might think of is let's try powers of 2. Actually, that one doesn't work at all, very well at all, because it winds up not comparing elements in even positions with elements in odd positions until the 1 sort, which means performance can be bad. Shell's original idea was to try powers of 2 minus 1, and that works okay. Knuth, when he wrote his books in the 60s, proposed the increment sequence 3x plus 1. You start with the 1, 4, 13, 40, 121, 364, like that. And that's good because it's easy to compute. When we're using in shell sort, of course, we find the largest increment less than our file size and then do the sorts for decreasing values of that increment. But finding the best increment sequence is a research problem that has confounded people for quite a long time. Here's an increment sequence that I found after maybe a year's work, and it works well, but nobody knows if that's the best one. So here's the implementation in Java of shell sort for Knuth's 3x plus 1 increment sequence. We just go ahead and compute the increments that are less than n over 3, and then starting at that increment, whatever it is, and say we start at 364, then next time we need an increment, we just divide by 3, 364, integer divide by 3, 364, integer divide by 3 gives 121, 40, and so forth. So this h equals h over 3 gets us to the next increment. And then the implementation is just insertion sort. We just go through starting at h for I, And when we do the insertion, the J loop, we decrement J by H each time. Otherwise, the code is exactly like insertion sort. So just adding this extra loop for H sorting and this extra loop to compute the increments to insertion sort, we get a slightly more complicated piece of code, but it's much, much more efficient. Here's what it looks like for a bigger array. We start with randomly ordered input, and you can see that it gets more and more in order on each time that we H sort for the decreasing values of H. Here's an animation. This animation does the whole H sort for each subarray. It gives a little better feeling for what's going on. And now it did the high ones pretty quickly, and now it's doing the one sort. And again, it zips through the array pretty quickly. If it's partially sorted, it doesn't make much difference. Does the higher order sorts a little bit faster. But that's a simple to implement and very efficient sorting algorithm. Now the analysis of shell sort is still open. There's a few things that we can say. For example, we can say that the number of compares in the worst case is big O of n to the 3/2 for the 3x plus 1 increments. But actually, in practice, it's much less than that. Problem is, nobody knows an accurate model for describing the number of compares taken by shell sort for any interesting increment sequence. They seem to be with a small value multiple of n times the number of increments used, which is some multiple maybe of n log n. But nobody's been able to find an accurate model that proves that for any interesting increment sequence for shell sort. So why are we interested in this algorithm? Well, it's a simple idea that leads to substantial performance gains. It's very useful in practice because it's pretty fast, except for very huge arrays. It's going to beat even the classical sophisticated methods for medium-sized arrays, and it doesn't take much code. It's often used in embedded systems or in hardware sort type systems because there's so little code involved to implement it. And it just leads to a lot of interesting questions. This gets to the intellectual challenge of developing algorithms. If you think what we've been studying so far is trivial, go ahead and find a better increment sequence. Try some technique to discover one. And try to say something about the average case performance of shell sort. People have been trying to do that for 50 years without a whole lot of success. So the lesson is that we can develop good algorithms or good implementations without much code, but there's some out there that are still waiting discovery. It could be that there's some increment sequence out there that makes shell sort more efficient than any other method, any other sorting method that we know for practical file size. No one can deny that. That's shell sort, our first non-trivial sorting method. Next, we're going to look at an easy application of sorting to a related problem called shuffling. So suppose you have a deck of cards. One of the things that you might want to try to do is to simply rearrange those cards into random order. That's called shuffling. Here's a way to get shuffling done using a sort. It seems like the opposite. The idea is just generate a random real number for every array entry, and then sort using those random numbers as the keys. That's an effective way to get things shuffled. And it's possible to prove that that produces a uniformly random permutation of the input if there's no duplicate values, assuming that you have real numbers that are generated uniformly at random. And that just means that it's well shuffled, that every possible way of shuffling the deck appears with equal probability. That's fine, but it requires a sort, and the sort seems like a lot of work for this problem. And the question is, can we do better? Can we have a faster way to shuffle? Do we really need to pay the cost of a full sort? And the answer to that question is no. There's actually a very easy way to rearrange an array so that the result is a uniformly random permutation and only require linear time to get the job done. Let's look at a demo. The idea is to pass through the array from left to right with an index I, as we've been doing. But now we start with the array in order, and actually it doesn't matter how we start the array. And every time we pick an integer between 0 and I uniformly at random and swap a of I with that integer. So let's look. At the beginning, we don't do anything. We just swap it with itself. Now with I equals 2, or I pointing to the second card, we generate a random integer in this between 0 and I. In this case, it's the one to the left, and we swap those. Increment I, generate a random integer. This time it's going to be the first one again. Swap them. Increment I, generate a random integer. Swap them. Increment I, generate a random integer. Swap them. And continue in that way. Swap. So for every I, we do exactly one swap. Now a card could be involved in more than one swap, but that's not an issue. The point is that the cards to the left of I are shuffled. They're uniform randomly shuffled. In this case, I and R are the same. There's no swap. Increment I, generate a random R, swap them. And at the end, we have the deck shuffled. That's a linear time shuffling algorithm making use of randomness. It was proved actually a long time ago, even before computer implementations, that if you do that, you get a uniformly random permutation, and it only takes linear time. So that's definitely a way to get a deck shuffled quite easily. Easy to implement. Now it's key that the uniform random number be between 0 and I minus 1. You'll often see programmers thinking that they're implementing a shuffle, and they just choose for every entry, they just choose a random place in the array to exchange it with, and that doesn't really work. You could do the items between I and n minus 1, the ones that you haven't seen yet, and that would also work, but doing the whole array doesn't give you a uniformly random result. So with that one caveat, this code is almost trivial. And it's a method in our standard random class. Now, if you're going to be using random methods that depend on randomness in real applications, you do have to be careful. So this is just an example about software security. There's a lot of difficult and deep issues to worry about in software security, and we're not going to worry about all of them. But one thing that we can do is make sure that our algorithms work as advertised. So here's an example of an implementation for online poker. Here's the code that you can find on the web for how to shuffle a deck of cards. That's pretty similar to our code, but it's actually got a few bugs, more than a few bugs. So first one is the way that random works, it actually never gets to 52, which means that the last card just stays, it can't end up in the last place. So it's definitely not shuffled because of that. Maybe that one's minor, but it also is picking a random card from the whole deck. And as we just pointed out, that's not uniform. Should be between 1 and I, or between I plus 1 and 52. Another problem is in this implementation that the random uses just a 32-bit seed that if you do that, there's not enough possible shuffles. The number of possible shuffles is much more. If n is 52, it's 52 factorial, which is a lot bigger than 2 to the 32nd. So it's not close to random or uniform. And the other thing is that the seed is just the number of milliseconds since midnight, and that cuts down the number of shuffles even more. And in fact, didn't take that much hacking for someone to realize that after seeing 5 cards and figuring out what the server clock was doing, you could get all the future cards in real time in a program. And that's a pretty tough thing to have happen if you're implementing online poker. You might want to make sure that if you're advertising that you're doing a random shuffle, that you go ahead and do so. A famous quote, and there's many similar quotes, the generation of random numbers is too important to be left to chance. So if your business does depend on shuffling, people have looked at all sorts of options, including using hardware random number generators, and there's various tests available to make sure that it's random. And you better use good shuffling code. That's our topic. But the bottom line is, don't think that it's easy to shuffle a deck of cards. So that's shuffling, our first non-trivial sorting application. Now we'll look at an application of sorting from the field of computational geometry for an interesting computation. If you have a set of n points in the plane, there's a geometric object called the convex hull, which is the smallest polygon that encloses all the points. There's the convex hull for that set of points. There's a lot of equivalent definitions of this, some of them very mathematical that extend to higher dimensions. It's the smallest convex set that contain all the points, the smallest area convex polygon enclosing the points. It's a convex polygon that encloses the points whose vertices are points in the set. Those are all equivalent definitions. And what we want to do is, given a set of points, we want to have a program that can give us the convex hull. Now, what should the output of such a program, such a method be? Well, in order to be able to work with the result, it should be a sequence of vertices that gives us that polygon if we follow it. If we've got some points that are on the boundary but aren't really vertices, they shouldn't be included. This points out examples of how difficult computational geometry can sometimes be, because degenerate cases like this are difficult to deal with in code. We're not going to spend a lot of time on this in this lecture, but it's something always to be aware of when trying to apply simple algorithms in situations like this that turn out to be maybe more sophisticated than we might think. Oh yeah, gotcha. Mm-hmm. Well, there's actually a way to compute the convex hull just mechanically. If you put nails around the points and put a rubber band around it, that gives you the convex hull. Now, we're not going to be able to really implement that in a computer program, but it's surprising how well we can do. Here's an application where people want to compute the convex hull. Suppose you have a robot that wants to get from S to T, and there's an obstacle that's defined by some polygon. You want to be able to go around the obstacle, and it turns out that the shortest path, either it's a straight line from S to T, or it's part of the convex hull. And it's not hard to see why that might be true. There's plenty of other applications where people want to be able to compute the convex hull. Here's another application. If you want to find the pair of points that are the farthest apart in a set of points in the plane, this is sometimes important in statistical calculation or other applications. They're on the convex hull. If you have the convex hull, this computation is easy. They're going to be extreme points on the convex hull. So there's a lot of geometric properties of the convex hull that we can take advantage of to develop an algorithm. And here are two properties. Now these are things that have to be proven, and we're not going to get into the details of geometric proof, but they're intuitive, and you'll certainly have no trouble accepting that these things are true. One thing is that you can traverse the convex hull by making only counterclockwise turns, or left turns if you're looking at the screen here. And the other thing is that, so if we travel from P to point 1, then we make a left turn to go to point 5, or a counterclockwise turn, and then from there we go to point 9 and 12, and then we eventually get back to the start point. The other thing is, if you take the point with the lowest y coordinate, and then if you look at the polar angle with respect, for every other point with respect to that one, so the angle you get from the x-axis through P up to the point, then the vertices appear in increasing order of that angle. And again, that's not difficult to see that that's a fact. And the algorithm we're going to look at, called the Gram scan, is based on those two facts. It's the idea is to start with point P, the one with the smallest y coordinate, sort the points by polar angle with P, that is, we're just going to consider them in that order, and then we'll just throw away the ones that do not create a counterclockwise turn. And you'll see how that works when we look at a demo. So we start at point P, sort the points by polar angle with P. So that is, if we take a vertical line and sweep it in a counterclockwise direction, what order do we hit the points? The first thing we hit is 0, 1, and then if we sweep counterclockwise, we get to 2, and then 3 and 4, and so forth. So that's the ordering of those points. And so now we'll just consider those points in order and then take them for the convex hull. At the beginning, 0, 1 is a line that's on the convex hull. So the point with the lowest y coordinates on the convex hull, and so is the one that is the smallest polar angle it creates with the x-axis. So now what about this one too? Is that on the convex hull? Well, as far as we know at this point, it could be. It could be that the thing is a triangle and 0 is the last point, in which case it would be. But it's and same with 3. As far as we know, that one could be on the convex hull. But as soon as we go out to 4, that's not a counterclockwise turn. It's going the wrong way. And essentially what this means is that point 4 is evidence that there's no way that point 3 can be on the convex hull. You can convince yourself of that quite easily. So we just throw point 3 out. It's not on the convex hull. So, and what about the angle from 1 to 2 to 4? That's not counterclockwise either. That's turning the wrong way. That's turning to the right. So point 2 can't be on the convex hull either. And indeed, if you just draw the line from 1 to 4, you can see the 2's inside. So there's no way it could be in the convex hull. That's essentially the proof that you have to have a counterclockwise turn. So now we go on to 5. Turning the wrong way, so point 4 can't be on the convex hull. So now we go to 6. As far as we know, it could be, but as soon as we hit 7, we know that it can't be because that's a right turn. So 6 is not there. Go to 8. Nope, 7 can't be on the convex hull. Go to 9. 8 can't be on the convex hull. Now we go to 10 and 11. As far as we know, they could be. If 12 weren't there, they would be. But as soon as we hit 12, we see that 11 can't be on the convex hull and 10 can't be on the convex hull. And that completes the computation of the convex hull with the Gram scan. Okay, so there are a number of implementation challenges for the Gram scan, and we're not going to go into detail on these because this is a lecture on sorting algorithms, not computational geometry. But it is indicative of how, even if we have a good sort, we might have to do some extra work to actually solve our problem in an application. So how do we find the point with the smallest y-coordinate? You could sort. You could define an order and compare the points by y-coordinate. Essentially sorting is the answer to that question. And we'll look at the next lecture of what it means to define ordering among objects, a little more general than what we do for sorting. How to sort the points by polar angle? Well, again, we need to define what we mean when we're comparing points. And in the next lecture, again, we'll look at ways to define different orderings among points. And Gram scan's a perfect example. We don't want to just be able to sort things. We don't want to just be able to sort them by defining a compare to. We want to be able to sort the same things in different ways sometimes. And this example is a fine motivation of that. Figuring out whether what we have is a counterclockwise turn, that's a little exercise in geometry, and we'll just talk about that briefly on the next couple of slides. And then, what about getting the sort done efficiently? Well, we could use shell sort, but actually in the next couple of lectures, we'll look at classical sorts, merge sort and quick sort, that we could use. The idea, though, is that this example illustrates that a good sorting algorithm gives us a good complex call algorithm. That's an extremely important principle in designing good algorithms. Once we have a good algorithm, if we have another problem, we can say to ourselves, well, we've got a good solution to this algorithm. Can we use that solution to solve our new problem? Convex hull, when we have a good sorting algorithm, it gives us a good convex hull algorithm, because the most work in convex hull is the sort. And then again, there's all kinds of difficulties in implementing convex hull in real-world situations because of various degeneracies. And these things are covered on the book site. So the main part of computation that we haven't really talked about, and we'll cover briefly, is if we have 3 points, A, B, and C, and you go from A to B to C, are you making a counterclockwise turn or not? So in the example at the left, A to B to C is counterclockwise. The example at the right, A to B to C is not counterclockwise. If you're going from A to B, you turn left to get to C in the first case, and you go right to get to C in the second case. And we want to do a computation that distinguishes this. Now, this computation would be pretty easy, except for the degeneracies, is what do you want to count it if they're all on the same line? Or if the slope is infinity. So you have to just be aware that these situations have to be dealt with. So the code isn't quite as simple as you might come up with in the first instance that you try. So there's degeneracies to deal with in floating point precision. But researchers in computational geometry have worked this out. And actually, there's not that much code at all in the end involved. And this is a slide that gives the math. And I won't talk through this math. If you're interested in implementing this, you can come back to this slide. And it's essentially based on the idea of computing the slopes of the lines between A and B and between A and C and comparing them to decide whether you're turning counterclockwise or clockwise. And this is the specific math that gets that implemented. This is if we implement a point data type for computational geometry, it can have a method, CCW, that just with this little math calculation, b dot x minus a dot x times c dot y minus a dot y minus b dot y, this calculation here gives you immediately whether it's counterclockwise, clockwise, or collinear. Not much code at all. And that method is the basis for the Gram scan. The Gram scan uses a sort where we give 2 different ways to sort the points, and it uses a pushdown stack for the hull. It puts the points on the hull, and it goes ahead and for every point, considering them in the order of the polar sort, it'll compare whether the top 2 points on the hull and the new point implement a CCW turn or not. And if it's not a CCW turn, it pops it and continues going. Very little code to implement the convex hull given that you have a sort. And that's our main point for this lecture. There's many natural applications of sorting, but also we'll be able to develop new algorithms that use sorts that gain efficiency because of the efficiency of sorting. Welcome back. Today we're going to look at merge sort, which is one of two classic sorting algorithms that are critical components in the world's computational infrastructure. We have a full scientific understanding of the properties of these algorithms, and they've been developed as practical system sorts and application sorts that have been heavily used over the past 50 years. In fact, Quicksort, which we'll consider next time, was honored as one of the top 10 algorithms of the 20th century in science and engineering. In this lecture, we're going to look at merge sort, which is the basic sort in plenty of different programming systems, including Java. Next time, we'll look at quicksort, which is also used in Java for different applications. All right, so basic merge sort algorithm, what's it going to look like? The idea is very simple. What we're going to do is divide an array into two halves, recursively sort each of the halves, and then merge the result. That's the overview of merge sort. It was actually one of the first non-trivial algorithms implemented on a computer. John von Neumann realized in the development of his EDVAC computer, one of the first general-purpose computers, that it was going to need a sorting method, and he came up with merge sort. He's widely credited as being the inventor of merge sort. So the idea of merge sort is based on the idea of merging. And so to understand how merging works, we'll think about the idea of an abstract in-place merge. So we've got an array A, and its first half is sorted, and its second half is sorted. And the computation we need to perform is to replace that with the sorted array where those two subhalves are merged together. Let's look at a demo. The method that we're going to use is based on taking an auxiliary array to hold the data. This is one of the easiest ways to implement the merge. So the first thing we do is copy everything over to the auxiliary array. Now, once that's done, what we'll want to do is copy back to the original array, but get it in sorted order. In order to do that, we're going to maintain three indices. I, the current entry on the left half, J, the current entry on the right half, and K, the current entry in the sorted result. So the first thing we do is take the smaller of the two entries pointed to by I and J and compare those and take the smallest one and move that one to be the next item output. In whichever one is taken, we increment its pointer. Now we compare the minimum again. Again, the one pointed to by J is smaller, so we move that one to K, increment that pointer J, and also increment K. Now, there's two E's equal. We always take the first, so the one in the left array goes to K's position, and now we increment I and K. And again, it's an E, and they're equal, but we'll take the first one, so we move that one up, increment I and K. Now JZ is smaller than G. It's the next thing that has to go in the output, so we move that one up and increment J and K. Now the one pointed to by I, the G is smallest, so move that up, increment I and K. Move the M up, increment I and K. Now the last element in the left subarray is the one that's going to get moved next. And now that first subarray is exhausted, so really all we need to do is take the rest of the elements from the right part and move them back in. Actually, since we copied, we could optimize by avoiding these moves. That's an abstract in-place merge for taking the two sorted subhalves of an array, use an auxiliary array, move them out, and then put them back in sorted order. All right, so here's the code for merging, which is quite straightforward from the demo. We first, in order to sort an array of comparables, in this implementation we pass a link to the auxiliary array in as well. And we have three arguments, low, mid, and high. So low is the first part of the array to be sorted. Mid's the midpoint that divides the first part from the second. So our conditions are that from low to mid is sorted and from mid plus 1 to high is sorted. So the merge implementation, then the first thing it does is copy everything over to the auxiliary array. And then that sets up for this for loop that accomplishes the merge. We start our I pointer at the left part of the left half, the J pointer at the left part of the right half, that's mid plus 1, and we start the K pointer at the beginning low. And for every value of K, what we're most often doing is comparing whether aux of J is less than aux of I. And if it is, we move the element at J over in increment J. If it's greater, we move the element I over in increment I. And then in both cases, we increment A, and that increment K, and that implements the merge. If the I pointer is exhausted, then we just move over the J, next Jth element. If the J pointer is exhausted, we move over the next Ith element. So every time we're moving a new element into K, and that's the code that implements the abstract in-place merge. Now, with this code, we're also introducing the idea of making assertions just to make it easier to debug in our code and to have confidence that it's correct. In this case, this insertion just says we want to be sure that A of low to mid is sorted and that mid plus 1 to high is sorted before our code, and then we want to check that the whole thing is sorted after our code. And generally, Java programmers know that it's a good idea to try to do these assertions. Not only does it help detect bugs, but it also documents what the code is supposed to do, and that merge code is a good example of this. If you put at the beginning of the code what you expect in the form of an assertion, which is code itself, and you put at the end of the code what you think it's going to do, again in the form of an assertion, you're both testing that these conditions hold and also telling someone reading the code what you're trying to do with it. So Java is just an assert statement, and it takes a Boolean condition. In this case, we're using that method is sorted that we wrote before that returns true if the port of the array is sorted and false if it's not. And what assert will do is it'll throw an exception unless that condition is true. Now the thing about assertions in Java is that you can enable or disable them at runtime. And that's really important because it means that you can put them into your code to check while developing, but it doesn't incur any extra costs at all in production code. So by default, assertions are disabled. Something goes wrong, somebody analyzing the situation can enable insertions, and they often will help find out what the problem is. So the best practice is to use insertions just as we did in that example with merge, and to assume that they're not going to be there in production code. So you shouldn't use them for things like checking if the input is the way you like it. All right, so with that merge implementation, then the sort implementation is a quite simple recursive procedure shown here. So we use the merge procedure we just showed, and then our sort procedure is recursive, so checks that we have something to do first. Then it computes the value of the midpoint, same way as we did for binary search. sort the first half, sort the second half, and then merge them together. And then the actual sort takes just the one argument of the array, creates the auxiliary array, and then uses that. Now, it's important to not create the auxiliary array in the recursive routine, because that could lead to extensive cost of extra array creation. And you'll sometimes see merge sort performing poorly because of that bug. Otherwise, this is a very straightforward implementation, and it's actually a prototype for algorithm design that we'll see come up again and again. It's called divide and conquer. Solve a problem by dividing it into two halves, solving the two halves, and then putting the solutions together to get an appropriate answer. Here's a trace of what merge sort does, and if you haven't studied a recursive program before, it's worthwhile studying this thing in some detail. This gives exactly what happens during each of the calls to merge. We start out with a big problem to solve, but we divide it in half, then we divide that one in half, and then we divide that one in half. And the very first thing that we actually do is just compare and exchange, if necessary, the first two elements. And then we do the same thing for the next two elements, then merge those two together to get the first four done. And then we do the same thing for the next four in the array. So now we have two sorted subarrays of size 4. We merge those together to get one of size 8. And then we do the same thing on the right. And eventually we have two 8s that we merge together to get the final result. Very instructive to study this trace to really understand what this recursive algorithm is doing. So now we can animate, and again, merge sort's more efficient, so we can do more and more items. You can see it's got the first half sorted, now it's working on the second half. And then once it gets the second half sorted, then it's going to go ahead and merge them right together to get the sorted result. And it's got a little extra dynamics in the animation because of the auxiliary array. Let's look at it when it's in reverse order. Again, it gets the first half done, now it's working on the second half. Once it gets the second half done, then it goes ahead and merges together the whole thing. It's just as fast on reverse ordered as in arbitrary order. So you can run merge sort on huge problems. It's a very efficient algorithm. And so, for example, what this table shows, if you were to try to use insertion sort for a huge file, say a file of 1 billion elements on your PC, it'd take a few centuries to finish. Even on a supercomputer, if you're using insertion sort nowadays, it'd maybe take a week or more. But if you have a good algorithm like merge sort and you're trying to do 1 billion items, you can do it in just less than half an hour on your PC, and a supercomputer can do it in an instant. And smaller problems only take an instant even on your PC. So you can spend a lot of money or a lot of time, or you can use a good algorithm. And that's one of our main themes in this course. A good algorithm is much more effective than spending money or time, wasting money or time using a bad one. So let's look at the analysis of merge sort. That's a bit of math, but very instructive because this really shows the power of the divide and conquer method and allow us to take a problem that was taking us quadratic time with methods like insertion and selection sort and get it done in n log n time with merge sort. So that's the proposition. Merge sort uses at most n log n compares and 6 n log n array accesses to sort any array of size n. And the way to prove this proposition is to, from examining the code, to write down what's called a recurrence relation. And all that is, it's a mathematical reflection of what's going on in the code. If we're sorting n items, then let C of n denote the number of compares that we need to sort the n items. In order to get that done, we're sorting the left half and the right half. and this notation ceiling of n over 2 and floor of n over 2. That's the n over 2 round up, n over 2 round down. That's the size of the two subarrays. And we're going to call the same routine for that size, so the number of compares you need for that is C of n over 2, ceiling of n over 2 for the left and C of floor of n over 2 for the right. And then for the merge, we need at least, at most, n compares. If neither one exhausts, we need exactly n compares. And so, and that's true as long as n's bigger than 1. If there's only one thing, we're not doing any compares at all. So this is a mathematical formula that we derive by examining the code, but it completely describes mathematically an upper bound on the number of compares that are going to be needed. And similarly for the number of array accesses, if you count up the number of times you're accessing an array for a merge, it could be at most 6n. So these are mathematical formulas, and there's techniques for solving them, and we won't go into that. This is not a course in discrete mathematics. But what we can do is show how to solve the recurrence when n is a power of 2. And then it turns out that it holds for all n, which we can prove by induction from the recurrence. So if you have this recurrence, which is similar to the ones that we're talking about, it's exactly the same when n is a power of 2. Let's look at this one. If d of n is 2d of n over 2 plus n, with d of 1 equals 0, then d of n equals n log n. And we'll look at 3 proofs of that, just assuming that n is a power of 2. If n is a power of 2, then n over 2 is also a power of 2, so the recurrence makes sense. So this is just a graphical representation. If we want to compute d of n, we want to compute d of n over 2 twice. So that's 2. And then the extra cost for the merge is n. But if we're going to do this twice, then we have 2 n over 2s. Whoops. We have 2 n over 2s. And then for each one of these, we have divided into n over 4s, and each one of those 4 n over 4s has an extra cost for the merge of n over 4. Well, 2 over n over 2 is n, 4 n over 4 is n, and we keep going down and doing that till we get down to d of 2, and we always, for the extra cost of the merge, we have n. And how many stages do we have here? Well, it's the number of times you divide n by 2 to get down to 2. That's exactly log base 2 of n. So the grand total of all the costs for the merge, which is where the compares are, is log n times n log n. That's kind of a graphical proof, or a proof by picture, that that recurrence has that solution. Here's a little bit more mathematical one. We write the recurrence down, and then we divide both sides by n. So then it says d of n over n equals d of n over 2 over n over 2 plus 1. So it's dividing by n. So now this is a recurrence that telescopes. The first term on the right-hand side is exactly the same as the left-hand side, so we can apply the same formula. And all it does is divides by 2 again and then throws out another 1. And we keep doing that until we get down to d of 1, which is 0. And when we've done that, we've thrown out log n 1s. So we get d of n over n equals log n, or d of n equals n log n. That's another proof by expansion. Or using either one of those techniques, you can just get the idea that d of n is close to n log n, or you can write a program to expand the recurrence and find that. And then once we have the idea that d of n equals n log n, we can plug back into the original formula with the inductive hypothesis that d of n equals n log n. We want to show that d of 2n equals 2n log 2n. Using the recurrence, d of 2n equals 2d of n plus throw out the 2n, plugging in n log n, we get the desired result. You use this same idea on our initial recurrences for compares and array accesses to show that the number of compares and array accesses is proportional to n log n for merge sort. So that's the running time. Merge sort is fast. The other thing that we usually want to know is memory. And one of merge sort's characteristics is that in practical applications, it uses extra space proportional to n. That is, we need that extra auxiliary array for the last merge. We took two sorted subarrays and we talked about an abstract in-place merge, but we didn't have an actual in-place merge. We were using an extra subarray. And in-place is important. A lot of times we're sorting everything we have. We want to fill up the memory with stuff to sort and then sort it. Insertion, selection, and shell sort were in place. They don't use much extra memory. But merge sort, you can only sort really half of what you can fit in memory because you need that auxiliary array for the other half. If you want, again, if you think that the things we're studying are easy, think about the idea of actually doing an in-place merge. People have come up with methods for getting this done, so it's theoretically possible, but the methods are generally too complex to be useful in practice, and they're not used. But there could be out there some easy way to do an in-place merge. That's another great algorithm waiting to be discovered. Now, there's a number of practical improvements that we can use to make merge sort even more efficient than the simple one that we've looked at. We'll take a look at those because they're examples of techniques that we can use for other algorithms. First thing is that merge sort is too complicated to use for tiny arrays. So say the subarrays are only of size 2 or 3 or 4. There's too much overhead with the recursive calls and so forth to get that done efficiently. And what's worse is the recursive nature of the sort definitely means that there's going to be lots of subarrays to be sorted. So one improvement that we can make is to use insertion sort and just cut off and use insertion sort, which is simple and efficient for small subarrays. So that's adding this one line of code to merge sort. We'll make it quite a bit faster, maybe 20% faster. A second improvement that we can make that'll improve the performance for cases when the array is partly sorted is to just stop if it's already sorted. And that's going to happen in the case where the biggest element in the first half is less than or equal to the smallest item in the second half. That means it's done. So that's easy. We just put a test in the recursive merge sort for that to this one line of code to check whether we're done. That way, for example, if you were to call merge sort for an array that's already in order, it would just do this test every time, and it would be done in linear time. That's pretty helpful, although not totally helpful, but there's a lot of situations where that's helpful. The other thing that's possible to do, and it's a little mind-bending, so recommended only for experts, is to save a little bit of time. You don't really have to copy over into the auxiliary array. You can kind of switch the role of the input in the auxiliary array every time you make a recursive call. You still need that array, but you can set up the code in this way, which to sort an array, put the result in the other one. To merge an array, put the result back in the first one. So it's a recursive argument switchery to get the job done. And it's effective. It means you don't have to actually move items. And that saves a little bit of time. So here's a visualization of what the practical merge sort might look like. And this is with a big cutoff to small subfiles. So you get a visual feeling of how this sort gets the job done. It sorts the first little chunk and then the next little chunk and then merges those together and so forth and so on. A good visual representation of how merge sort gets its job done. That's the basic merge sort algorithm that we're going to look at different versions of next. Next, we're going to look at a bottom-up version of merge sort. While merge sort is easy to understand as a recursive program, this bottom-up version that has no recursion is also quite simple to understand and to code up. The basic idea is to think of the array as being a little, at the beginning, a set of little sorted subarrays of size 1. And then what this method will do is go through and merge those little subarrays of size 1 together in pairs to get subarrays of size 2. Then the whole array consists of sorted subarrays of size 2. Then we make another pass through to get size 4 and then size 8 and so forth. So as you can see in this example, we start out by merging the first two subarrays of size 1 to make an array of size 2 EM that's sorted. And then do the same thing for the next two elements and the next two and so forth until eventually, instead of 16 individual elements, we have 8 sorted subarrays of size 2. Then in another pass through, we can take the EM and the GR and merge them together to make EGMR, and the ES and the OR, merge those together to make EORS and so forth, and we have 4 subarrays of size 4. One more pass makes 2 subarrays of size 8, and then the last pass is just a sorted array. The bottom line in this is a sequence of passes through the whole array, and there's no recursion needed at all. It's extremely easy to code up, as you can see from this code. We use the same merge code as before, and we take a nested for loop. The first one is the size of the subarray, and this loop gets executed only log n times because each time we double the size of the subarray until we get to n. And then we pass through, picking out from low to low plus size minus 1, and then the next part is low plus size minus 1. Until we run to the end of the array, we might not have a full subarray of size SZ. That is a fully complete industrial strength code for sorting. The only downside, as with regular merge sort, is that it uses extra space proportional to the size of the array. But otherwise, that's a fine method for merging. That's bottom-up merge sort. If you look at this visual trace, you can see how it works. The thing is totally unsorted. Then it gets sorted into subarrays of size 4, then 8, 16, and 32. Now in this case, the second subarray to be sorted is smaller, but the merge routine doesn't really care about that so much. It can merge things that are not equal in size, and then we get a final sorted array. Whatever the size, bottom-up merge sort gets the job done in log n passes, each pass using about n compares for a total cost of about n log n. With merge sort is a good opportunity to take a look at the intrinsic difficulty of the sorting problem. That's called complexity, and we'll look at that next. The idea of complexity is it's a framework for studying the efficiency of all the algorithms for solving a particular problem. That's called computational complexity. And in order to do this sensibly, we need what's called a model of computation, the operations that the algorithms are allowed to perform. For sorting, that's kind of straightforward. What we're going to do is have a cost model where we count the comparisons. Now, in framing the difficulty of problems, we'll need two things. One is what's called an upper bound, which is a cost guarantee that's provided by some algorithm for solving the problem. That's an upper bound on how difficult it is to solve the problem. We have an algorithm that can solve it. It's at least that easy. And then we also look for a lower bound, which is a limit on the cost guarantee of all algorithms. No algorithm can do better. Now what we seek ideally is what's called an optimal algorithm, where we prove that the upper bound and the lower bound are the same. That's an algorithm that we know that has the best possible cost guarantee. That's the ideal for solving any problem. So for sorting, let's look at what each of these are. The model of computation is what's called a decision tree. What that means is that all we can use is compares. That's the only way we can access the data. So our cost model is the number of compares. Merge sort provides an upper bound. That's an algorithm that's guaranteed to get the sort done in time proportional to n log n. And what we'll look at now is the lower bound. There's trivial lower bound, which says you have to look at all the data, that's n, and we'll look at a better lower bound and see that merge sort is optimal. So here's the basic idea for proving a lower bound for sorting. Let's say we have three different items, A, B, and C. Whatever algorithm we have is going to first do a comparison between two of the items. Let's say they're A and B. And then there's two cases. Either it's yes or it's not yes. Let's say they're distinct. And there'll be some code between the compares, but either way, then there's going to be a different compare. If A is less than B, maybe the next compare is B against C. And if you find that B is less than C and A is less than B, then you know that they're in any algorithm that does that knows that the items are in the order A, B, C. If B less than C goes the other way, then it takes another comparison to determine the order. In this case, if C is less than B and A is less than C, then those three compares show that the order has to be A, C, B. And if C is less than A, then it's got to be C, A, B. Those three compares that C is less than A, C is less than B, and A is less than B. The only possibility is C, A, B. And continuing on the right, perhaps the next compare is A less than C, and maybe if C is less than A, another compare B less than C. So in this case, if you go from top to bottom in the tree, with three compares at most, you can determine the ordering of the three different items. The idea of the lower bound generalizes this argument to figure out the number of compares that you need for a minimum to determine the ordering among n items. Now, the height of the tree, as I just mentioned, is the worst case number of compares. Out of all the orderings, the one that's furthest down in the tree, that's the worst case. And so the algorithm, no matter what the input is, the tree tells us a bound on the number of compares taken by the algorithm. And there's got to be at least one leaf for each possible ordering. If there's some ordering that is not appear in a tree corresponding to a particular algorithm, then that algorithm can't sort, can't tell the difference between two different orderings. So the lower bound is a proposition that uses a decision tree like that to prove that any compare-based sorting algorithm has to use at least log base 2 of n factorial compares in the worst case. And by Stirling's approximation, we know that log base 2 of n factorial is proportional to n log base 2n. And then the proof is generalizes what I talked about in the decision tree on the last slide. We assume that the array consists of n distinct values, and there's a decision tree that describes the performance of any algorithm, the compare sequence done by any algorithm to determine the n factorial different orderings. So this tree has to have at least n factorial leaves, and if the tree is of height h, it has at most 2 to the h leaves. The tree that has the most leaves of height h is totally complete, and that one has 2 to the h leaves. And those observations give us the lower bound. 2 to the h has to be greater than or equal to the number of leaves, and the number of leaves has to be greater than or equal to n factorial, so that implies the height of the tree has to be greater than or equal to log base 2 of n factorial, which is proportional to n log n by Stirling's formula. That's a lower bound on the complexity of sorting. So we knew that the upper bound was proportional to n log n, and we just proved that the lower bound is proportional to n log n, and that means that merge sort is an optimal algorithm. That's the first goal of algorithm design, is to try and find optimal algorithms for the problems that we need to solve. Now, you have to take these results in context. Really, what we proved is that merge sort is optimal with respect to number compares, but we already know that it's not optimal with respect to space usage. Merge sort uses twice as extra space proportional to the size of the array it has to sort. And simple algorithms like insertion sort don't. don't use any extra space at all. So what we want to take from these theoretical results is a guide when we're looking at implementations and trying to solve practical problems. In this example, what the theory tells us is, don't try to design a sorting algorithm that guarantees to use substantially fewer compares than merge sort. Say half n log n compares. Is there a method that uses half log n compares? The lower bound says no. And that's a very useful thing, because otherwise we might try to define such an algorithm. On the other hand, maybe there is an algorithm that uses n log n compares and also uses optimal space. It's optimal with respect to both space and time, and that's what we're going to look at soon. The other thing is that the lower bound is for the particular model of computation being studied, in this case compares. It might not hold if the algorithm has more information about the keys. For example, if it's known that the input is almost ordered. We saw that insertion sort can be linear time for files that are almost ordered. Or if something about the distribution of key values. If there are a lot of equal keys, we can get it sorted faster than in n log n. And maybe the way the keys are represented, we'll look at different methods that take advantage of such properties. So partially ordered arrays, we may not need n log n compares. Duplicate keys, we may not need n log n compares. We're going to look at a method that gets that done in linear time in a lot of situations. And later on, we'll look at digital properties of keys where we can use digit or character compares instead of whole key compares and get a faster sort for certain practical applications. Computational complexity is a very useful way to help us understand properties of algorithm and help guide our design decisions. Next, we'll take a look at comparators, which is a Java mechanism that helps us sort the same data on different sort keys in different orders. And you're familiar with this. Your music library, maybe at one point you sort it by the artist's name. In this case, we're looking at the Bees. But in another situation, you might want to sort it by song names to look through it by song names. That's the same data using different sort keys. How do we arrange to do something as natural as this in our Java sorts? Now, we used before, in order to be able to implement sorts that can sort any type of data, we use Java's comparable interface. And the concept is that there's some natural ordering of the data that you'll want to use most of the time. That's what the comparable interface is all about. But there's a different interface called the comparator interface, which is a way to help us sort using some alternate order or many different orders on the same data. And the comparator interface, again, just says that it's going to implement a method compare that compares two different keys of a given type, of the generic type. Again, it has to be a total order. And this is very familiar. For example, with strings, there's many different ways that we might want to sort strings. We might want to use the natural alphabetic order, or we might want to make it case insensitive, or maybe there's different languages that have different rules of the ordering. We're sorting strings, but we're implementing a different ordering, various different orderings on that same data. That's what the comparator interface is for. So the Java system sort will have a different method to implement comparators. And the idea is that you create a comparator object and then pass that as a second argument to Java's sort routine. And we can do the same thing for our sorts. The idea is we want to decouple the definition of the data type from the definition of what it means to compare two items of that type. With the natural order, we had to put the definition of compare to within the data type. With comparators, we can do that outside of the data type, even at some later time. Strings were defined as part of the Java system, but we can define our own ordering on strings with a comparator. So in our sort implementations, we can change them as shown in this example to support comparators. To support comparators in our sort implementations, we'll pass an array of objects instead of array of comparable, and then as a second argument, pass a comparator. Then the less method will take that comparator as an argument, and it's the one that actually invokes the method compare of two different keys. This is a straightforward modification to our sorts. And then exchange, of course, rather than doing comparable, has to use object. So with these straightforward changes, add the comparator as argument to the sort and to less, and make our array to be sorted array of objects. It's easy to convert any of our implementations to support comparators. To implement a comparator, you can use this code as a model. I won't go through it all in detail, just to point out that this implements two different comparators as nested classes. So, say for this fictional class student that's got two instance variables, name and section. And the first one, called by name, implements a comparator for students. And when you compare two students by name, it's going to use the string compare to method. If you're going to implement it, compare two students by section, then it'll return just the difference of the sections, which is minus if less, 0 if equal, and plus if greater. And this code is a straightforward way to implement comparators that you can use as a model if you need to be able to sort data on two different keys. So here's just an example of what happens if with those implemented comparators for that class student using the Java system sort. If you call arrays.sort with your array of students and you give it this by name comparator, it'll put them in order, alphabetical order by the name field. And if you give it the by section comparator, it'll put them in order by the second field. Very convenient for all kinds of data processing applications. And we came up with that before when we were talking about using a sort for the gram scan. We needed to have a comparison for points that orders them by the polar angle they make with a given point P. That's what we needed for the gram scan algorithm for the convex hull. Points are a defined data type for geometric objects, and so what we need is code that'll compute the polar angle and use that as the basis for comparison. There's an easy way to do this based on CCW that is described here in this text. Most of the time, all you need to do is do the CCW of the 2 points, but you do have to check whether one of the points is above P and the other one is below. But otherwise, usually it's a CCW call. And this code, which again I won't go through in detail, is an implementation of a comparator for 2D points. It implements the compare method that takes 2 points as argument, and with just a little bit of calculation, it's able to do the compare. So this code is the basis for applying the system sort method or any sort method for the gram scan for the complex hull that we did at the end of the last lecture. So that's the basis for the gram scan method for the complex hull that we used at the end of the last lecture. Finally, we talk about stability. This is really one of the rules of the game, but it's much easier to talk about in the context of the real algorithms that we've seen so far. And really, it doesn't make sense if you don't know about comparators, which we just introduced. So the typical application that I just used as an example is, say, this set of student records. So we have them sorted by name. This is, say, something that we do just before assigning final grades. Maybe the third line there is the final grade. So it's all fine, it's sorted by name, but then in order to distribute it out to the people leading each of the sections, what we want to do is sort by the second field, sort by section. The problem is that when we do that, it messes up the sort by name. And that's annoying. You might assume that once you have it sorted by name, that when you sort it by the second field, then it should maintain the sort of by name for all that have equal keys in that second field. Actually, not all sorts preserve that property. That's called stability. And clearly, it's worthwhile to think about for your application whether you want or need a stable sort. It's an annoying surprise for many people in many applications. So a stable sort is a sort that preserves the relative order of items with equal keys. Which of our sorts are stable? That's an interesting question that we'll take a look at now. The quick bottom line is that insertion sort and merge sort are stable, but not selection sort or shell sort. And even within that bottom line, there's implementations that maybe are not stable. You have to carefully check the code to be sure. Always in this class, we have an exercise or exam question. Is this version of this sort stable or not? So students learn to recognize whether code is stable. So this is just another typical example where we've got things sorted by time. And then what we want to do is maybe these are important events, people buying tickets to a rock concert. And then we want to sort by location. What we'd hope is that it would keep the sort by time, but this is a non-stable sort that doesn't do that. So then out in the locations, they're going to have to resort it if they use one of these. But if they use a stable sort, then it stays sorted by time. Lots of applications you want stability. All right, so let's just look at each of the algorithms that we've considered so far. Insertion sort. Insertion sort is stable. Why is it stable? Well, we never move equal items past one another. In this example here, when we get A1, well, that's, so in this case, the index is just when it appears in the array, it's just A's and B's. When we get our second A, we stop the sort as long as we're not less. We're equal, we're not less, we stop it. So we never move an equal item past another one. If this less were less than or equal, then it wouldn't work. Or if we did it the other way around and proceeded accordingly. So equal items never move past each other in this code, so therefore insertion sort is stable. But selection sort is not stable. Usually the way to show that a sort is not stable is just to see if it has a long distance exchange that might move an item past some equal item. So in this case, for example, for selection sort, when we do that first exchange, where we found the minimum A and B is in position 0, we did a long distance exchange. And that catapulted that first item past any item that it might be equal, putting them out of order. And that may not get fixed, so that sort is not stable. It might move items past some equal item and leave a result where items that are equal are in different order than they were originally in the file. Selection sort is not stable. Shell sort also has long distance exchanges, so it's not stable. It moves keys past other keys that could be equal. And so it's easy to construct examples showing that selection sort is not stable. And what about merge sort? Merge sort is stable. Well, it's stable as long as the merge operation is stable. And that operation is going to be stable depending on how we code it. And in our code, if the two keys are equal, it takes from the left subarray. So that means that it'll always take the, if there's two sets of equal keys, it'll preserve the relative order. And that's enough to show that the merge operation is stable, and then therefore merge sort is stable. Stability is an important property in sorting algorithms. Merge sort is not only efficient, it's also stable. Now we're going to look at binary heaps, which is an ingenious and very simple data structure that's going to help us implement all the priority queue operations quickly. So the idea of a binary heap is based on the idea of a complete binary tree. So a complete binary tree, well, first of all, a binary tree is either empty or it's a node with links to left and right binary trees. So that's an example of a binary tree. A complete binary tree is one that's perfectly balanced except possibly for the bottom level. So there might be a few nodes on the bottom level and one level lower than the bottom level, but otherwise all the levels are full. And we'll see how that looks in just a second. The property of a complete tree is that the height of a complete tree with n nodes is the biggest integer less than log base 2 of n. And that's really easy to convince yourself that that's true because the height, if we add nodes one at a time, going from left to right on the bottom level, say, the height only increases when n is a power of 2. Complete binary trees actually happen in nature. Here's an example of one that goes 1, 2, 3, 4 levels at least. So 16 bushes at the end there. All right, now the way we're going to use complete binary trees to implement priority queues is to, first of all, associate information with each node. We'll put our keys in the nodes. And also, we're going to represent it with an array. So when we start putting the keys in the nodes, we're going to impose one more condition that's called heap ordering. And the idea is that the parent's key is going to be no smaller than its children's key, and that's true for every node in the tree. The array representation, all we do is we start with indices at 1. It's a little less calculation that way. We leave A of 0 empty. And then we just take the nodes in level order. So first we put the root, then we put the 2 nodes on the first level going left from right, and then all the nodes on the third level going from left to right, and so forth. This is interesting because we can draw the tree to get more intuition about what's happening, but in the actual data structure representation, we don't need any links at all. It's just an array. The way that we move around the tree is by doing arithmetic on the indices. So let's look at a few properties of binary heaps. So that's complete binary trees represented in an array with keys in the nodes satisfying the heap order property. Well, first thing is that A of 1 is the largest key. It's larger than the keys, there's 2 children, and they're larger than theirs, and so forth. So it's the largest key in the data structure. The other thing is, as I just mentioned, you can use the array indices to move through the tree. For example, if the node is at position k, index k in the array, then its parent is at k over 2. And that's integer divide. So the parents of, say, H and G are both n. H is at 10, G is at 11, n's at 5. So both of those are 10 over 2, 11 over 2, integer divide is 5. And going the other way, it's easy to see that the children of the node at k are 2k and 2k plus 1. So we don't need explicit links at all to represent these data structures. We can just use array indices. So that's the basic setup or the invariant that we want to maintain in this data structure. And now what we're going to do is take a look at just a couple of different scenarios that where we violate that invariant temporarily and then fix it. And that's going to give us the flexibility that we need to implement priority queue operations. So one scenario shown here is if for whatever reason a child's key becomes larger than its parent's key. So in this case, we have an example where t, the node t here, its value changes and it becomes larger than its parent key p. So the heap order condition is satisfied everywhere except at this node. Well, it's easy to fix this one. All we do is exchange the key in the child with the key in the parent. After that exchange, then that would have t up here and p down here, then the heap order condition is satisfied at that node because the parent was smaller, so that one's smaller. And this other one is still smaller, so t is, after it's exchanged up here, will be bigger than both its children. But the heap condition will be violated because t is still smaller than s. So we have to do it again, exchange it with s. So we move up the tree, exchanging the larger key with its smaller parent until we get to a point where it's larger than both its children. That's restoring the heap order along a path from the place where it's violated to the root. You can think of that as kind of like the well-known Peter principle, where a node gets promoted to a level where it finally can't be better than its boss. It's a level of its maximum incompetence. And implementing that in code is really easy. We call that the swim operation. It swims up to the top. And if we have a node at index k and we know the heap condition is violated there, as long as we're not at the root and k's parent, k over 2, is less than a of k, then we just exchange it with its parent and move up. That's the swim operation to eliminate a violation when a key value increases. So, for example, this gives us a way to insert a new element into a heap. What we do is we add a new node at the end of the heap. So that's one position over. The thing is, remember, represented in array, 1, 2, 3, and so forth. So the next empty position in the array, there's a place to put a new node. And then we just declare that that's part of the heap. And that node, well, if it's less than its parent, we're fine. But in general, we have to check whether the heap condition is violated and exchange it with its parent as long as it's smaller. And that's just perform the swim operation. So if n is the number of items in the heap defined to be in the heap, we're going to increment it, store our new key there, and then perform the swim operation. So that's a quick implementation of the insert operation. And notice, since it's just going from bottom to top in the heap, it takes at most 1 plus log base 2 of n compares. Now there's another scenario where a key becomes smaller. For whatever reason a parent key decreases, it might become smaller than one or both of its children's. In this case, the value at position 2 is changed to h for whatever reason. And that's smaller, in this case, than both its children. So how do we fix that violation? Well, that one's also easy. We figure out which of the children is larger. In this case, it's the s. And we exchange that one with the one that's violating the condition. So that's moving the smaller key down. After that exchange, then S is in position 2, and it's bigger than both P and H, and the heap condition is only violated, again, where H is sitting. And again, we keep going until getting to the bottom or getting to a place where both children are smaller. And that's maybe a little bit what happens when a new boss is hired from the outside. And then the two subordinates struggle to take over that position, and then the boss would get demoted to its level of competence. And again, that level of flexibility. Here's the implementation of it. And again, it's quite straightforward using the index arithmetic to move around in the heap. And that's called the sync operation because we're going down in the heap. If we're at position k, then what we need to worry about is the nodes at 2k and 2k plus 1. And the first thing to check is find out which one's bigger. It's either 2k or 2k plus 1, and so set j accordingly. So that's j now, is after this statement, is the larger of the two children. And don't forget to check that we're going off the end of the heap. And then if the k is not less than either one of those, then we're done. If it is, then we exchange with the larger of the two children and move down the heap. Again, just a few lines of code to eliminate the violation when a key value in a heap decreases. And that one we're going to use to implement delete the maximum in a heap. So delete the maximum, we have to do two things. One thing is the size of the heap has got to go down by 1. The other thing is return the maximum. Well, we know the one that we want to return is the one at the root, so we'll save that value away to return to the client. And then, since it has to go down by one, the place to get remove the element from the heap is at the end of the array, because it's now going to have to not occupy that position. So we take that element and replace the root with it. So move the H up, and actually put the root value there, just exchange them, but it's no longer in the heap. Now, that element, which went from the bottom to the top, is most likely going to violate the heap order. It's going to be smaller than both of its children, so we do a sync. Now, in this case, to implement delete max, we save away that value at the root in max, and we eliminate loitering by nulling out that vacated position, then return the max value. So that's an implementation of the delete max operation for a heap using sync, where a key value that decreases goes down in the heap. So let's just take a look at what happens with a real heap with the demo when we do these things. And you'll have a good feeling for how this data structure works. So we're starting at some point where we have these 10 keys in a heap, and it's heap ordered. So we've drawn the data structure with the links, so we have an intuition for what's going on. But all the program sees is the array in gray at the bottom, where T's in position 1, P and R position 2 and 3, and so forth. So now suppose that we're supposed to add S. So to add it to the heap, that's going to go in the position at the end. And then now we've added it to the heap by just incrementing n and putting it in there. But now we have to bring the heap order back into condition. And so that's going to, that key is larger than its parent, so we're going to swim it up. Exchange it with its parent as long as it's smaller than its parent. So first thing, it goes up to exchange with the S. It's still bigger than P, so we exchange it with the P. And now we're done because S is not bigger than T, and the heap order condition is now satisfied everywhere in the heap. So with just 2 exchanges, we insert that new element into the heap in this case. Now suppose the next operation is remove the maximum. So we're going to take T and we're going to exchange it with the last element, and then declare that to be no longer part of the heap. So now we have to bring the heap order back because it might be violated at the root. So now we invoke the sync, where we exchange that node with the larger of its 2 children until we find a place where it's larger than both its children. So S is the larger of the 2 children, R and S, and now H is still smaller than both its children, so we promote the larger, which is P. Now H has no right child, just a left child, and it's larger than that one, so we're finished with that operation. We've removed the maximum, and we still have our data structure heap ordered, and our n keys stored in the first n positions in the array. Let's remove the maximum again. Again, we take it out by exchanging, this time G with the root, and then decrease the size of the heap by 1, just take that out. Now the node at the root violates the heap order, so we have to exchange it with the largest of its 2 children. In this case, that's R. Again, G is not larger than its 2 children, so we have to exchange it with the larger of the 2, that's O. And now we're done, we've removed the largest again. Now suppose we insert S back into the heap. So that's adding it at the end, violates the heap order, exchange it with the parent who's smaller, and keep doing until we get to a place where it's larger than its 2 children. In this case, S goes all the way up to the root, and it's all heap ordered again. So that's a little survey of some operations on a heap, and you can see how every operation is done with just a few exchanges along the path from the bottom to the top, or the top to the bottom. Okay, here's the complete Java implementation of a priority queue using the binary heap data structure. It's actually not so different from the elementary implementations that we looked at in the last section. Our representation is an array of keys and a size. That's the number of items in the heap. For simplicity, we'll show the code where the client gives the capacity of the heap. We can use a resizing array in an industrial strength implementation, the same that we did for stacks and other data structures where we use arrays. So we'll build a new array of keys, and we have to use an ugly cast because we can't have generic arrays in Java. So it's comparable, and we need one more than the capacity to handle this thing where we don't use position 0. So the priority queue operations is the insert and del max that we just showed in the previous slides. Isent is just checking whether n is equal to 0. We have the swim and sync functions that we showed earlier, and then we have helper functions less and exchange that access the array directly so that the code doesn't have to access them directly. That's a complete implementation of priority queues in Java. And this implementation by itself is extremely significant because it's really very simple, optimal representation of the data, and only a little arithmetic with array indices. But as you can see by looking at this table, it gives us a way to implement priority queues where both operations are guaranteed to happen in log n time. Now, experts have worked to come up with improvements on this, and there are slight improvements possible. We can make the heap D-way rather than just two-way, and depending on the frequency of execution of the insert and del max operations, that might work out better. There's an advanced data structure called a Fibonacci heap where inserts are done in constant time and delete max done in log n time on average over all the operations. But that one's generally too complicated to use in practice. But still, again, using theory as a guide, maybe there's a way to, to decrease costs a little bit from binary heaps. And of course, we cannot get down to having constant time for all operations. Why? Well, we can sort with a heap by inserting all the elements and then deleting the maximum and getting a sort done. And that would be linear time if we had this kind of variation, if we had constant time operations for both insert and del max. But for certain applications, we can get close to constant time for one of the other operations, and that'll be useful in different implementations. Now, there's an important consideration that we have to bring up related to the programming language, and this is a more general consideration than usually we bring into focus in algorithms, but it's worthwhile mentioning. We're assuming that the client doesn't get to change the keys while they're on the priority queue. And it's better not to assume that. It's better to arrange for that in our implementations by using keys that are immutable, whose values don't change. There's many reasons that immutable keys are that programming languages provide the capability to build immutable keys, and this is a fine example of one. And we'll talk more about that in a minute. The other things that we didn't talk about in the implementation should throw an exception if the client tries to delete from an empty priority queue. And we should have a no argument constructor and use a resizing array to account for gradual growth and shrinkage in an industrial strength implementation. Usually we provide two implementations, one that's max-oriented, one that's min-oriented, so that nobody gets confused, and they're the same except less and greater are switched. We'll see later on there's times when we want to expand the API and provide other operations like removing an arbitrary item from the priority queue, or give the client in the API the capability of changing the priority of an item. Our sync and swim methods are good for making this happen, but we'll delay these implementations until we need them in a more complicated algorithm. So what about immutability? In every thing in Java is implemented as a data type, a set of values and operations on those values. And the idea of immutable data type is you can't change the value once it's created. So that's kind of like when you when you create a literal value to be assigned to an integer, it has that value. Here's an example, say using a data type for vectors. It might be a way to implement vectors. So we put the word final to means that the instance methods can't be overridden. And not only that, instance variables are private. They can't be seen from the outside, and they don't change. And so a constructor for an immutable vector data type, it might take an array as its argument, and that array has got values stored in it, say of doubles, and those can change. But what an immutable implementation would do would be to copy those values into the local data array instance variable. And then those values are not going to change. And the instance methods won't change them, and the client can't change them. So that value stays the same. Lots of implementations, data type implementations in Java are immutable, like string is immutable. When you create a string, that value doesn't change. If you want a new string, you have to create a new string using concatenation or some other operation. And the same with the wrapper types like integer and double or color and lots of things. Whereas, on the other hand, sometimes the whole purpose of a data type is to maintain a changing value. Like a good example is a counter or a stack. So you wouldn't put those things on a priority queue because the value is changing, but the other ones you would. The advantages of immutability, and again, maybe this isn't the place to really sell those advantages, it's more for a programming language course, is that it really simplifies debugging. We can have more confidence that our priority queue operations are going to work correctly if we know that the type of data that's on the priority queue is immutable. If the client could change the values, how do we know that the heap order operation is preserved? If we want the client to be able to change the values, we're going to provide methods for that purpose, as I just mentioned. And there's many other reasons that people use immutable data types. There is a disadvantage that you have to create a new object for every data type value, but for a lot of applications, that disadvantage is not viewed to be significant compared to the advantages. Here's a quote from one of Java's architect, Josh Block. Classes should be immutable unless there's a very good reason to make them mutable. If a class cannot be made immutable, you should still limit its mutability as much as possible. And many programmers live by that kind of precept. So that's a basic implementation of priority queues using the heap data structure represented as an array. Next, we're going to look at the use of the binary heap data structure to implement a clever sorting algorithm known as heap sort. So here's the basic plan. What we're going to do is we have our n keys, and we'll have them in an array. We'll view that array as eventually being a max heap. So what we have to do first is to rearrange the keys in the array to heap order it. So just make it so that every key is larger than its two children. And for example, the largest of all the keys is at the root. And then the next phase would be to take that heap ordered array and get it to be a sorted result in place. And again, the heap is stored in the array with the first key position 1, next to position 2 and 3, and like that. So the end result would be like that with no keys in the heap, but all the keys in the array in sorted order. So it's a little exercise in abstraction. Part of the array is the heap, part of the array is the sorted subarray, and eventually we bring it down to the whole thing being sorted. There's very little code beyond the basic heap code that we've looked at can get this implemented. That's called heap sort. Let's take a demo of how heap sort works in our example. The idea is we're going to use a bottom-up method. So all that means is we start with an array in arbitrary order, and then we're going to work from the bottom up to make sure that it's heap ordered. Well, all the nodes with no children are heap ordered. They're only of size 1. The first one we have to worry about is this one here. The root we haven't examined yet. Its children are heap ordered, so it's a small heap of size 3 that may not be heap ordered. In this case, it's not, because one of the children is larger. So that's where things are going to start. We have a lot of one-node heaps, and then we're going to have to perform the sync operation on this one at node 5. That's, in this case, just exchange it with this parent. And then proceeding in that way, moving bottom up or moving from right to left, the next thing we do is, then we have a 3-node heap that's heap ordered, and we're fine. Now we'll move over to the T, and again, that's the root of a 3-node heap that's heap ordered except at the root. We may need to fix it with the sync operation. In this case, nothing is required because it's larger than its children, so we have a 3-node heap. And then we move one more to the left. Now we're looking at the R. Again, root of a 3-node heap may or may not be heap ordered. We do have to do the sync operation. In this case, that brings the X up. 3-node heap. Now we go to 2. Now that's the root of a 7-node heap. We know the 2 3-node heaps that are children are heap ordered, but we may have to correct the heap ordering at the root, so we do a sync on 2. And that's going to involve exchanging with the T, because T is larger than O, and exchanging with the P, because P is larger than O. Now that heap is a 7-node heap that's all heap ordered. And then the last thing is to do the root of the whole thing. And again, now the 2 subtrees are heap ordered. That's what we mean by bottom up. We took care of the heap ordering from the bottom up. And so we'll do a sync on the S and bring it into heap ordering. So that's with just a few exchanges, we got that whole array heap ordered. And now what we want to do is take advantage of the heap ordering in the array to do a sort. And the concept is very simple. Right away, we have the maximum element in the array right at the root. We want that to be at the end, so that's what we're going to do, is just put it at the end. We exchange the element at the root with the last element, pull it off the heap, and then that's our example. We might have violated the heap order condition at the heap right now, so now we have to do a sync operation on the E. And so it's larger than it's both children, and the larger of the 2 children is T, so we promote the T. And the P is larger of the 2 children, promote that. And then finally the E comes down to the bottom. So now that's one step in the sort. We got the largest element off. Now the next largest element in the array is now at the root of the heap. So we're going to do the same thing, exchange it with the last element in the heap. Then now the T is in its final position in the sorted array. We take it off the heap. So now we've got a heap with 9 elements, and 2 of the elements in the array are already in their final position. And now this one's not heap ordered, so we have to exchange it with the largest of its 2 children. In this case, that involves promoting the S and the R. Now it's heap ordered. So that's the end of 2 steps in heap sort. And then we just keep going, pulling off the largest element from the heap, exchanging it with the element in the heap in the largest position in the array, which brings that element into its final position in the sorted array, and then adjusting the heap ordering with the sync operation. So that E again is going to come down, and now it only goes down 1 step in this case. So now R exchanges with M, and it's in its final position. And you can see down at the bottom the large elements in the array filling in their final position. In the left part of the array is representing the heap. The R goes off the heap, do the sync operation on the M, and now we have a heap ordered array. So now do the P, exchange that with the A, take it off the heap, do the sync operation on the A. Now we're going to do the O, exchange that with the E, take it off the heap, do the sync operation on E, which involves promoting the larger of its two children until it gets to the bottom or a place where it's larger than both its children. So now we have just 5 elements left. We'll get the M, do heap ordering on the heap of 4, and that only involves one exchange. Now we get the L. A exchange with the larger of its two children. Well, they're both the same, so it goes with the left one. That's a heap of size 3. Pull off the first E. It's already heap ordered. Pull off that E. And now we're left with only one element in the heap, and it's in the first position, so there's nothing to do. So with a series of N exchange and then sync operations, we pull the sorted array out of the heap. Okay, this slide summarizes the code for heap construction, and as you can see, it's a one-liner. We go backwards through the heap, starting at n over 2, because the n over half of the rightmost half of the array is just little heaps of size 1. We just go backwards doing a sync starting at k. So that's the first piece of code for heap ordering an array with arbitrary values. And then these diagrams summarize the sync calls that we just went through in the demo, starting at 5, 4, 3, 2, 1. As you can see, only 1, 2, 3, 4, 5 exchanges are needed to bring this into heap ordering. Then the second pass, again, that's only a 2-liner. We exchange the first element with the one at the end and then decrement the size of the heap and then do sync operations. And these diagrams summarize the sync operations that we showed in the demo. On an ever smaller heap, we continue just performing sync operations at the root until we get a completely sorted array. Given the sync implementation, we had a 1-liner for the first pass and a 3-liner for the second pass. So that gives a complete implementation of heap sort with the code that we've given so far. There's one little detail. When you're sorting an array, of course, position 0 comes into account. And we've been building our heaps from position 1, but we can take care of that in the less and exchange methods by just decrementing the indices in those methods to have it work as if the array were 0 through n. And that's a little implementation detail, but otherwise this is a fine sort implementation that actually is very little code, and it's got a place in the theory of algorithms that I'll talk about in just a second. This is just another trace without the data structures shown to just show in our standard way the elements in black and red are the ones that are touched, and the elements in gray are the ones that are not touched at all. And to just show that this thing gets the sort done with touching relatively few elements. That's a trace. Let's look at an animation. Animation of heap sort is interesting to watch. The construction of the heap happens in a blink, and now it's pulling off the largest elements moving from right to left. Again, a very efficient way to get a sorting job done. So what about the mathematical analysis? Mathematical analysis for the heap sort part is pretty easy. N times, we're doing a sync operation, and the size of the heap is at most log n, so it's n log n. The construction actually, it turns out, although it's a little more complicated to prove, that it always uses just a linear number of compares and exchanges. And that's an interesting result in itself. You can build a heap from n values in linear time. And then in n log n more time, you can sort from that heap. And that's significant because it's the first sorting algorithm that we've seen that is both in place and manages to get the sorting job done with guaranteed n log n compares. Merge sort doesn't do that. It takes linear extra space. Quicksort doesn't do that. It takes quadratic time in the worst case, even though we make that unlikely by random shuffling. It still takes quadratic time in the worst case. But heap sort does both. Now there's more complicated versions of merge sort and quicksort that can do this in theory, but heap sort is a pretty simple algorithm that gets both done. So if on a job interview somebody asks you what's an in-place sorting algorithm that's guaranteed n log n, your answer is going to be heap sort. Now in practice, heap sort's actually not used that much for a couple of reasons, and they might ask you these on your job interview too. First thing is the inner loop is longer than quicksorts. Like merge sort, there's more things to do in the inner loop. There's that compare the two children bigger, and then compare. So there's two compares that get done in n log n times, and then there's some that array index arithmetic. The other thing, which is probably more significant on modern machines, is that the references to memory are all over the place when it's a huge array. So it's not a good algorithm for a situation where there's caching, which is almost everywhere nowadays. It doesn't have local memory reference like quicksort does. It's always referring to something that's nearby something else that it just referred to. So if a big block of things comes into memory, there's no more extra cost. Whereas heap sort is going to look far away from the current place as it goes down the tree, and that makes it slower in a lot of situations. And the other thing is it's not stable. Sometimes people choose to use merge sort in practice because of the stability, but heap sort's not stable for the usual reason that it does long distance exchanges that might bring items that have equal keys back out of order. So that's our full summary of sorting algorithms. It completes our treatment of sorting algorithms with heap sort. And this is just adding the heap sort line to the table. It's in place. We don't use any auxiliary array. It's not stable, but its worst case guaranteed time is proportional to n log n, as well as the average and the best. This is not a trivial result, but it's also the case. So it's n log n guarantee in place, but it's not stable, and we still have the hope that someday somebody will develop a simple, in-place, stable, worst-case n log n algorithm, but we're not quite there yet. And that completes our treatment of sorting algorithms with the heap sort algorithm. Now we'll look at an interesting application of priority queues that's actually representative of a whole family of critically important applications in applications of computing. It's called event-driven simulation. And the idea is we want to study some property of the natural world by simulating it. And that's something that's very, very common in scientific inquiry nowadays. And this is a very natural idea. And actually, the idea goes back to Einstein. So we want to simulate the motion of n moving particles that might collide. With a priority, this kind of simulation is enabled by priority queues. Without something like priority queues, you couldn't do this for a large number of particles because it would require quadratic time and simply can't be afforded for a huge number of particles. So let's take a look at how we can possibly make this happen. So we use a simple scientific model called the hard disk model, and then this is just for simplicity to get this done in just part of a lecture. Clearly, these things can be extended in many ways. So we're going to have moving particles that either collide with each other and with the walls, and each particle is a disk that's got known position, velocity, mass, and radius. And there's no other forces involved. It gets more complicated if there's more forces, like gravity involved. And this one by itself is very significant. As I mentioned, goes back to study of physics with trying to understand pressure and temperature and Einstein's famous experiment on pollen grains showing that their motion was Brownian or random. So whether it's individual atoms and molecules or it's some bigger kinds of particles, it's a complex dynamic situation that is better understood through computer simulation. And nowadays, that means priority queues. So as a warm-up, here's the code to implement bouncing balls without the collisions. And this is an elementary programming exercise that is the code at the left has the effect shown at the right. So we have a data type called ball that represents just one of the particles and has instance variables that has the position and the velocity. So we make a bunch of them, and then we have a while loop, which is just every 50 milliseconds, clear the whole drawing, and then move the balls a little bit, and then draw them in their current position. And the only thing the move operation does is to update the position of the ball by the velocity, which is just another number, and then it does the bouncing off the walls. If it happens to hit the left wall, you reflect the x-coordinate, and the right wall, you reflect the x-coordinate, and bottom and top, you do the same for the y-coordinates. So this is an easy programming exercise given the right display primitives. And it's a good exercise in object-oriented programming showing how just one implementation, then we can use that same implementation to simulate a number of instances. So that's our starting point in terms of the code. So this is the implementation of the ball class. So it's got position and velocity, as I mentioned, and every ball has a radius. And then there's a constructor, and maybe we have a constructor that takes arguments that would initialize the position and the velocity, or maybe initialize them to a random position if there's no arguments. And then here's the move method. And the move method, again, most of the times just takes the x and y coordinates and adds the current velocity times the speed constant, dt, or speed variable that's given as argument dt. And then these tests are for whether it hits the walls, in which case you have to flip the x or y velocity. And then draw is just using standard draw, just draw the ball. So that's all the code for doing the bouncing ball simulation. Now, what's missing in this is what happens when the balls collide with each other. And to cope with that, we need to do both a little bit of high school physics and a little bit of basic computer science. So the physics problem is exactly what happens when two balls hit. They bounce off each other according to some well understood physical process, and that's the high school physics. And the CS problem is how and when do we exactly do these computations for each of the balls, and how can we do it efficiently, that is in n log n time versus quadratic time. Because if we have a computational process that takes quadratic time, then it's not going to scale. We're not going to be able to do large numbers of particles. Simulations of the real world, usually we wind up doing huge amounts of data, and we cannot have a quadratic algorithm. And this is just a first indication of that, of why if you want to do this simulation, you better know about some data structure like priority queues. If you try to do it without it, you're not going to be successful. All right, so let's take a look at what happens. So there's a number of things that you might consider trying. So one idea is a so-called time-driven simulation. And we just say we're going to update everything every dt seconds. And then we go ahead and do that, and then we could check if there's a collision, if the two balls, some pieces of two balls are occupying the same space. And if there is, then we could roll back time just a little bit and try to figure out exactly the moment at which they collided, and then figure out how their position of velocity should change accordingly, and then continue the simulation. But this has a huge problem. The first one is that you have to check all pairs of balls for overlap. So that's quadratic. So it's going to be really a lot of overall checks. You're not going to be able to do it for a huge value of n. But the other thing is, even if n is small, if you do a very small dt, then you're just doing this calculation over and over again, and there's just too much computation, moving the balls a little bit at a time. On the other hand, if you try and improve things by making dt too large, you might completely miss a collision, as shown in the example at right. So figuring out the value of dt that would really work is a huge problem for the time-driven simulation. Instead, what we want to do is called an event-driven simulation. And this is a very general concept that's useful in all kinds of contexts. And we're only going to change things when something happens. So since the only thing that matters is collisions, we're going to figure that particles move in a straight line between collisions. And what we're going to do is focus only on the times when the collisions are going to occur. And so the way we're going to do that is to maintain a priority queue. And that priority queue is going to have all the possible collisions that could happen in the future, and they're going to be prioritized by time. And when we remove the minimum element from the priority queue, that's the next collision that we have to deal with. And so we have two phases. We have prediction and resolution. So at some time, t, we can take two particles. We know their position and velocity is shown at the bottom here. And we can predict exactly the moment at which they'll collide, assuming that something else doesn't happen to them in between. And then, so then we'll put that predicted collision time on the priority queue. Then later on, when that time comes to pass, we'll be right at the moment when they collide, and we can figure out what to do. Now, there is the possibility that something else happened to them in between, and we'll talk about that change too. So we have to do collision prediction, which is given position, velocity, and radius, when's it going to hit with another particle or the wall. And then there's resolution, which is to figure out how to change the velocities of the particles according to physical laws. Now, this part I'm not going to talk about in that much detail right now because it's high school physics. And so I think most students have had some high school physics and will be able to do this math or at least be convinced that the code that does this math is correct. So if you know that you have a particle that's at a certain position, Rx, Ry, and it's got a certain velocity, Vx in the x direction, Vy in the y direction, then you can, from the distance to the vertical wall, you can figure out how many seconds it's going to take until it hits it. It's basically that distance divided by the velocity. And so that's the prediction. And then the resolution, when it hits the wall, is just going to change the velocity. So that's you know what the position is. So that's just an example of collision prediction. When's it going to hit the wall? And resolution, what do you do when it gets to the wall? When you have two particles, there's definitely more math. And again, this is high school physics, and we're not going to test on it or even go through the details. But it's just a little bit of arithmetic with the velocities and the positions to deal with what happens how to predict when a given particle is going to collide with another given particle, knowing their velocity and position. So you have to take both velocities and divide their distance by those, and so forth. There's simple formulas to tell us what to do, and we can also figure out the formulas for what we do once they do collide. And again, nobody's claiming that this is easy, but this is the physics part, and it's worked out, and it comes from Newton's second law, and anybody taking high school physics will be able to deal with these formulas. And the rest of us may have to go to a reference book to get up to speed on them. But once it's reduced to code, we can it might have some trouble debugging at first, but at least we can be convinced that it works. But now let's look at the computer science code. So this is just extending our ball data type that we use for the bouncing balls that didn't collide to taking into account these extra things. So ours will have mass, so there'll be some big heavy ones that make things more interesting. And there's also a variable called count, which is the number of collisions the particle's been involved in, and that's useful for a couple of purposes. So we're going to need a bunch of procedures which do the prediction and the collision resolution. Given a particle, what's the time till we hit that particle? What's the time till we hit a vertical or horizontal wall? And the same thing is if we're at the point where we're hitting a particle, what do we do? Same with vertical and horizontal wall. So that's the skeleton. We need those procedures that implement those physics rules for every particle. And this is what they look like. And again, this is high school physics, so we're not going to do it in detail, other than to point out it's really not a huge amount of code. Lots of dx's and dy's and dv's, but really not a huge amount of code. And the other point is we're going to return infinity if there's no collision at all. So that is going to keep that on the priority queue, that event on the priority queue forever. Okay, so that's the procedures that we need, and then there's similar ones for the horizontal and vertical walls. Okay, so now let's look at the main loop for the event-driven simulation. So the first thing is we're going to, for every particle, we're going to compute the next time that it might hit every horizontal and vertical wall. Well, actually, if it's going away from a wall, it's not going to hit it, so that would be infinity. But if it's going towards a wall, then we'll compute the time, and then that's a time in the future. We'll put that event on the priority queue with that time as the key. And then we'll do the same thing for all pairs of particles. So we do have a quadratic initialization phase that we perform just once to get the priority queue filled up. Now, all collisions might not happen. So we might have two particles that are on a collision course, and we're going to predict that point for both of those particles, even right at the beginning. But it might be the case that there's a third particle that knocks one of those out before that thing happens, and that event would be invalidated. So the simulation has to be careful to take that into account, but that's not difficult to do. So here's what the main loop is. So we're going to take the next event from the priority queue. That's the next collision that's going to happen. From all our calculations, there's one collision that's going to happen next. Then we test whether that event has been invalidated. And we do that by using that count field in the particle. So then that tells us what time it's going to be next. So then we have to go through all the particles and change their positions on a straight line trajectory. Where would there be after that much time? Then we have to take the two particles that collide and change their velocities. They bounce off one another. Now those two particles' velocities have changed. Essentially that invalidates the future collisions involving those. And then what we have to do is for those two particles is go through and predict the future collisions with any walls and collisions with any other particles and put all those new events onto the priority queue. but that's it. You got two particles, change their velocities, figure out the future collisions of those particles with the wall, and update the priority queue. Then the main loop is take the next thing off the priority queue and keep going. That's the code that we'll look at next. We have a bunch of convections just to reduce the code. If we have this thing called event, which involves, it says between two particles something is going to happen at a certain time. And we're going to adopt the conventions that if neither particle is null, then we're talking about two particles. If one of the particles is null, then we're talking about a wall, a vertical or horizontal wall. And if both particles are null, we're saying we just want to redraw things. That's a bit of a hack, but it cuts down a lot of code. Our compare to is by time. And then, again, we need an is valid to check about intervening collision. And then here's the skeleton of what's going to happen with the collision system, which is the key thing is this prediction method that takes a particle as argument and adds to the priority queue all the possible collisions involving this particle. So it's going to go through every particle and call the time to hit method for that particle, and then it'll put an event on the priority queue for that time, this particle with that particle. And then it'll also put an event for the vertical wall and the horizontal wall, again using this null convention to say that the event second argument null is vertical, first argument null is horizontal. So that's a key method that gets used in the simulation for each of the two particles that are going to collide. So now we can look finally at the main event-driven simulation loop. There's build the priority queue. There's do this prediction for every one of the particles. And then also we're going to put as the first thing to happen always an event that says redraw everything. That's just a way of making sure that the simulation keeps proceeding. It's an easy way to get things drawn. Okay, so now the main loop is while the priority queue is not empty, we're going to pull off an event. We're going to test whether it's valid, and that's to just check if anything happened with those two particles. We're going to pull off the two particles, and then we're going to move all particles by the amount of time that has elapsed since the last event. And then we're going to test which of the four types of events that it is. It's either redraw, bounce B off A, or bounce off a vertical wall or horizontal wall. And then we'll go ahead and do the predictions of each of those particles, A and B, against all other particles. That's pretty much all the code for the simulation. This is data-driven code. One thing we can do is just run it for 100 balls in random position at random velocity. But what's nice about data-driven code is now that the code's working, and again, we're not saying this is trivial code to write, but it's definitely manageable, and it's enabled by priority queues. Without priority queues, it would be quite a bit more complicated to figure out how to do this, and also it wouldn't be reasonably efficient at all for large data sets. So that's a simple simulation, just generate random positions. People might be interested in this one. Now, this isn't exactly precisely what would happen in the real world, mainly because we didn't put in the simulation what happens when three particles are touching, or there's two touching and another one hits them. And also, nobody racks up a set of billiard balls such that all 15 are touching in all places. So life can be complicated when you're trying to simulate the natural world. This is a little bit about Einstein's experiment. If you got one big particle like a pollen grain and lots of little particles like atoms, molecules bouncing against it, the big one is going to move about randomly. Then this is another famous physics experiment showing diffusion. There's many other things that you can do with this basic collision system. If you have huge numbers of particles and you measure the number that hit the sides and the frequency with which they hit the sides, you can do experiments relating temperature and pressure and many other things, or do three-dimensional versions. Again, simulation of the natural world is an increasingly important application of computing. And you need efficient data structures like priority queues to get it done. Welcome back. In this and the next few lectures, we're going to look at symbol tables, a fundamental and extremely important data type that have led to all kinds of fascinating implementations, and we're going to look at several of them in this course. To begin, we'll take a look at the API and some elementary implementations and various operations that people want to perform on symbol tables. Start with the API. The idea behind symbol tables is to implement the following abstraction. We're going to have keys, like our keys in priority queues, but the whole idea is that we're going to want to associate values with each key. So the two operations that we're going to perform in symbol tables is the insert operation, where we're really putting a key value pair into the symbol table, a value with the specified key. And then given a key, we want to search for the corresponding value. Those are the two basic operations. Now the keys and the values can interchange roles, and that's why we have the abstraction to separate them. So, for example, a domain name server might have a lookup where you've got a table that's got an IP address and a URL associated with that IP address. And different clients might want to use this data in different ways. One might want to use the URL as key. Given the URL, give us the corresponding IP address. Another client might want to use the IP address as key, have an IP address, give me the corresponding client. So those are just a couple of examples. This is a very fundamental and basic abstraction. And the list of applications is huge. In fact, almost any computer application system is going to have a symbol table or multiple symbol tables at its core. All the way down to the basic memory system of the computer or the networking system that your computer access to information depends on. You can think of it intuitively as like a dictionary. Well, there used to be books, and people would open up those books to look for a word to find the definition. Nowadays, you're more likely to do that online. Or when you're trying to find a song to download, you provide the name of the song, and then the value will tell you what computer to go to get that. Or in commercial computing, the key might be an account number, and the value might be the transaction details for that account. Web search is something we all do multiple times every day, and the key is a keyword or a list of keywords, and the value is a list of places where that keyword is found. And there's many, many other applications, including scientific applications, where, say in genomics, people use symbol tables to keep track of finding markers in a genome, and again, many other applications. So it's a very fundamental concept, and we'll look at plenty of applications, but first we want to look at some algorithms. So the way that it's convenient to set up a symbol table is to implement the so-called associative array abstraction. And the idea behind that is to think about just associating one value with each key. Well, it's like in a Java array of integers, say. Our keys in that case are indices that are restricted to be between 0 and the array size, but we're only associating one value with each index. We think of storing the value in the array position given by that index. And a good way to think of a symbol table is as shown in the right here. When we put a key value pair onto the symbol table, think of that as using the key to index an array and storing the value there. Now this isn't legal in Java if key is not an int, and we're going to do this generic. It can be any type of data. But it's a good way to think about it. And then to retrieve it, you just give that same key and it'll return the value. So that's our two primary operations. Put a key value pair into the table, so that is associate the value with key, and then get the value paired with the key. There's particular rules for null that I'll talk about in a second. And then to properly maintain a symbol table in a dynamic situation, in many clients you want to support a delete operation, and contains is a simpler operation than get that's convenient for many clients, where it just tells us whether there's some value paired with that key in the table is empty in size. And then another thing that you might want to do is iterate through all the keys in the table. So those are the basic operations that we're going to want to implement to get the associative array abstraction. And then there's many, many possibilities for clients, and we'll look at some later on. Now there's a couple of conventions around null. And these are not critical, but they make it a bit more convenient for several implementations. So we're not going to allow null values. You can't associate null with any key. And then we're going to adopt the convention that the get method returns null if the key is not present in the table. And also the associative array abstraction is the put method will overwrite an old value with a new value. So these are our consequences. So it's the contains implementation is the same for all our symbol table implementations. If get returns a non-null value, then there's a value corresponding to that key in the table. If it returns null, it's not. Get returns null if key is not present. And the other thing that we can do is we can use null in some situations or temporary situations to implement a lazy version of the delete operation. We can associate the key with null internally, and then a client won't know the difference whether that's in there or not. And some algorithms take advantage of the ability to use null in this way. These are just conventions and somewhat details, but it's important to point them out at front. So now we're going to want the value to be any generic type at all, but the key type we have to make some natural assumptions about them. And actually there's different assumptions that we make in our implementations depending on the application. One of the most useful ones is to have comparable keys. Just as in sorting algorithms, we'll assume that the keys have are values that come from a total order, and we can use compare to compare whether one key is less than another or not. This is for two reasons. One is we can get more efficient implementations if we can use the ordering of the keys to help us find our way around the data structure. And the other reason is that we can support a broader set of symbol table operations that are very convenient for many clients. And it's very typical for keys to come from an ordered set, for example, in the dictionary application, or if keys are strings or numbers or count numbers or many other situations. So if they're going to be comparable, we might as well take advantage of it, both to get more efficient algorithms and to be able to take advantage of a broader set of operations. Now, in other situations, maybe they're not comparable, and all we are allowed to use is to use the equals operation. That is, everything, every type of data in Java has to support an equals operation. That we use that to test whether they're equal. And there's another family of methods where there's no ordering, and there's a special method called hashcode that helps us inject randomness into the process. That's built into Java, and also some classic algorithms depend on that. We're going to start out with the comparable mostly. And again, as with priority queues, the best practice is to use immutable types. And experienced programmers know this, and it's not difficult to arrange for the natural types of data that people are going to use for symbol table keys. Unreasonable to expect the implementation to work well if the client can change the values of keys that are in the table. If you want that, you have to provide that as a specific operation. But in case of symbol tables, we're not going to do that. You'd have to remove it and put it back in. All right, so there's equalities. Now equality, again, we're getting into a programming language issue, but still it's important to be explicit about what's going on with equality. How do we test if two objects are equal? So Java's got requirements as for compare to, and here's the basic requirements about equals. There's a method that all Java classes inherit for equals, but the default implementation is simply to test whether the references are equal. Are those precisely the same objects or not? Usually in applications, when we want to have something more general than that, we have a concept of a value, or like a key in our case, and then we want to know if two references refer to objects that have the same value, and we want to call that equal. That's what equals is about. So anyway, we're required to make sure that x is always equal to x, and that x equals y is the same as y equals x, and if x equals y, y equals z, then x equals z. So that means that in mathematical terms, equals is called an equivalence relation. And also, no object is equal to null. So those are absolute requirements for Java. And again, the default implementation is to check whether they refer to the same object, and that's rarely what we want. Java systems programs maybe want that, but client programs usually have customized implementations that are based on comparing some sort of value. And the standard built-in types of the Java language are going to have those customized implementations, and we can rely on them doing what we expect. If we're going to implement our own types and then use those types as keys in symbol tables, you have to exercise a little bit of care, and we'll talk about that briefly. So say we have this simplified date implementation that we had talked about before. It's a mutable type, and every date's got a month, a day, and a year. It seems like it should be easy to implement equals. Basically, we're just going to check that all the significant fields are the same. Two dates should be equal if they have the same day, month, and year, and if any one of those are not the same value, then just return false. So that seems as if it should work, but that doesn't have all the characteristics that we need in a Java implementation. And so all of this code in red shows a model for what you might do if you're going to implement your own type of data, equals for your own type of data. Shouldn't use it in connection with inheritance, so we don't use inheritance that much, so I won't talk about that. The type of the argument in the equals must be object. You'd think it should be date, and experts debate about that. And people who are interested can look on the web for that kind of date. If it is the case that you happen to be testing two objects that are the same object for equality, you might as well optimize everything and just test that. If y is a reference that's pointing to the same object as this object, just return true, because if you're going to test the values, they're going to have the same values anyway. And that's a good optimization for lots of situations. Why go through all that rest of that code if you know right away they're equal? There's this test for null that has to be there, and if it's not there, can lead to nefarious bugs and unusual problems. So your equals test, you better test that the client didn't give you null. They have to be in the same class, and well, there's a couple of different ways to check about the same class, and that's another religious debate that we'll ignore. We'll use get class, and that's something that's got to work, or they'll get an exception in this later code. Because since y had to be an object, now we have to cast it to a date. And then it better be the right class, or otherwise it's not going to have these fields that we can test for. So details, but anyway, you can use this code as a model to implement equals for any data type that you might wind up using as a symbol table key. Okay, so that's a standard, this is just in words, the standard recipe for user-defined type, optimized for reference equality, check against null, make sure they're the same type and do the casting, and then compare all the similar significant fields. It could be that if one of the fields is an object, then you use that object's equals, which applies the rule recursively. And then if you have a field that's an array, you can go ahead and try applying it to each entry. And there's implementations in Java. You don't want to use a.equals b. That checks if those arrays are the same objects, and that's not what you want. You want to check that all the values are the same. And if it's an array of objects, you can see that testing for equals can actually involve a lot of code and a lot of cost. All right, so, and certainly you want to follow some of these best practices. So fields that are most likely to differ, those are the ones you might want to compare first. And you're also going to want to make compare to consistent with equals. Though we'll generally, if we have comparable types, we'll use compare to, and if we don't have comparable types, we'll use equals. Okay, so now let's look at a couple of test clients before we look at any particular implementation. So this is a test client. So symbol tables are, ST is the type, symbol table. They're generic on key and value. And so this statement builds a new symbol table with string keys and integer values. So it's going to associate integers with strings. And so what the test client's going to do is going to just go in a loop as long as standard in is not empty, and it's going to read a string off standard input, and then put it in the symbol table associated with the value I, where did it appear in the input. So this is an indexing client where we associate each string with its position, most recent position in the input. And notice it's an associative array implementation. So for example, we have two E's, and at the end, E is associated with value 12, the place where it most recently appeared. We could also keep these things in a bag and do a client that gives all the positions that appeared. This is a simple indexing client that we use for our traces. For analysis, for bigger problems, we'll use a client called a frequency counter client. And so that one is going to read a sequence of strings from standard input and print out the one that occurs with highest frequency. So for this small data from the beginning of Dickens' Tale of Two Cities, if we run a frequency counter, the frequency counter client, and this first argument is just ignore words of fewer than this many letters. It'll say that the most frequent word, where there's no word that appears more frequently than it, which appears 10 times. And we'll want this client to work well for huge data sets. So Leipzig is a data set from the web of 20 million words, about 500,000 distinct ones. And in that corpus, the word government appears about 25,000 times. So if you have a quadratic time algorithm for implementing symbol tables or linear time for each operation, you're not going to be able to run this client in a reasonable amount of time for a big amount of data. So that's the client that we're going to use for analysis. Here's the code for that frequency counter client. Again, it's similar to the other one. We're creating a symbol table that associates strings with integers. We take that command line argument, which is the minimum length that we care about. We'll read a new word, and we'll ignore the short strings, just trap out if the word length is too small. And now the integer that we're going to associate with each word is the frequency of occurrence of that word in the symbol table. So if the word's not in the symbol table, we'll put it there with a frequency of occurrence of 1. That's the first time we saw the word. If it is in the symbol table, we'll just overwrite the old value, which is stgetWord, with the new value, stgetWord plus 1. So increment the frequency in the symbol table. So this loop reads in all the data and associates each word with its frequency of occurrence. And then we'll have a client that uses the iterator going through all the keys in the symbol table. It'll get the value associated with each key. And if that's bigger than the maximum found so far, we'll save that away and then print out the word that occurs the most often along with its frequency. So this is a useful and non-trivial client that's enabled by symbol table, but it won't work well unless we have an efficient symbol table operation. And we'll use this client to compare different symbol table implementations. So that's the symbol table API, and next we'll take a look at implementations. Next we'll look at some elementary symbol table implementations. These are so simple that we won't go into much detail, but still it's worthwhile to take a look at them to set the stage for the more advanced implementations we'll consider next. Well, one thing we could do is maintain a linked list. We could keep it in order or keep it unordered. This version keeps it unordered. So we're going to have nodes in the linked list that have key value pairs. They have every key in the symbol table and a value associated with that key. For search, we have to, since it's unordered, scan through the whole list to find a match, a key that's there. For insert, we'd also have to scan through all keys to find the place to update a value if it's a value that's already there. And if there's no match, we could add it to the front. So here's our simple client for traces. So if we associate S with 0, we just add it. That's our one node linked list that's got that information. Associate E with 1, that's not there, so we just add it to the beginning of the list. A with 2, R with 3, C with 4, H with 5, and so forth. So now when we associate E with 6, we have to search through the list to see if there's an E. And in this case there is, and then we just update that value. That's the associative array abstraction. It's possible to implement symbol tables that allow multiple values with the same key and so forth, and that leads to different types of clients, different types of implementations. We're going to stick to this associative array abstraction and no duplicate keys in the symbol table because it both simplifies implementations and leads to simpler client code. Okay, X7 is a new value. A8, we found A in there and update the value 8. And then M9, P10, L11 are all not there and they go at the beginning. And then the last one changes the value at E again, 12. So this is a simple, implementing this is a simple example of linked list processing. Slight modification of our stack and queue code, and we will skip the details and just note that what's the cost of implementing this? If there are n things on the symbol table, you have to, for both search and insert, look all the way through. If everything's random, then on average you only have to look halfway through for a successful search, while you still have to insert. Another issue is for many clients, if the keys are ordered, it's nice to be able to iterate through the symbol table in order, and this one by definition doesn't provide that. This one just uses equals, so the keys don't have to be comparable for this. It just uses equals. Our challenge is to look for methods that give us more efficient implementations of these search and insert operations. And we've already looked at an algorithm that can do this, and that's binary search. So for binary search, what we're going to do is use an ordered array and actually use parallel arrays, one for the keys and one for the values. And the idea is to keep the array of keys in sorted order and then find the index associated with the key that we're searching for using binary search, and then use that index to get the value associated with that key that's stored in a parallel array. We looked at the binary search algorithm earlier in the course, and so, for example, if these are the keys in our symbol table, and we're doing a search for the index where P is stored, we look at the middle. P is bigger than L, so we look to the right. Look in the middle of the right half. P is less than R, so we look to the left and continue until we find P. When we find P, we return its index, and we use that index to get us the value that we need. Or another way to look at this is it implements the function, how many keys are there that are less than K. So for example, for Q, that's an unsuccessful search, and you can figure out from the last index when you don't find your element that you're seeking, you can figure out the return value, which is the number of keys that are less than it. So that's a trace of implementing binary search to find the rank of a key in ordered array. And again, for successful, you can use that rank to return the value, and for if it's unsuccessful, you can use that rank to figure out where to insert the new key. All right, so this is the code for the get operation in this rank, which is binary search. This is precisely the binary search code that we looked at before. So let's look at the get. If the whole table is empty, we return null. Otherwise, we call rank, and that gives us the number of keys less than the current key. And so that is where we look to check to see if that key's there. If it's there, then we return the value with the same index in the parallel array. If it's not there, then we return null, saying the key's not there. Now, the problem with binary search is well, not necessarily the problem, but the situation is that when it's time to insert a new element, we have to move everything larger over one position, just like in insertion sort. So if the table has A, E, R, and S, and we have to insert the value C, then we have to move the E, R, and S over one position to put the C, and then put the value associated with C. You have to do the same thing in the vals array, move all the values associated with those keys over one position, and put the associated value in. So this is a trace of what would happen for our trace. And again, every insertion involves making a new position by moving all the larger keys over one position. Do the same thing in the vals array. And if it's changing the value associated with the key that's already there, then it's just a matter of finding where the key is and changing the value at that index. So those from that trace, it's pretty easy to see what's involved for the code, and we'll skip that code and just take a look at the comparison between this elementary implementation for symbol tables with the sequential search in an unordered list. So one thing is we're using a different key interface. We're taking advantage of the fact that the keys are comparable to give us an efficient search. We can do search in worst case, in average case, in time proportional to log n. That's what binary search provides for us. And this is a fine data structure for symbol tables where there's that are relatively static, where the values don't change much, and most of the operations are search. It's hard to beat binary search. On the other hand, in a dynamic situation where there are a lot of inserts, this method is going to be problematic because the cost of insert is linear. It's proportional to n over 2. If you have a huge number of operations and every one of them is proportional to the symbol table size, then you're just not going to be able to support huge numbers of keys. What we want is efficient implementations of both search and insert. Those are elementary implementations. Next we'll look at more advanced ones. When keys are comparable and we can put them in order, we saw that we can use binary search to get an efficient symbol table implementation. But we can also provide a lot of convenient functionality for the client. That's what we're going to look at next. So this is just an example of an application that might try to associate keys with values, and an illustration of all the different operations that a client might want. So we already looked at the get operation, so we might want to know what city is associated with the event that happened at time 9:13, and so that should return that value. But there's plenty of other things that we might want, like, for example, what's the earliest time? That's the min. Or what's the latest time? That's the max. What about being able to iterate among all the keys between two given times? That certainly is convenient. Then there's what's the seventh largest time? So that's select like the median, or it generalizes min or max. Which key happens second or seventh? So that's order statistics in our dynamic thing. What happened, what's the closest time thing that happened just before 9:05? Certainly plenty of clients might want that. So this one is, I've only got 10 tickets to sell, so that's the cutoff point for selling, or 7 tickets, that's the cutoff point for anybody after that time doesn't get a ticket. And this one might be, if there's a time cutoff, I'm not going to sell tickets to anyone that came after that time. And then the corresponding one is, what's the first thing that happened after that time? That's call into the radio show. I'm going to take that caller, first call that comes at 9:30, and so forth. So then see how many things happen between 9:15 and 9:25, and how many calls were there before 9:10:25. So you can see that all of these operations are quite natural when we have the table in sorted order, and that's what we have for our binary search implementation. So we can implement these efficiently, and they are convenient and useful for the clients. Typically for ordered symbol tables, when keys are comparable, will provide a much wider interface. It's very useful for many clients. So we say that we're dealing with keys that are comparable by simply adding this extends comparable key to our declaration, same way we did for sorting methods. So all that means is our implementations can use compare to. But for the client, it means that all of these operations have meaning. Give me the minimum key, give me the largest key, and then I can get the value associated with that using get. Give me the largest key less than or equal to this key value, or the smallest key greater than that key value. Give me the number of keys less than that key. You can actually implement priority queues this way. Delete the minimum key, delete the largest key. Usually we argue against wide interfaces, just adding operations to an interface. But usually our reason for doing so is that we can't guarantee that all the operations can be performed efficiently. In this case, as we'll see, ultimately we have ways to guarantee that all the operations can be performed efficiently, and they're so convenient for clients, it's certainly worth adding them. So we have iterate through all the keys and iterate through all the keys in a given range and count the number of keys in a given range. All of these operations are very useful for clients, and we'll see plenty of examples later on. So we have to greatly expand our table. What are going to be the costs of all of these things? And this is a big difference between the binary search implementation, where the keys are kept in order in an array, and the sequential search implementation when they're all in a linked list. So for example, to provide ordered iteration, you have to get them sorted, and that's going to be a lot of work and take n log n time. Whereas binary search, you just iterate through the things in order. Give me the seventh key, we just go and look there, they're in order. The rank operation, that's essentially what binary search provides. That's our basic implementation is providing rank. Floor and ceiling, that's again an outgrowth of the rank operation. Minimum and maximum, well, again, those are like select, they're just right there. You look at the first or the last. To insert or delete, however, takes linear time. To maintain the sorted array in dynamic fashion is going to take linear time. You have to go through the whole thing. And so that's really the key to thinking about ordered symbol tables and symbol tables in general. How can we guarantee that all operations are fast? Binary search is pretty good, but that's a major flaw. It can't maintain a dynamic table efficiently with binary search. And that's going to be our focus in the next lecture. Welcome back. Next we're going to talk about binary search trees, a classic data structure that will enable us to provide efficient implementations of symbol table algorithms. Let's look at the basic binary search tree data structure. With heaps, we talk about implicit representations of trees with an array. For binary search trees, we're going to talk about actual explicit tree data structures. A binary search tree is a binary tree in symmetric order. Let's look at the meaning of those words. So a binary tree is an explicit data structure. It's got what we call nodes, which contain information, and every node's got two links, two binary trees that are disjoint from one another, a left tree and a right tree associated with each node. Each node has a left tree and a right tree. Links can be null, left tree can be null and right tree can be null, or both. We refer to every node in the tree as the root of a subtree, and we've referred to the nodes below each node as its children. So this is the right child of the root, and that's a left link, and so forth. So that's the definition of a binary tree. Binary search tree, each node has a key, and every node's key is larger than all the keys in its left subtree and smaller than all the keys in its right subtree. So this is a different ordering than we had for heaps. Heap, we had every node larger than both its children. This one, every node is between the value of every node is between the values of the nodes in its two subtrees. So the nodes to the left of E are smaller, the nodes to the right of E are larger. Now we're going to use these to implement symbol tables, and there's values associated with each key. When appropriate, we'll write the values in small numbers next to the keys, but usually we're just going to worry about the keys, and we'll keep the values in the nodes along with them. So that's a binary search tree, is a binary tree in symmetric order. That's the data structure that we're going to use to implement symbol table operations. So how are we going to represent binary search trees in Java? Well, we're going to extend our implementations of linked list structures to have two references instead of just one. So first of all is there's a node at the root, so a binary search tree in Java is just going to be referenced to a root node. And every node's got 4 fields, a key and a value, and references to the left subtree that contains the smaller keys and the right subtree that contains the larger keys. So here's what the code is based on. The inner class that we'll use to implement nodes has 1, 2, 3, 4 instance variables, all of which are private as usual, a key of type key, a value of type value, and then references to a left and a right node. For convenience, we'll provide a constructor that takes a key and value as argument and fills in the key and value instance variables. And then the left and right links are initialized to null. And our data structure then will be a root that points to a node in the tree, and then that node will point to subtrees, and that'll be the data structure that we use for symbol tables. So here's a skeleton of our symbol table implementation. It's for comparable keys associated with values, and those are both generic types. The only instance variable is a link to the root node called root. The inner class node is the code that was given on the previous slide, and then we'll need implementations of put and get, and we'll also look at an implementation of delete and an iterator as well. So that's our skeleton implementation. Let's look at the keys. So let's look at search first. So here's a binary search tree. Let's do a demo of what different searches will look like in this tree. So there's a tree. So S is at the root. Everybody to the left is less than S. Everybody to the right is bigger. So this is a dynamic data structure that kind of follows the same rule as binary search. So to look for do a search for the key H in this tree, we start at the root, and we compare our key against the key at the root. And in this case, H is less. So all that says to us is that if H is in the tree, it has to be to the left, because everybody to the right is greater than S. So we move to the left and compare H against the root of the left subtree. In this case, that's E. Now H is greater, so that says we should go right. Now we compare H against the root of the right subtree of E, and that's R. And it's less, so we have to go left, because everybody to the right of R is bigger and H is smaller. And eventually, if the key is in the tree, we're going to hit it. And in this case, we find H as the left subtree of R, and that's a search hit. And for the get operation, we can return the value that's stored in that node along with the key H. What about an unsuccessful search? Well, the same rules follow. If it's in the tree, it's got to be according to the left or right, according to whether it's smaller or larger than the key at the root. In this case, if we're searching for G, it's got to go left because it's less than S. We come against the E, we got to go right because it's bigger than E. Against the R, we have to go left because it's less than R. We come against the H, we have to go left. And then we come off a null link. And all that says is that there's no place in this tree where G could be. So G is not there. So that's a search miss, and the get operation would return null in that case. What about insertion? Well, to insert a new key, all we do is follow the same steps as we did for search. That falling off that null link, and again, we'll just for G travel down the tree until we come to the null link. Really, what we're saying is when we go to the left link of H, it says if G is in the tree, it has to be down this link. Since it's not there, to insert G, all we need to do is just put it there. And that's how we insert a new node into a binary search tree. All right, here's the code corresponding to the process that we just demoed. And it's quite straightforward, simple code, as simple as binary search, really. We start at the root. We set a variable x to be the root, and that's going to be the pointer to the current node as we move down the tree. As long as our current node x is not null, what we'll want to do is a comparison between the key at node x and our search key. If our search key is less, we go to the left. If it's greater, we go to the right. And if it's equal, and we don't even have to test that, that's why it's in gray. If it's not less or greater, it has to be equal. Then we return the value right at that node. If we get to the bottom and our current node is null, and that's falling off the bottom of the tree, we return null. And that's equivalent to saying by our convention that that key is not in our data structure, or not in our symbol table. So that's a very straightforward implementation of the get operation for symbol tables with a binary search tree representation. Now what's the cost? Well, we went down a path in the tree, so it's 1 plus the depth of the node in the tree. So what about search? Well, search for put, there's two cases. If we're supposed to associate a value with the key, if the key's already in the tree, then we're just going to reset the value. If the key's not in the tree, then we add a new node at the bottom. So now it's a little bit tricky the way that we implement it, since we use a recursive implementation. And the reason we do this is that it generalizes to give us more efficient data structures later on. So what we'll do is use a recursive implementation that as it moves down the tree, it'll return a link up higher in the tree. And so when we insert a new node L, say in this tree, we go down that path, we create a new node and then return the link to that node higher up. There's ways to implement that don't involve this, but the code is so simple and it extends to more powerful data structures later on that we'll introduce this right now, and you'll see how it works. So this is very concise recursive code, but it's tricky because of that last point, so it's worth reading carefully. So we're going to use a recursive method put that to associate a value with a key in the tree. And that recursive method is going to return a node. So the client method put, of course, just is supposed to do the association, so it has a void return. But what we'll do is invoke our recursive method starting at the root, and whatever link gets returned, we'll set that to root. So right away we can see, let's suppose that we have an empty tree where root is null. So then if we put with null as the first argument, then null as the first argument, what we do is we say if the argument is null, return a reference to a new node that associates key with value. And then that one has null links. So in this case, that first call will return a link, and whatever link gets returned, that'll be set to root. So without any extra special code, we insert a node into an empty tree. And that works again recursively. Say we have one node in the tree and we have a new key to associate. And let's say that key is less than the key at the root. So now we do put, and it's actually a link to that one node that's got two null links. So it's not null, so we'll compare our key against the key in that node. If that comparison comes out left, here's how we do the insert. We change our left link, which is right now it's null, to whatever put returns. So what's put going to return? Well, that left link is null, so what's going to happen is in that call, x is null. It's going to be created a new node, and the link to that node will be returned, and that's the link that we'll put in the left. This is very concise code that otherwise would have to have various cases about saving which link we went down in order to reset that later on. So now the best way, having looked at those small examples, the best way to understand this code is recursively. Let's believe that it works for small cases, which we have just done. So let's see what the code does. So if x is null, we want to create a new node and return the link to that node. So even if it's a huge tree, down at the bottom, we just came off a null link. We just want to create a new node with our new key and return a link to that node. That's all we want to do. Now we can assume that put is going to return a link to a subtree that contains our new key. If our new key is smaller than the key at the node that we're processing now, then we want to insert the new key value pair in the new node on the left. Otherwise, we want to insert it on the right. Most of the time, the link that we get back will be the same as the link that we put in, but for that bottom node, it'll be different. So if put works properly, inserting a new node on the left, then that's what we want our left link to be. If it works properly, putting in the subtree on the right, that's what we want our right link to be. By the way, if we find a key that's in the tree already, then we just want to reset the value. And in all of these cases where we're on a node that already existed, we just want to return the link to that node. Again, when we look at more sophisticated values, we'll be returning something else. So it's worthwhile checking that you believe that this code implements the simple binary search tree algorithm that we demoed, where when we fall off a null link, we create a new node and replace that null link with the new node. So that's insert for binary search tree in a symbol table. And again, the cost of this is the number of compares is equal to 1 plus the depth of the node. We just go down a path in the tree. Now, what's interesting about binary search trees is that there are many different binary search trees that correspond to the same set of keys. So the number of compares is going to depend on the order in which the keys come in, and that's a key feature of binary search trees that we'll come back to again when we look at more sophisticated data structures. So it depends on how the keys come in. The shape of the tree could be, well, in the best case, it would be perfectly balanced. And one of the things we'll look at is algorithms that come very, very close to achieving that goal. A typical case, it'll be sort of balanced. Now, but one problem is if the keys come in and really unfortunately, if they come in a natural order, like if they come in order, that's the worst case. We don't get any benefit from having it in a tree shape. It's no different than a linked list. So we'll come back to dealing with that worst case in the next lecture. But the point is the tree shape depends on the order of insertion. Now, but let's look at what's happened or visualize what happens when keys come in random order. So the tree grows from the bottom, and the little side-to-side motion is just accommodating room for each new key as it's added. But you can see that even for this case, which is hundreds of keys, the length of the path from top to bottom is not so much. In this case, the maximum distance from the top to the bottom is 16. The average is only 9. And the best you could do in a perfectly balanced tree, it would be 7. So it's pretty well balanced, which means that our search and insert costs, in this case for 255 keys, is only going to be 16, quite a bit less. So one remark before we do the analysis is that actually binary search trees correspond exactly to quicksort partitioning. In the binary search tree, we have a node at the root, and we have everybody smaller to the left and everybody larger to the right. In quicksort partitioning, after the random shuffling, we have the partitioning element, and then we process everybody to the left independently of everybody to the right. So it's a there's a direct correspondence. If there's no duplicate keys, quicksort processes them, and we've ruled them out in BSDs. But if there's no duplicate keys, there's a one-to-one correspondence between what happens with quicksort and what happens with binary search trees. And we point that out because that helps with the mathematical analysis. In fact, this correspondence with quicksort partitioning tells us we can take that proof and prove that if you insert n distinct keys into a BST in random order, then the expected number of compares for a search and an insert is 2 natural log n. Again, about 1.38 log base 2 of n, almost the best that you could do. It also has been shown, actually not that long ago, that the expected height of the tree, if they're inserted in random order, the height, that's the worst case length of a path in the tree. This is the average path in a tree. This is the worst of all the keys, is about 4 natural log n. So if you have the keys in random order, the binary search tree gives efficient search and insert. But there is this problem that the actual worst case height, if the keys come in order and reverse order and other natural orders, that the time could be proportional to n. So we have this summary, which is looking pretty good because we have the average case for both operations, the search and insert, to be 1.39 log n. And that's probabilistic. If they're in random order, it's extremely likely to be there. But the problem by comparison with sorting is we don't get to randomize the order. The client is providing the keys. So we're going to need something better to provide the guarantee than just randomly ordering the keys. That's what we're going to be looking at next when we look at more efficient algorithms. But first, we're going to look at the implementation of ordered operations with the binary search tree structure. It expands, like binary search, to handle all these convenient client operations in a very natural manner. That's the implementation of binary search trees for symbol tables. It gives efficient implementation of both search and insert. Now we're going to take a look at ordered symbol table operations using the binary search tree data structure as the underlying implementation. Well, each one of these operations are fairly straightforward, but just to check our ability to manipulate this data structure, we'll take a look at each. Suppose we want to find the minimum key in a binary search tree, or the maximum key. Well, just looking at one example, you can see almost immediately what to do. To find the minimum, we move left from the root until we find a null key. That's where the smallest key in the data structure is. To find the maximum, we move right from the root until we find a null key. What about floor and ceiling? Well, those are a little bit more complicated, and we'll have to, not quite the same as in the ordered array for binary search. So we have to do a little bit more work for that. So just for example, let's take a look at the problem of computing the floor. So what we want to find is, so say we're seeking the floor of G. So that's the largest key in the data structure that is less than G. In this case, the answer is E. So let's just take a look at what we have to do in the tree, the path we have to take in the tree to figure that out. Well, so we're looking for the largest key that's less than G, and we have S. Well, that key is definitely going to be in the left subtree. It's not going to be bigger than S because S is bigger than G, so we go to the left. So now we're sitting at E, and so what's the largest key that's less than G in this tree here? Well, it might be E, but there's no way that it's to the left of E because those keys are all smaller than E and therefore smaller than G, so E's a candidate. But it might also be in the right. So we move to the right in this case. So that's if K is equal to the key at the root, the floor of K is K. If K is less than the key at root, it's in the left subtree. That's the one we just did. If it's greater than the key at the root, the floor of K is in the right subtree if there is any key smaller than K in the right subtree. So in this case, there's no key smaller than G in the right subtree, so therefore the answer is E. So our code has to check for these three cases. And here's the code that does it. It's not that much code, it's just complicated code to understand. So if we find our key, that's the floor. If we're going to the left, we find the floor of the one on the left. And in the right, we have to do a little bit of tricky code to make sure that we return the floor in the right subtree if there's some tree there. If there's no node there, then we return the root itself. So that's a implementation, but that code is definitely tricky. And there's similar code for ceiling. So now, what about operations like rank and select? How many keys are there less than a given key? And give us the seventh largest key. To facilitate implementing those operations and also size, all we do is keep an extra field in each node, which is the number of the nodes in the subtree rooted at that node. So this tree's got 8 nodes in it. This subtree has 6 nodes in it, and so forth. And those counts are going to not only enable us to immediately implement the size function, just return the count at the root, but they'll give us good implementations of rank and select. So let's look at those now. So we add a count field to every node. And then to implement the size function, well, if it's null, we return 0. So a client might call us for a null tree or an empty tree. Otherwise, we return x.count, which is the number of nodes in that subtree by definition. The way we maintain, there's a number of ways we could maintain the thing, but the one that we'll adopt uniformly because it adapts to more complicated situations is just before we're done with the put operation, we'll say, okay, we've done all our work, and before we return a pointer to the given subtree, we're going to take the size of what's on the left and the size of what's on the right and add 1 for us, and that's going to be our count. So whether or not there was a new node added, we don't have to test for that. This recursively takes care of the problem of maintaining the size in every node when there's a new node inserted. And it also handles more general situations, as we'll see later on. So that's how to maintain size. So now how do we implement rank? Well, it's a little like floor. It's an easy recursive algorithm, but there are three cases. Let's look at the three cases. So we want to know the number of keys less than k. We're going to have a recursive algorithm for our given key. One of the easy ones is if our key is equal to the key at the current node, then the number of keys less than our key is the size of the left subtree of that node. So if we're looking for the rank of E, say, how many keys are there less than E? There's exactly 2. That's by definition in the data structure. That's the number of keys that are less than E. So that's that one for rank. What about starting at the root? If we have the case where E is less than S, so the rank of E in this whole tree is the same as the rank of E in the left subtree. So that's that case. And then if we're going to the right, then we have to add 1 for the root and 1 for the left subtree of the root, and then find the rank of us in the right. So that's an easy recursive algorithm for finding out the rank, and it's definitely an instructive exercise to check that you believe that that method works. The other thing we have to do is iteration, and iteration is a fundamental operation on tree structure, and it's based on so-called in-order traversal. And that's also a simple recursive algorithm. Traverse the left subtree, NQ the key, traverse the right subtree. So to iterate, we're going to maintain a queue of keys, and then we're going to call this recursive in-order method, and that method is going to add all the keys in the tree to the queue, and then we'll just return that queue, and queue is an iterable data structure, and the client can iterate that. And in order is just a simple recursive method. Put everybody to the left on the queue, then put the root on the queue, then put everybody to the right on the queue. And to believe this method, you just have to think recursively and prove by induction that this in-order method puts all the keys in the data structure on the queue in their natural order. First, it puts all the ones to the left on the queue. If that happens in their natural order, then the next thing that has to appear is the key at the root. And then if the ones on the right go in their natural order, and then by induction, they're all in their natural order. That's a very simple implementation of an iterator for the symbol table with comparable keys. So you have to, again, prove that property by induction, and that's easy to do. And the diagram at the right gives another simple way to look at it pictorially. All the keys that are smaller on the left, we're going to put them out, and then we put the key at the root, and then we put all the keys on the right out in order, and then that key is going to have all those keys in order by induction. So here's the operation summary for ordered symbol table. The quick summary is that every one of those operations, well, ordered iteration is optimal. It just gets them in linear time. And all the rest of them take time proportional to the height of the tree. Now, if the keys are inserted in random order, we know that height by analysis is going to be proportional to log n. Or if it's some application where the order of insertion of the keys is well modeled by random order, and that's not unusual at all. Binary search tree is a simple and extremely effective data structure that can support all of these operations quickly, much better than binary search in an ordered array, which is not dynamic and slow for insertion. So that's a look at binary search tree implementations of ordered operations when keys are comparable. If our symbol table is really going to be dynamic, we need to be able to delete key value pairs from the table. As we'll see, all symbol table implementations lead to complications when we try to do this operation. Binary search trees is our first example. So we need to fill in this one table. What's the cost of deletion in a binary search tree? How are we going to really do that? Well, let's take a look at a very lazy approach, which we set up for in our basic conventions for symbol tables. What we can do to remove a node with a given key is just mark it with a tombstone. Say, well, we'll leave the key in the tree to guide searches, but we won't count it as being in the symbol table. And actually, you can make some progress with this kind of method, leaving tombstones throughout the tree, and make sure that you keep, as long as there aren't too many deletions, you can keep the search cost and deletion and insert cost to be logarithmic. But it definitely becomes inconvenient to manage large numbers of tombstones in highly dynamic situations with large numbers of keys and values. Eventually, you're going to get an overload of memory, and you're going to have to rebuild the thing or clean out the tombstones in some way. So we need to look for a better way. This is a general method that people often use in all different types of implementations, but in modern systems it's rather unsatisfactory. Well, let's look at a simpler problem. What about deleting the minimum? Actually, that's maybe not too difficult. To delete the minimum in a binary search tree, again, we just go to the left until we get a null left link. And then what we can do is just return that node's right link. Then that old node, nobody's pointing to it, so it's available for garbage collection. And then we use our usual trick of returning the link that we went down to update the other links after the recursive calls. And also, we have to update the counts. Something happened down below, and we use that code to update the counts in a consistent way. So this code implements delete min. Not too bad at all. If x.left equals null, return x right. Otherwise, x left equals delete min x left. And then when you're done with that, you fix the count. So maybe a node got deleted down there, but always the invariant is that the count of the node is 1 plus the size of the left and right, and then return x and fix the links and the counts on the way up. That's a fine implementation for delete min, and it also works for delete max. And that's the basis for a general method for deleting nodes from BSTs known as Hibbard deletion. So that's the second case. The first case for Hibbard deletion is what we want to do to delete a node with key k is we search for the node that contains the key. And the easiest case is that node has no children. So to delete a node that has no children, just return null. And then go back up to update the counts as usual. That's the easy case. The next most difficult case is like the delete min case. We find a node T that contains our key, so like deleting R in this tree. It only has one child. Just go ahead and return the link to that child, and that updates the link and everything works fine. Then the node that was deleted is available for garbage collection because nobody's pointing to it. And again, update all the counts after the recursive calls. So 0 children, no problem. 1 child, no problem. The problem is what happens when there's 2 children. So say we want to delete node E in this tree. We have only one link. We can get rid of the node, but we have only one link pointing to it, but we have 2 links pointing down from it. So what are we going to do with those 2 links? Well, the Hibbard deletion mechanism, which is pretty old, 50 years ago it was proposed, says go ahead and find the next smallest node in the right subtree of that tree. So in this case, that's H. And what's that node? Well, it's the minimum in T's right subtree. And we know how to delete the minimum, so we just find that minimum node, and in this case it's H, and we put that node in T spot and then delete the minimum. So find the H, that's the minimum, hang on to it, and then delete the minimum in T subtree, and then so we take the E, replace it with the H, and delete the H, and then everything's fine. It's still a BST. So we're finding a node that has only one link, and deleting that node, and then replacing the node that we need to delete with that one. That's Hibberd deletion. It's a little bit asymmetric. Why are we using the successor and not the predecessor? No real reason. And it's not really satisfactory because of that, and we'll come back to this, but it works. So this is the code for Hibberd deletion. So we search for the key. If it's got no right child, we're fine. We just return x.left, and that handles both cases 0 and 1. If it does have a right child, then we do this find the minimum on the right, delete min on the right, and then fix the links, and then update our count that covers all cases. So actually not that much code. It's complicated, but not particularly more complicated than other code we've seen, like rank and floor and ceiling, and that implements Hibberd deletion. So now we have a fully dynamic symbol table where we can insert and delete. The number of nodes that we have in the tree is always proportional to the number of key value pairs in the symbol table. And the problem is, and this was quite a surprise when it was first discovered, actually many years after Hibberd proposed the algorithm, is this lack of symmetry tends to lead to difficulties. And here we're just inserting, deleting, alternating, insert and delete a random key. So that maybe well models a situation, a practical situation. And as you watch it go for a while, you can see that this thing about going to the right and taking the successor all the time, the tree's becoming much less balanced than it was. And this seems to be a problem. We can't be supposedly having a dynamic situation that is going to allow support of lots of different inserts and deletes, and in the end wind up with a less balanced tree. What's worse, so how are we going to fix it? So in the end, researchers showed that after sufficiently long sequence of random inserts and deletes, the height of the tree becomes square root of n, not log n. Square root of n is hugely bigger than log n. It might make the difference between acceptable and unacceptable performance in real applications. And what's worse, if you try to fix it by, say, randomly choosing between the left and the right, that doesn't work. It still becomes square root of n. And it's a very long-standing open problem to find a natural, simple, efficient delete for binary search trees. That's another one like merging in place that you'd think there ought to be an easy way to do it, but in 50 years, no one's really discovered one. We're going to look at something pretty close in the next lecture, but here's the situation that we're left with. We have a binary search tree algorithm which is fine in that it gives us log n performance for search and insert in a situation where we can think that these things are happening randomly. But we're kind of stuck if we allow delete. In fact, everything degenerates to square root of n. And we also have the problem with the worst case. If the keys happen to have some order in them, our trees are not going to be balanced at all. And that's going to make the difference between acceptable and not acceptable performance. What we're going to look at next time, called a red-black binary search tree, will guarantee logarithmic performance for all operations. That's extremely significant and much better than binary search trees. But the delete operation for binary search trees shows us the kind of complexity that we can encounter with working with these kinds of data structures. Welcome back. Today we're going to talk about balanced search trees, which will lead us to an ultimate symbol table implementation that can provide fast performance for all the symbol table operations we've looked at, guaranteed. So here's a review of where we were with symbol tables. We took a look at the last time at the binary search tree, which if things are well modeled by random insertions have great performance. They get search and insert done in time proportional to log base 2 of n, and they support ordered operations. But really, our goal is to have these operations be guaranteed to take time proportional to log n, because we don't have control over the order of operations, and they may not be random at all. And in fact, in many real applications, they're not very random. So that's what we're going to look at now, is try to find an implementation that can guarantee to be fast for all the symbol table operations. That's our challenge. So what we're going to talk about to do it is a algorithm that actually a pretty old algorithm called 2-3 trees in a particular implementation that requires very little code called left-leaning red-black BSDs. And then we'll talk about a generalization called B trees. And these methods are all widely used throughout our computational infrastructure. To start, we'll talk about 2-3 search trees, which is a model that underlies the concise and efficient implementation that we're going to look at. So a 2-3 tree is a way to generalize BSTs to provide the flexibility that we need to guarantee fast performance. And the idea is very simple. We allow 1 or 2 keys per node. That is, we allow for the possibility of something called a 3 node that can hold 2 keys, but then it has to have 3 children. In a regular BST node, a 2 node, we have 1 link for the keys that are less than the key in the node, and 1 link for the keys that are greater. In a 3 node, we need 3 links, 1 for less, 1 for between, and 1 for greater. Another property of these 2-3 trees is that we're going to have perfect balance. That is, every path from the root to a null link is going to have the same length in a 2-3 tree. So as I mentioned, the symmetric order is part of the definition of a 2-3 tree. Every 3 node has 3 links and 2 keys. The left link is for the keys that points to a 2-3 tree with the keys that are smaller than the smaller of the 2 keys in the 3 node. The middle link points to a 2-3 tree that contains all the keys that are between the 2 keys. And the right link points to a 2-3 tree containing all the keys that are larger than the larger of the 2 keys in the 3 node. Okay, let's take a look at a demo of searching in a 2-3 tree. So say we have this 2-3 tree here, and we want to search for whether or not H is one of the keys in the tree. So we start at the root, compare the search key against the key or keys in the node, and follow the link corresponding to the interval that we know must contain the search key by the definition of the tree. And then we recursively continue the search. So if we're looking for H, it's less than M, so the only place it could be in this 2-3 tree is in the 2-3 tree on the left link, so we follow the left link. Now we compare H with E and J, and in this case it's between, so now we're going to take the middle link. That's the only place that H possibly could be. And in this case, that node, one node 2-3 tree contains H, so that's a search hit. Let's take another example for unsuccessful search, a key that's not in the tree. As usual, we start at the root. It's less, so we go left. It's less than both keys, so if it's in the tree, it would have to be on the left link. And it's between those 2 keys, so if it's in the tree, it would have to be on the middle link. And that link is null, so that's a search miss. So the search is a natural generalization of the search in binary search trees. Now what about inserting? Well, it's a similar type of strategy as with regular binary search trees, except that we manipulate the 2 and 3 nodes to keep perfect balance in the tree. So the easy case is if the key winds up in a 2 node at the bottom, like this one. Suppose we're inserting K. K is less than M, so we go left. K is greater than both keys, so we go right. K is less than L, so the search ends at the left link of L. And to perform an insertion, all we need to do is replace that 2 node with the 3 node containing K. Now K is inserted into the 2-3 tree and it satisfies all the rules. Now if we're inserting into a 3 node at the bottom, we have to do more work. And specifically, the work we do is we add the key to a 3 node to create a temporary 4 node and then split up that 4 node and move its middle key into the parent. So let's see an example. If we're going to insert Z into this tree, it's greater than M, so we go to the right. It's greater than R, so we go to the right. Now it's greater than X, and that's a null link to the right of X, so the search ends there, and what we'd want to do is insert Z into that 3 node. And the way we do it is first make a temporary 4 node that replaces that 3 node. And then that's not a 2-3 tree because it's got that one 4 node with 3 keys and 4 links. But what we can do is split that 4 node and pass the middle key up to its parent. So split it into 2 nodes and pass the middle key to the parent. That's kind of a magical operation, and believe me, it's easier to get it done in the implementation than the graphics. But now you can see that that local transformation on the 2-3 tree completes the insertion. Now, if that parent were a 3 node, it would become a temporary 4 node and would continue the process moving up the tree. That's a demo of search and insertion in a 2-3 tree. So let's look at a double split like that. So say we're inserting L into this tree. So it goes down to the middle and winds up needing to be inserted in the 3 node in the middle. So we're going to convert that into a 4 node. Now L's the middle key of that one, so we're going to split that 4 node into 2 nodes and move L to the parent. The 4 node had 4 links, and the 2 nodes have 4 links, so nothing has to be changed below. And then this insertion into the parent changed it from a 3 node into a 4 node, essentially adding a link because of the split with the 2 nodes, where there was only one 3 node before. But now that's not a 2-3 tree, so we have to split again. And in this case, there's no parent, so we create a new one, and the height of the tree increases by 1. That's the only time the height of a 2-3 tree changes. When the root splits, the height increases by 1. So that's a demo of insertion into a 3 node at the bottom in a 2-3 tree that percolates all the way to the top. Now let's look at constructing a 2-3 tree from an initially empty tree. So if we start by just inserting a key, well, that just creates a 2 node containing that key. And that's a legal 2-3 tree, so we're fine. Now inserting E into that, well, it's going to be, if it's in the tree left of S, that's a null link, so we need to convert that 2 node into a 3 node. Okay, and that's the legal 2-3 tree, so we stop. Inserting A into that, we convert that 3 node into a temporary 4 node, but then we need to split that 4 node, moving E to the parent, and that creates a new root node and increases the size of the tree by 1, but now that's a legal 2-3 tree, so we stop. Insert R into that, it goes to the right of E, convert into a 3 node. Now insert C into that, goes to the left of E, has to be joined with A into a new 3 node. Again, that's a legal 2-3 tree, and we stop. Now we insert H, that goes to the right of E, that 3 node gets converted into a 4 node. That's a temporary 4 node, we split and move R to the parent. Now that parent's a legal 3 node, and there's nothing more to be done. We have a legal 2-3 tree. Insert X, it's bigger than R, goes to the right. There's a 2 node, there's room for the X. Insert P, That goes between E and R, the 2-node containing H. Right link is null, so we convert that 2-node into a 3-node. And now we have a legal 2-3 tree. Now you can see this next insertion is going to cause some splitting, wherever it is. So insert L, that's between E and R, so it goes in the 3-node containing H and P. We convert that into a temporary 4-node, split that 4-node, moving L to the parent. Now that parent's a 4-node, and that has to be split, and we create a new root node, and then the height of the tree grows by 1. And that's a legal 2-3 tree, so we stop. So those local transformations, converting a 2-node to a 3-node, or converting a 3 to a 4, and then splitting and passing a node up, those are the only operations we need to consider to get balance in our search trees. All right, so as I've mentioned, and this diagram shows, the splitting a 4-node in a 2-3 tree is a local transformation. It only involves changing a constant number of links. So in this example shows the general situation when the 4-node to be split is the middle link, but the same is true if it's a left or right. And those 6 subtrees drawn could be huge. They could contain millions of keys. But it doesn't matter what they contain. We don't touch them at all, nor do we touch anything above this node in the tree until a split happens. So the transformation that splits that BCD node and inserts the C into the 3-node at the root just involves making that 3-node into a temporary 4-node and making that 4-node into 2 2-nodes and adjusting the links appropriately. Just a constant number of operations, and that's why this operation is in general efficient. So let's look at just the global properties that these manipulations preserve. The 2 things that are critical is that in a 2-3 tree we always have symmetric order. That is the order that we defined for 2 nodes and 3 nodes. And we also have perfect balance. The distance from the root to the bottom is always the same. And to prove that, we just need to show that each transformation maintains symmetric order and perfect balance. And these are all the possible transformations that we could do. If we split the root, then that's what happens at the root. And if there was perfect balance before, there's perfect balance after with the height 1 bigger. If the parent was a 2-node, then the transformation is a local transformation. And if you look at where the links are, then it's easy to see by induction that if there was perfect balance before, there's perfect balance afterward, because we didn't change anything about the perfect balance in any of those subtrees. And that's true in every case. If the 3 nodes at the right, then this one is 1 higher and those 4 are 1 lower, and afterwards it's the same. If there was perfect balance before, there's perfect balance afterwards, because we didn't change the height of any nodes. We just moved things around locally within nodes. And this is when the parent is a 3-node, then there's the 3 cases. If we split at the left, split at the middle, and split at the right. And again, changing the 4-node to 2 nodes and adding links. If there was perfect balance before, there's perfect balance after, because we didn't change the heights of anything else in the tree. So our operations maintain symmetric order and perfect balance in a 2-3 tree. So that's going to give us a very easy way to describe the performance. All our operations have cost that's proportional to the path length from the height to the bottom, and every path from the root to a null link has the same length. How long can those paths be? Well, it's not hard to see that in the worst case, if they're all 2 nodes, that's the longest they could be. It's log base 2 of n. And if they're all 3 nodes, it would be log base 3 of n, which is less. It's about 0.63 log base 2 of n. So all the paths in a 2-3 tree with n nodes have to have length between those 2 bounds. And those are pretty small numbers. For 1 million nodes, that's between 12 and 20. And if it's 1 billion nodes, that's between 18 and 30. Those are remarkably small numbers. So we're going to have guaranteed performance, even for huge databases. We're going to be able to guarantee that we can get search and insert done with just 18 to 30 operations. That's quite remarkable, really. So here's what our table will look like when we finish the implementation of 2-3 trees. Every operation is guaranteed to be a constant times log n. Now the constant depends on the implementation, exactly what kind of manipulations we need to do to convert 3 nodes to 4 nodes and so forth. But it's easy to see from the demos and the diagrams that those are going to be constant. Guaranteed logarithmic performance for all operations, which is certainly what we want in a symbol table implementation. Now, what about the implementation? Well, we're actually not going to talk about a direct implementation of 2-3 trees because it's kind of complicated. It's cumbersome to maintain multiple node types. You might need multiple compares to move down the tree. If there's a 3 node, it takes more compares than a 2 node, so it's complicated to analyze. We have to keep track of links as we go up and down the tree to handle the splitting, and there's a lot of cases. I drew all the cases, and there's whether you're splitting into the middle of a 4 node or the right of a 2 node, there's just a lot of cases. So you could do it, but we're not going to because there's a much easier way. So that's 2-3 trees, a model for implementing balanced trees and guaranteed logarithmic time. Now we'll look at red-black BSTs, which is a simple data structure that allows us to implement 2-3 trees with very little extra code beyond the basic binary search tree code. So this is, and actually the version that we're looking at is called left-leaning red-black BSTs. On a personal note, I wrote a research paper on this topic in 1979 with Leo Gibas, and we thought we pretty well understood these data structures at that time. And people around the world use them in implementing various different systems. But just a few years ago, for this course, I found a much simpler implementation of red-black trees. And this is just a case study showing that there are simple algorithms still out there waiting to be discovered, and this is one of them that we're going to talk about. So the idea is that we are going to represent every 2-3 tree as a binary search tree. And in order to get that done, we just need a simple representation for 3 nodes. So what we're going to do is use internal left-leaning links to glue the 3 nodes together. So the larger of the 2 nodes in the 3 node will always be the root of a little binary search tree of size 2 for the 3 node. And the link between the 2 nodes, the left link that links the larger key to the smaller one, we'll color red, and that's to distinguish those links from the other links in the binary tree so that we can tell when we're inserting things which nodes belong to 3 nodes and which ones don't. And you can see from this transformation that it's easy to perform this, see this correspondence. The middle link between A and B, those are the keys that are less than B and larger than A. So that takes 2 comparisons to get to them. The ones that are less than A, less than B, less than A, that's 2 comparisons for that. And the ones that are greater than B are the right link of B. So just following those 3 cases, see that this correspondence is going to work. So any 2-3 tree corresponds to a left-leaning red-black BST in this way. Just take the 3 nodes and split them into little binary search trees of size 2 held together by a red link. And correspondingly, given a red-black BST, then you can get the 2-3 tree if you wanted it. But just look at the properties of, looking at the properties of a left-leaning red-black BST. with reference to what we know about 2-3 trees. First of all, no node has 2 red links connected to it, because the only red links are internal to 3 nodes, and those have to have external links or tree links connecting them to some other node. Every path from the root down to a null link has the same number of black links. That just follows directly from the corresponding property for 2-3 trees. A left-leaning red-black BST has perfect black balance. And all the red links lean left. So given a BST with some of the links colored red that has those properties, that's going to correspond to a 2-3 tree. And that's a key property, is this one-to-one correspondence between 2-3 trees and left-leaning red-black trees. Given a 2-3 tree, we saw how to do it. Given a red-black tree, we just make the red links horizontal and merge the nodes together to be 3 nodes. So all of the operations that we're going to look at for red-black trees can be understood in terms of the corresponding operations on 2-3 trees. Now, the first and really one of the most critical observations is that search in a red-black BST is exactly the same as for an elementary BST. We just ignore the color. Now, it's going to be much faster because of better balance in the tree, but in terms of the code, we don't have to change the code at all. Our regular search code doesn't examine the color of a link, and so we can just use it exactly as is. And in fact, most of the other operations that we implemented on BSTs are also identical. They don't need the colors, but they can all benefit from the fact that the trees are much better balanced. So this aspect of red-black BSTs is an extremely nice one, because the operations that we implemented for regular BSTs involve some complicated code for floor and ceiling and rank and so forth, and we don't have to change that code at all. We just, during the insertion, make sure that we maintain the properties, the balance properties, and by doing that, we wind up with balanced trees, and we make all the operations quick, and we don't have to re-implement, we don't have to change them at all. So first, before we get to the code for insertion, we have to look at the representation. We didn't actually have explicit representation of links. Our links in trees are just references to nodes. You could implement this by building explicit links, but an easier thing to do is to notice that every node is referenced by just one link in a tree, the one from its parents. So you can put the color of a link in the node that it references. So in this case, we have a red link connecting E and C. What we do is put a color bit in each in the node class, and then if the link coming into a node is red, we set that to true. So this simple thing just tests, is a node red? We consider all null nodes to be black, null links to be black. We don't have red links dangling off. That'd be incomplete 3 nodes. Otherwise, if the color is red, we return true. Otherwise, return false to test whether a node's red. So in this tree, the color of h.left is red, the color of h.right is black, and so forth. So that's the way we represent colors, by putting a color bit in the node for the color of the link that points to it. All right, so now there's a couple of elementary operations that we have to perform on red-black trees called rotations. And the idea is that during the construction of a tree, or during an insertion operation, sometimes we wind up with red links that are leaning in the wrong direction. So we'll need what's called a left rotation. And the job of that operation is to take a right-leaning red link that is there for whatever reason and reorient it to lean to the left. So in this case, we have the right link of E points to S, and S is red, so that's a right-leaning red link. And so that's the before, and what we want to do is reorient things so that it leans to the left. And again, that has to be a local operation that only changes a few links. And just from the diagram, it's not difficult to see that this little bit of code will do the job. If we start with a right-leaning red link, so first thing we do is take the reference of h.right and save that in X. So that's the node that's going to be the new root of the three nodes, so to speak. And then x.left after the rotation is going to be h. And also whatever color h was, well, it looks like it should be black, but actually there's situations where it could be red. Then x is going to have that color because the link coming into h is going to be the link coming into x. And then h's color is going to be black afterwards. And then we return x to link further up the tree, which happens during our standard recursive insert. So that's a rotate left operation. Now the property of this operation that's very important is it maintains a symmetric order. The keys between E and S are still there. We just change the way we get to them, and the keys less than E and so forth. And also we maintain perfect black balance because we didn't change the black height of anything by doing this transformation. All those subtrees, those three subtrees are exactly the same relative to the top and bottom of the tree as they were before the rotation. Now, paradoxically, and you'll see why very soon, it also turns out that to get the insertion done properly, we sometimes need to take a left-leaning red link and temporarily make it lean right. Later on, we'll get it back to the left again, but anyway, that's a basic operation that we sometimes need. And so that's just the symmetric code to the code that we just did. Now x is h.left, and h.left is going to be x.right after the rotation. X's color is still going to be h's color, and h's color is going to be red. And the right rotation implements this. And again, that's going to maintain symmetric order and perfect black balance. We changed the way the red goes, but we didn't change anything about the black. Okay, that's a right rotation. Now here's the third elementary operation that we're going to perform. It's called a color flip. Sometimes during the insertion, we might wind up with a node that's got two red links coming out of it. That corresponds precisely to our temporary 4 node when we're doing 2-3 trees. And what we wanted to do with the temporary 4 node was to split it and pass the center node up to the root. Well, you can see from this structure that we're all set to do that. All we need to do actually is not change any links, just change all the colors. And so that is, we change the link from E to A and from E to S to be black. That essentially splits the 4 node. And then we want to insert the E into its parent, and we just do that by changing its link to be red. So that's flipping the colors, and that's the way we split a temporary 4 node in a left-leaning red-black tree. And again, that's just flipping colors, doesn't change any links, so it still, of course, maintains symmetric order and perfect black balance. So those are the 3 basic operations we're going to use: rotate left, rotate right, and flip colors. So the basic strategy is, with those operations, maintain one-to-one correspondence with 2-3 trees when we do insertions. So here's an example. If we want to insert C into this red-black tree, which is a representation of this 2-3 tree, then C is going to be less than E, greater than A, so it'll get added as the right link of A. And every time we add a node, we just create a red link to its parents, and so that's changing the 2-node into a 3-node. In this case, it's a 3-node that's oriented the wrong way, so we need to do a left rotate. After we do the left rotate, we have a legal left-leaning red-black tree, and it exactly corresponds to that 2-3 tree. So the insertion of C gives us exactly what we'd want, the correspondence with the 2-3 tree. And we have to work through other cases that can arise, but there's not too many, so we'll work through them. And we have the basic operations: left rotate, right rotate, and flip colors. All right, so first to warm up, insert into a tree with exactly 1 node. Well, if it goes on the left, then we just make a red link and add it on, and we're done. If it goes on the right, then we attach a new node with a red link on the right, but we have to rotate it to the left to make a legal 3-node. So that's insert into a tree with 1 node and make it a tree with 2 nodes. And that one generalizes to help us insert into a 2-node at the bottom. So we do the standard VST insert, color the new link red, and then if that new 3-node happens to lean right, rotate it to the left. That's the case that we just did. So now let's look at a second warm-up. So say we have just 2 nodes in the tree, so we have 2 nodes, and that means it's a single 3-node. Then there's 3 cases. So one is that the new one is larger than both of the keys. If that's true, then we attach the new node with a red link as always, and that gives us a temporary 4-node. And what we want to do is split that 4-node, and in this case, since we're at the root, that's all, so that just flips the colors. Now the color of the root in our code would temporarily turn red and then would turn it black again. So that's inserting into a tree that's a single 3-node, a node that's larger than both of them, a key that's larger than both of them, and we wind up with a 4-node. But let's look at the other 2 cases, and understanding these is crucial to understanding the whole algorithm. Let's say the new key is smaller than both of the keys in our 3-node. Well, we attach a new link at the left of the smaller node, and now we've got to find BST, but it has 2 red links in a row. And that's something that's not allowed. So what we're going to do is we're going to rotate the top link to the right. So that puts B at the root, and now it's got 2 red children. It reduces it to this case, and we flip the colors, and we have a single 4-node, a red-black tree that's got 3 2-nodes and no red links. Same situation as before. So we had a single temporary 4-node, and we split it up into 2 2-nodes connected to a 2-node. And then, so that's the case when it's smaller. Now we have to look at the third case, which is when it's the new node is inserted as in between, and comes out at this link here. Again, we just add a red link, and now we have a BST with 2 red links along a path connected to A, and that's not allowed. In this case, it's a bit trickier to fix the situation. What we do is we rotate the bottom link left. And that gives us this, and reduce it to the other situation that we had before. And then we rotate the top link right, and then we flip the colors. So this one we use all 3 of our operations: rotate left, rotate right, and flip the colors. And that gets us an insertion into a tree that has, from a tree that is a single 3-node to a tree that is 3 2-nodes containing 3 keys. So that sort of operation is going to work in a big tree when we insert into a new 3-node at the bottom. We do the standard BST insert, color the new link red, Then we do the rotations that we need, either 1 or 2 rotations to balance the temporary 4 node, and then we flip colors to pass the red link up 1 level, and then we might need to rotate to that to make that one lean left. So for example, if we insert H into this tree here, it comes off as the left link of R. So that gives us a temporary 4 node that's not balanced. So we need to rotate the link from S to the right. And that gives us now a temporary 4 node that is balanced. And again, these are all local transformations. It's not changing the rest of the tree. Now we flip colors, and that gives us a good red-black tree, except that that one red link that we just made is leaning the wrong way. So now we need to rotate left. And then once we've done that, now we have a legal left-leaning red-black tree. So that's a insertion into a 3 node at the bottom. So here's another one that involves, remember we passed that red link up. If that gets passed up to a 3 node, then we have to continue moving up the tree and just treat it in the same way as we just treated inserting at the bottom. We have a new red link appearing into some 3 node. There's the 3 cases that could happen. And here's an example. So say we're inserting P into this left-leaning red-black tree. It goes to the right of M, so we get a temporary 4 node that's got 2 red links. Both children are red in that thing, so we want to flip the colors. We flip the colors, and now our temporary 4 node is up higher in the tree, but it's not balanced, so we're going to have to do 2 rotations to make that balanced. First one is to make the bottom link left-leaning, and then the second one is to make the top link right-leaning so that we can have the temporary 4 node balanced. And then the last thing we do is flip the colors, and now that's the result of that insertion. It's a bunch of transformations, but they're all simple using our flip colors or left or right rotation. And that one happened to be at the root. If that red link were way down in the tree and there were another 3 node above it, we might have to do it again. Again, exactly as would happen in a 2-3 tree. So let's do a demo of constructing the red-black BST from our standard set of keys. So we start with a single key, and now if we want to insert E, it goes to the left, that's fine. That's a legal left-leaning red-black tree. A would go to the left of E, 2 lefts in a row, so we have to rotate S right, and then we have to flip the colors. And that's a legal red-black BST. So now if we insert R into this one, then it goes on a red link to the left of S, and that's fine, it's a red-black BST. And now if we insert C into this one, it goes less than E, greater than A. It's a red link connecting A and C, but it's leaning the wrong way, so we have to do a left rotation. Legal red-black BST. We want to insert H, that goes to the left of R, 2 reds in a row, rotate the top. Rotate the top, our temporary 4 node is balanced, flip colors. Now we have a 3 node, but the red link is leaning right, so we have to rotate. And then now we have a legal red-black BST. Insert X into that one, it goes to the right of S, that's leaning the wrong way, rotate left. Insert M into this one, it goes to the right of H, leaning the wrong way, rotate left. Most of the operations are simple ones like this happening at the bottom. Insert P, that goes to the right of M, that makes M a temporary 4 node that happens to be balanced, so flip the colors. Flip the colors, now we have a temporary 4 node that's out of balance, so we need a double rotation. First rotate E to make that link point lean to the left, then rotate R to bring the temporary 4 node into balance, and then flip the colors. And that's a legal red-black BST. Insert L into that one, goes to the right of H, leaning the wrong way, rotate left. And that's an example of building a red-black BST from our standard set of keys. Now we're ready to look at the implementation of the code for inserting into a left-leaning red-black tree. And the key to understanding this code is to realize that the same code handles all of the cases. The way that it works is we're always reducing one case to another. We get this most complicated case. We did a left rotate on the bottom node, and that transformed it to this case where they're both leaning left. And then we did a right rotate on the top node, and that transformed to the case where our temporary 4 node is balanced, and then we flip colors on that. So for a particular insertion, we can take advantage of this reduce one case to another in the way that we're moving in the tree to get everything happen with just a few extra lines of code in our standard binary search tree. So in gray is our standard insertion code for binary search trees. Remember, we took some pains to think about the recursive implementation where when we go down a link, we replace that link by whatever the recursive routine gives us back. And that strategy is going to pay off in giving us really simple code. Because in this implementation for left-leaning red-black trees, we're going to return the link whenever we're done, and then that'll get that link installed up in the node above, whether it be left or right. Typical implementations of red-black trees that do not use this recursive strategy wind up having lots of cases depending on whether left or right, or double rotate to the left or double rotate to the right. I can be critical of this code because my own code was this way for the first 3 editions of the book. It's only in this edition that we figured out how to make the code this simple. Okay, so what are the things that have to be done? Let's just check. When we insert a new node, all we want to do is create a new node with the associating the given value with the given key as before, but now we just make that node red. So that's adding a new node with a red link at the bottom, inserting that into whatever 2 or 3 node it's attached to. And then we do the comparisons as before, and that's all fine. Now, when it's returned, then that's the point at which we're going to check whether the links are leaning to the left as they're supposed to, and whether or not there are any double links or not. So the first thing is if is red h dot right and not is red h dot left. So that means h is h dot right is red. So that means that the right link of h is leaning the wrong way. H is a 3 node leaning the wrong way. So we just rotate left h. So whenever we find a right link, we're sitting on a right red link, we just rotate it left and return that. So that would be, in this case here, we'd rotate it left and reduce it to that one. Or in the case when we're just inserting a new node and it turns out to be the right red link attached to a black one. So that handles that case. Now, if h dot left is red and h dot left is also red, that's this case here, where we have 2 left-leaning red links. And then in that case, we just rotate the top one right, and that brings us to this one. So notice, so we're in this case, we do this rotation first. We're on this node. And then that returns and we come up to deal with the situation on this node after the return, and then we do that rotation. And then after that rotation, or if there were no rotations at all, if the insertion happened over here, then we test and flip the colors. It's a little mind-bending at first because of the recursive structure, but it won't take you long to convince yourself that this little bit of extra code completes the implementation of left-leaning red-black trees. It's quite remarkable, actually. So let's look at a visualization. This is a balanced tree getting constructed in the worst case, where everything that comes in is in ascending order. A regular binary search tree would just be all strung out in a single line and would have quadratic time for this input. But a left-leaning red-black tree actually, whenever it becomes a power of 2, is completely balanced, as you can see from this example. Even though they came in ascending order, the tree winds up being perfectly balanced. And what about descending order? Well, it's left-leaning, and the process is a little bit different. And sometimes the left path can get long, but not that long. The worst that can happen is that it alternates red and black. And then after it gets to that worst case, it also winds up being completely balanced when we have a power of 2. Interesting to think just about this case and to prove to yourself that it's always going to be perfectly balanced when it's descending. This is just for random insertions. The tree stays very balanced. It's guaranteed that the longest path, which is alternating red and black, can be no more than twice as long as the shortest path, which is all blacks. And so in this case, the longest path is 10, and the average path is 7 for 255, very close to log base 2 of n. Easy to prove by correspondence with 2-3 trees that the height is guaranteed to be less than 2 log base 2n. Every search in a left-leaning red-black tree is guaranteed to take less than 2 log base 2 of n. Because every path's got the same number of black links, so you never have 2 red links in a row. And actually, in typical applications with any kind of randomness, or even if there's a lot of order, it's difficult to find situations, orders of keys that build trees that height is bigger than actually 1 log n. In real applications, it's very close to fully balanced all the time. So that completes our summary for symbol table implementations. With red-black BSTs, we have full code. It's the regular BST code with a couple of lines adding the calls on the basic operations to rotate right, rotate left, and color flip, and we get guaranteed logarithmic performance. Not just for search, insert, and delete. Well, delete code is a bit more complicated, but it's on the book site and in the book. But also, since it's the compare to interface, and since it's a binary tree representation, all the other comparable operations, extended operations for ordered symbol tables are going to be implemented and take time proportional to log in. A lot of people ask, why did we use the name red-black? We invented this data structure, this way of looking at balanced trees at Xerox PARC, which was the home of the personal computer and many other innovations that we live with today in turning graphic user interface and Ethernet and object-oriented programming and many other things. But one of the things that was invented there was laser printing. And we were very excited to have nearby a color laser printer that could print things out in color. And out of the colors, the red looked the best. So that's why we picked the color red, to distinguish red links, the types of links in 3 nodes. So that's an answer to the question for people that have been asking. Now here's another war story about red-black BSTs. As I mentioned, they're widely used, and there was an example not that long ago where a telephone company contracted with a database provider to build a database that could store customer information. And the provider implemented the database using red-black BSTs for search and insert. Now, our original paper on red-black trees was the way the paper was laid out. It turned out that the delete implementation happened to be placed after all the references, so a lot of people didn't see the delete implementation. And also, we didn't have the simple left-leaning representation, so it was more complicated and involved a lot more cases, and so usually not all the cases were put in the textbooks. So people found deletion more difficult. In fact, that's what led me to analyze the situation and come up with the left-leaning variant. So what they did in this implementation was they just put in regular Hibberd deletion in the binary search in the red-black BST, not the deletion algorithm that's guaranteed to keep the constant black height all the time. And so but they still thought that it should be balanced and it shouldn't matter much. And they had a complex error recovery process that got triggered if the height limit got too big. And they would rebuild the whole tree, and then because of the way they did this deletion, well, the end of the story was that they had extended, the client had extended outage because the implementer didn't use the full algorithm. And there was a lawsuit and some legal testimony. And happy to report that it was clear that Hibberd deletion was the problem once the expert analyzed it. And the expert witness, who's a colleague of mine, said if implemented properly, the height of a red-black BST with n keys is at most 2 log n. So that's the story of red-black BSTs, guaranteed logarithmic performance for all symbol table operations. Okay, we're going to finish up by talking about some practical applications of red-black trees, and in particular B trees, which are a general version. So the idea behind B trees is that often the data that we're trying to store is really huge. There's a large amount of data, and we're going to look at a more general model for external storage, where we work with contiguous blocks of data that are big, maybe 4K or bigger, or maybe even a whole file. And all we want to count is the first time we access a page, because the main cost is trying to find where the page is. Once it's read in, we get to read all the page for free, pretty much. So the real property of external storage, that not your local memory, is that the time required to get to a page is way larger than the time to access data within a page. So what we want to do is try to access data that's out externally using a minimum number of probes. That's a model of a file system that is pretty workable. And so B trees are a generalization of balanced trees that allow for this. The idea is to allow not just 2 or 3 keys per node, but a large number, like the number that can fit in a page. So might be m equals 1,000, or m equals 4,000. And well, we've got to have at least 2 keys at the root. And the only other restriction is that we don't want the nodes to get too empty. So we can have less than m, but we want to have at least m over 2. And as you'll see, this is a generalization of 2-3 trees that allows us to build balanced trees that are very, very shallow. Typically, these are set up so that all the data is in the external nodes. And so the external nodes have no links, they just have keys. And they're kept in sorted order. So for example, this is this is m equals 6, this is an external 5 node. So it's got 5 keys, it's got room for one more temporary one. And then what'll happen is when you insert into a full node, it'll split in the same as before, and then we'll pass the split up, causing a split up higher. So the red keys in the internal nodes are copies of keys down below that direct the search. And that's a little extra detail that just makes the implementation a little bit easier, and that's the way that it's usually done. But for now, the main idea is that it's like a 2-3 tree, except that we allow way more keys per node. And then when a node gets filled, it splits into 2, so a node's always between half full and full. So m is 1,000, it splits in 2, and then each side has 500. And then we can use that property of the trees in the analysis to show that it's not going to be very many probes to get to any key. So the search is just the same as we've been doing, just generalized. There's a list of keys at every internal node, and that key tells you that then links for every key that give you a place where your key would have to be. This link is for all the keys in the B tree that are between this key and the next one. And in every case it's that way. So if we're looking for E and this B tree, we'd go down the left link, and then it would go down the second link because E is between D and H, and that's just the way it organized. And then when you get to an external node, you just look for it. That's all searches terminate at an external node, and otherwise it's just a generalization of what we just did. And insertion works the same way. We get to the bottom and then we split. So let's look at just inserting A into this B tree. It comes into the node on the left, and then that makes that temporarily over full. It's got one too many, so we split it into 2 nodes, and that causes us to add a new entry into this internal node. In this case, it's a C, which is the smallest one in this new page, and that has to be added. And we can move all those over. There's plenty of time by the memory model. We're only counting the number of times we access the pages, and we get to move things around for free. And you could have some hybrid structure where you use something different for the internal model, but usually it's fine just to do that. Now that one becomes overfull, so it has to split, and we have to create a new route, just in the same way as we've been doing. So without seeing all the details, you can understand that the same basic idea is going to work in this this situation where we're dealing with much more memory. And so the end result is that a search or an insertion in a B tree of order m, that's where we're putting the m keys per page, requires between log base m minus 1n and log base m over 2n probes. And that's going to be a really small number. So say m is 1,000, log base m over 2 is this log base 500. So what power do you have to raise 500 to get bigger than n? In practice, that's going to be like 4 or 5. And we can keep the root page in memory, so that it means for any conceivable application, you can get to any piece of data, even if it's trillions of pieces of data. It's huge file. You can get to any one with only 5 or 6 probes. That's quite amazing. It's really an astounding example of algorithmic technology, doing something that you wouldn't really necessarily think that you could do so easily. Maintain a dynamic search symbol table with trillions of keys so that you can get to any key just by looking 5 or 6 places. But that's what B-trees provide for us. This is a simulation that shows a growing B-tree. So when a page, at the top, there's just one page that fills up. When it fills up, it's red, and that splits into 2 half pages. And then keys get added on one side or the other. So each line in this table, some page is getting a new key, and eventually one of them fills up and splits. Now we have 3 pages, and we keep going. Eventually one of them fills up and splits. Now we have 4 pages, and now this time the first one fills up and splits, and so forth. So the black is the occupied part of the page, the white's the unoccupied part, and full page about to split, then right below there's 2 pages. So this shows the process of building a large B-tree. And you can see the amount of black. It's kind of half empty. It's a little more than half empty usually, analysis shows. And people have variants of these algorithms that keep it much more than half empty if that kind of space is a consideration. So as I've mentioned, red-black trees and B-trees are widely used as system symbol tables. The Java implementation of tree map and tree set is red-black trees. C++ standard template library uses red-black trees. And it's also used in the Linux kernel and in many other systems. B-trees, there's many different variants that give different characteristics of space usage and other characteristics in most databases nowadays that you might use. SQL or Oracle's database and others are based on some variant of B-trees because they're so effective. But you really know that your data structure algorithm is used by a lot of people when it appears in the popular culture. My friend Philippe Flageolet, who recently died, but was a famous French mathematician, sent me an email late one night. He was quite excited because he was watching a rerun of an English actually Canadian TV show on French TV. I didn't know he spent his time doing that, but he was very excited because he saw this clip.
It was the red door again.
I thought the red door was the storage container.
But it wasn't red anymore, it was black.
So red turning to black means what?
Budget deficits, red ink, black ink.
It could be from a binary search tree. A red-black tree tracks every simple path from a node to a descendant leaf that has the same number of black nodes.
Does that help you with the ladies?
So not only is there some excitement in that dialogue, but it's also technically correct, which you don't often find with math and popular culture or computer science. A red-black tree tracks every simple path from a node to a descendant leaf with the same number of black nodes. They got that right. And that's also true of B-trees, and both of these methods are very effective and widely used. Welcome back. Today we're going to take a look at a number of interesting applications of symbol tables and the binary search tree data structure to address problems with processing geometric data. So let's take a look at it. The idea is that we're going to be talking about geometric objects, not simple keys like strings and numbers. So here's an example. So say your geometric objects are points in the plane, and you specify a rectangle that's oriented with the horizontal vertical axes. And you might want to ask which points are inside the rectangle, or how many points are inside the rectangle. Or maybe what you're processing is rectangles. You have a set of rectangles, and we want to know which of these rectangles intersect, or how many rectangle intersections are there. These are interesting problems that have lots and lots of applications, from computer-aided design to games and movies, and also in abstractions such as databases and other situations where you might have multiple keys or multiple dimensions. And it's a very interesting extension of the ideas that we've looked at for symbol tables for all sorts of familiar applications. And surprisingly, binary search trees and the associated algorithms that we've looked at are going to provide very efficient solutions to a number of important problems in this area and really have enabled new developments and new technology in all of these kinds of applications. So to get started, we're going to look at a simple problem called one-dimensional range search, and it really forms the basis for what we're going to do. It's a little bit of an extension of the ordered symbol table API that we gave before. And we're going to have the operations range search and range count. So one-dimensional just means we have one key. So we'll insert a key value pair as before. And what we want to do is be able to search for a key and the value associated with it. We want to be able to delete. But then we want these operations range search and range count. So find all the keys that are between two given keys, or give how many keys are there between two given keys. So for this example at right, we have insert a number of keys, and we're just showing them in sorted order. But then you might say, well, how many keys are there that are between G and K? In this case, there's just two. And then the client might say, well, what are those keys? You want to be able to return them. And this is a very common operation, say, in databases. You want to return how many taxpayers have salaries between 1 million and 10 million, and then which ones are there, and so forth. So range searching is a very important fundamental operation. Now, in geometric interpretation, we just think of the keys as points on a line. And so the key values, are just specified as points on a line. We might convert the letters to numbers, or keys might be numbers. And then what we're looking for is to find or count the points in a given interval in one dimension. So how we're going to implement that? Well, this is a basic problem that is very similar to our symbol table problem. We might consider keeping the things in an unordered array. Just put them in an array, and then, while insertion is fast, we just add it to the end of the array. We might have to use resizing to make the array grow. But this is unattractive because for large numbers of keys, in order to count the keys that fall within a given range, you have to go through all the keys and test whether they're in the range or not, and to return them the same way. So take linear time for a large number of keys. If you keep the things in order, like in a binary search situation, then to insert, in order to keep it in order in an array, you might need to move the larger ones over one position and so forth. Our elementary implementation of binary search, when we did symbol tables, did this. So the insertion time might be linear, but then you can use binary search to look for the two endpoints. So it's only going to take time proportional to log n, and then from that you could figure out how many keys there are, or return them all between the index of the lowest one in the range, the index of the highest one in their range. So those elementary implementations are not acceptable for large numbers of keys because they have the linear time operations. So what we really want is to have time proportional to log n for insert and for counting. For range search, of course, we have to touch every key that we return, so the running time is going to be proportional to the number of keys that match. But anyway, those are reasonable goals, and they're easy to achieve. So, for example, what about one-dimensional range counting? Well, what we're going to do is just keep the keys in a binary search tree. And we looked at the implementation of the rank function for binary search trees, where for every key we can compute how many keys are there that are strictly less than that key. So in this case, the rank of E is 2 and H is 3 and so forth. So in a binary search tree, those rank numbers go in increasing order as we do an in-order traversal. And that's easy to compute. Either keep that rank tree as a field or keep a field which has the size of the tree, and it's easy to compute the rank from that. So how many keys between, say, E and S? Well, 1, 2, 3, 4, 5. It's actually just the difference between the ranks plus 1 if the high entry in the range query is in the table and not plus 1 everywhere. So there's the same number of keys between E and S as there are between E and T. 5. Between F and T, there's only 4. So that's a really 1D range count is a very easy computation to perform in log time with a binary search tree. The number of nodes examined when we do a search is the length of the search path to low plus the length of the search path to high to find their ranks, and that's going to be time proportional to log n. So in range search, well, we just do a recursive search, and to find all the keys between low and high, you look in the left subtree if any of them could fall in the range. You look at the current node, and you look in the right subtree if any of them could fall in the range. And it's easy to tell whether any of them could fall in the range by just checking whether the range overlaps the root or not. So if we're looking for all the keys between F and T, then we have to look at both subtrees of the root S, but we don't have to look at the left subtree of E because all of those are less than E and therefore are less than F, so we don't have to look there. But otherwise, it's a simple modification of recursive tree search to find all the keys. And it's easy to see that the running time of that is going to be proportional to the number of keys returned plus log n. So that's one-dimensional range search using binary search trees. So now let's look at a basic geometric data processing problem of determining intersections among a set of line segments. So it's called the orthogonal line segment intersection search, where the line segments are constrained to be either horizontal or vertical. And so suppose we have a large number of such line segments, and what we want to do is be able to find all places where they intersect. And as we'll see, this extends to a practical problem in a number of situations. So in this case, there's 4 places where these lines intersect. So how are we going to be able to determine these intersections efficiently? Now, the natural algorithm, or the naive brute force algorithm, is quadratic in time. So that is, for every line segment, you check whether it intersects with every other line segment. And again, as we know, such an algorithm is not going to be practical for huge numbers of line segments. So just to simplify our code in these slides, and it's often the case for geometric data processing, we have to worry about degeneracies, where lots of things have the same x or y coordinate. And just to simplify the code and to get at the main principles of the algorithms, we're going to assume that all the coordinates that we have are distinct, that we've preprocessed in some way to remove the ones that touch without intersecting. So the method that we're going to look at is the so-called sweep line algorithm. And the idea is to think of a vertical line that sweeps from left to right through the data, and to consider it as every time it hits some line segment as an event where we have to do something. So sweeping from left to right means we consider each x-coordinate as an event. First thing is, if we hit a horizontal line segment, we're going to hit the left endpoint first. And so what we'll do when we hit the left endpoint is insert the y-coordinate of that line into a binary search tree. So we're going to keep track of y-coordinates in a binary search tree. So that's what's happening over in the right there. So now, again, sweep from left to right. What's the next smallest x-coordinate? In this case, it's the line number 1 there, and we'll remember its y-coordinate in a binary search tree. And then 2 and 3. So that's one kind of event that can happen as we sweep from left to right. Another kind of event is that we hit the right endpoint of a horizontal line segment. In this case, we hit the right endpoint of line segment 2. So at that point, the right endpoint of a horizontal line segment, we just remove it because we've processed that line completely. In this case, we didn't find any intersections. So left endpoint, insert the y-coordinate into a BST. Right endpoint, remove that y-coordinate from the BST. So the BST contains the y-coordinates of all the horizontal lines that currently might involve an intersection. And then the third kind of event is what happens when we hit a vertical line segment. Well, in that case, all we need to do is just do a range search for the interval of y endpoints. Any point that's inside that interval is going to represent a horizontal line segment that is an intersection. That's the basic idea behind the sweep line algorithm to find intersections in sets of horizontal and vertical lines. And it's actually a very simple algorithm, and it's very easy to see that the running time is going to be proportional to n log n plus the number of intersections returned, where there's n horizontal vertical line segments. And it's a couple of ways to implement it. One thing is you could sort according to the x-coordinates, or you could just put them all on a priority queue. So that's going to take n log n for every one of the lines to process them all. Either n to build a priority queue and then log n to take the smallest off each time, or n log n for the sort. And then putting the y-coordinates into a binary search tree is, again, n log n, and same for deleting. Each point has to be inserted, deleted. There could be as many n as n in the tree for each one, so it's a total of n log n. And then the range search in the binary tree for each one of the range searches. It might take log n, it might be as many as n, and then there's plus the number of points returned. That's a quick sketch of the proof of this proposition. And with that 1D range search implementation, we get an efficient n log n 2D orthogonal line segment intersection algorithm. Now we're going to look at KD trees, which is an extension of BSTs that allow us to do efficient processing of sets of points in space. And it's very flexible and very useful in lots of applications. Now we're going to extend the API to talk about two-dimensional keys. So that's just, you can think of two-dimensional keys as points in a two-dimensional geometric space. So we're going to talk about insertion and search. We want to talk about deletion, and then range search and range count. So we want to be able to insert and delete points. You can think of a two-dimensional key as a point in a two-dimensional space. And then we want to be able to find all keys that lie within a two-dimensional range. That's a rectangle, as I mentioned at the beginning, or count the number of keys that lie in a two-dimensional range. So again, the geometric interpretation is the keys are points in the plane. And we have a range, 2D range is a rectangle or is oriented to align with the horizontal vertical axes. And we want to be able to find or count the points in a given rectangle. And this one has many, many applications, and we'll talk about some of them later on. And even if it's not points in the plane, just databases, you might ask for all the people with incomes between 1 million and 10 million who are between 40 and 50 years of age. And this kind of algorithm and data structure would be useful for that kind of situation too. So how are we going to solve this problem, implement this API? We build a data structure containing points that can efficiently support range searching and range counting. Well, one easy way to do it is to just think about dividing space into a grid of squares. So we'll pick a parameter m and divide space into an m by m grid of squares, and then process all the points and make a list of points that are contained in each square. We can use a two-dimensional array to directly index relevant squares. And for insert, you just take x, y, figure out which square it belongs to, simply divide by both coordinates by m and look in the two-dimensional array, and just add the point to the list for the corresponding square. Then range search is only find the squares that intersect the query and process the points in that square. And depending on the value of the parameter m, you have a space-time trade-off. The amount of space required is m squared for the grid, plus n. You have to have a linked list element or whatever for each point. And then the time, though, gets divided by m squared. Your number of points m are spread out over the m squared different squares. And so on average, you examine n over m squared points per square. So you don't want to make m too big, be too much space. You don't want to make m too small, be too much time. So what we want to choose is the square size that would best balance these two needs, and then it's easy to see that what you should choose is m to be about square root of n, so then your space is within a constant factor of n and your time is constant. So if the points are randomly distributed, then this is ideal. It takes this linear time to initialize the data structure, and to insert and search, it takes constant time per point in the range. And this is absolutely a fine method that is not that difficult to implement in the case that the points are evenly distributed. Unfortunately, it's usually the case that in geometric data that the points are not evenly distributed. And so a well-known phenomenon known as clustering that says that the points aren't going to be evenly distributed all over the whole thing. In the case of the grid implementation, they might all fall in the same square. And so the average list length is short. This is like what we encountered with hashing. If you take all the points in one square and zero in all the rest of them, your average is still n over m squared, but they're all in that long list, and you're going to have a slow algorithm if it's based on this. So we need a data structure that more gracefully adapts to the distribution of the data. And again, it's well known that most geometric data has this kind of problem. So for example, here's some data which is cities in the US. It's got 13,000 points, but if you tried to use the grid implementation for this, you find that half the squares would be empty and half the points are in just 10% of the squares. So the clustering in the data is going to make the implementation inefficient. We need to adapt to the data, and this is very, very typical in geometric data, particularly in higher dimensional data, as we'll see in a minute. So people have developed all different kinds of methods for adapting in this way. And what we're going to look at is one of the most widely used, which is basically to use a tree to represent a recursive subdivision of the plane of two-dimensional space. It's going to be recursive. It's going to be based on the points, the way in which we divide into half planes. And it's one of many different algorithms that have been studied for this, but again, it's a simple one and widely used. So, for example, if you've played the game Doom or used a flight simulator, these types of graphical simulations and animations are made possible only through the use of space partitioning trees like 2D trees and quad trees, and also in all different types of scientific data processing. These things are extremely important. Whenever you're processing geometric data, you're doing some kind of geometric search. Where's the closest thing? How am I going to find the closest thing efficiently? What things are nearby? And so forth. So rest assured, these types of algorithms lie at the heart of any program that you use that is involving a lot of geometric data. So those are just two examples. So let's look at how it looks now. So a 2D tree is, again, it's going to be a data structure based on a bunch of points that's going to facilitate efficient data processing of these points. So just as we do for symbol tables where we take keys, now we're going to take points and we're going to build a data structure based on these points. And the idea is to build a tree that corresponds to recursively partitioning the plane. So arbitrarily, our first point, we're going to divide the plane into two parts based on a vertical line through that point. So now in the tree on the right there, all the points that fall to the left of the first point are going to be on the left, and all the points that fall to the right of that first point are going to be on the right. But then we get to the next point, we'll switch and we'll partition on a horizontal line. So now our second point in the tree, the left subtree corresponds to everybody below that horizontal line, and the right subtree corresponds to everybody above it. Similar, if our third point comes on the left, again we'll partition according to the horizontal line through that point on the left. So if we go left and then left, that means all the points to the left of 1 and above 3, so the square in the upper left is represented by that node in the tree. Again, now when we go to one level below, we switch again to vertical, alternate between horizontal and vertical partitioning of the plane. So it's a regular binary search tree, but it's got this interpretation based on the geometric data where we switch which key we use for the comparison, the x-coordinate or the y-coordinate at each level. And that corresponds to this partitioning of the plane. So now 5 comes in, that's to the left of 4 because it was partitioned on a vertical, and 5 is going to partition on a horizontal. And this is a simple and completely well-defined partitioning of the plane corresponding to a binary tree. Now the 9th point, well, it's to the left of 8, above 2 to the left of 8, and then corresponds to horizontal partitioning. 10th point is to the right of 1, it's below 2, so we go to the left, and it's to the right of 7, so we go to the right. So that's a way to build a binary tree corresponding to a partitioning of the plane. And it's really the same as a binary search tree, it's just that we alternate which coordinate we use as the key. At the even levels, we think of a vertical line, and the left subtree is all the points to the left, and the right subtree is all the points to the right. On odd levels, we use a horizontal line, and the left subtree is all points below, and the right subtree is all points above. And the code for this is the same as for binary search trees. It's simply which coordinate we use for the comparison. That's the only difference. So that's 2D tree implementation. So now what about solving a problem like this range search problem for a 2D tree? So now we have a query like this green rectangle, and what we want to find is all the points in the data structure that fall within that rectangle. Well, we're going to use the 2D tree represents our points, and we're going to use the structure and definition of that tree to go ahead and help us find the points that are in the rectangle. If the root node lies in the rectangle, then we're done. We can return that point, but we have to look on both sides to look for more. But if the rectangle lies to the left of the root node, then we only have to look in the left and so forth. So let's look at how this works in a demo. All right, so we're going to try to find all the points that are contained in that green query rectangle. So first thing is to check if our rectangle contains the node at the root. In this case, it doesn't. So since it's to the left of the splitting line at the root, we only have to search in the left subtree. Now we search the left subtree. We're going to check if it contains 0.3. It does not contain 0.3, but now which subtrees do we search? In this case, the rectangle intersects our splitting line, so we have to search both subtrees, both above and below. So first we search the left subtree, that's the one below. Does it contain 0.4? No. It's to the left, so we only have to search the left subtree of 0.4. And so we search the left subtree and we check if it contains 0.5, and it does. That's the one that we return. It also intersects the splitting line, so we have to search both the subtrees. In this case, they're both empty. So we're done with that, but now we have to go back and we have to search the other subtree of 0.3. That's the above, so now we check is 0.6 in the rectangle. In this case, it's not. And it's to the left, so we have to search the left subtree of 0.6, and that one's empty, and now we return, and we're done. So we don't always go down just one branch. If our splitting line hits our rectangle, we have to go down both branches. But still, this is a very efficient algorithm. Particularly think about the rectangle being small. It's going to be not that different than a regular search in a binary search tree. All right, so what about the analysis of how long is this going to take? Well, again, a typical case, a rectangle's small, that we're only going to examine really a path of the tree, maybe a couple of other nodes along the path, and the running time will be proportional to the number of points returned plus log n. With geometric data, the worst case can be bad. So like all the points could be arranged in a circle, all different types of problems might occur. And with some difficulty, it's possible to prove that even if the tree's balanced, you can get a worst case proportional to square root of n. So analysis of 2D trees is a bit beyond our scope. But for many practical applications, they're easy to implement and worth using. Let's look at another, using 2D trees to solve another problem, the so-called nearest neighbor search. So now, instead of a rectangle, we have a query point, and our goal is to find the closest point to that point. So in this case, our query point is over here in green, and the algorithm's going to want to return 0.5. That's the closest one to the query point. So let's see how that looks in a demo. So again, we start at the root, and what do we want to do? Well, we're going to check, whenever we're at a node, it represents a point, so we're going to check that point. And we'll compute the distance from that point to our query point. And if that distance is less than the best found so far, then we'll keep that as the champion. So the first point, that's the closest we found so far to the query point, so we'll save number 1 as the distance. And we'll only worry about the possibility of finding something closer than that. And so just using that distance, we recursively search any part of the tree that could contain a closer point. And so that's what we'll continue to do. So in this case, the query point is to the left of the splitting line, and we'll always go towards the query point first. So in this case, we have to search both. There might possibly be a closer point than one over in the right. If you come like straight across, there might be a closer point. We're going to have to look at both as far as we know now, but we'll go towards the query point and see if we can find something closer. So in that case, now we go to point 3, compute the distance of that point to the query point. It's closer, so we update 3 to be our new champion. And so now we're only going to look in parts of the tree that could give us a point that's closer to our query point than 3. Notice already that'll mean when we get back to point 1, we won't search the right subtree because there could be no point on the right subtree, the right of this splitting line that's closer to the query point than 3. And so that idea of getting closer and closer to the query point is going to cut out different parts of the tree as we process. But anyway, starting at point 3, as far as we know, we're going to have to look at both subtrees. So sometimes we look at both subtrees, but as we get closer and closer, we only look at one. So let's look at point 3 now. Again, go towards the query point, so we'll go to the top first, and that takes us to 6. 6 is not any closer than 3 was, so that's not going to update our champion. And so we'll search 6's left subtree, which is empty, and then its right subtree. Well, the nearest neighbor can't, we don't have to go down the right subtree of 6 because you can't have a point in that rectangle that's closer to the query point than 3. So now we can return from that, and now we have to look at the bottom subtree associated with 3. And so that takes us to 4, and that one is not closer, so we still have 3 as our current champion. So now we'll search the left subtree of 4 first, because the query point is to the left of that splitting line, and that takes us to 5. And 5 is our new champion, so that's the closest point that we know about. Could there be a node that's closer to 5, to our query point than 5 in the right subtree of 4? We have to go above, sorry, to look at the top subtree associated with 5 and find that it's empty. And now we're back at 4. Do we have to search the right subtree of 4? No, because there can't be a closer point than 5 in the right subtree of 4. So we're done with 4, and we return to come to 3. And now we search the supposed to search and return from there. We now are at 1, supposed to search the right subtree of 1 next, but we can prune that. Nearest neighbor couldn't be in there. So then we're done, and we found that the nearest neighbor is 5. And this is going to be very efficient because as we get closer and closer to the query point, we're cutting out all the subtrees that are away. And again, in practice, the running time of this algorithm is going to be close to logarithmic. So in typical cases, the running time of nearest neighbor search in a 2D tree is going to be proportional to logarithmic. It is possible to concoct cases where you're going to have to examine all the points. For example, if they're all arranged in a circle and your query point's in the center or something of that sort. But for typical nearest neighbors and do range searching extremely efficiently. It's a very efficient and simple data structure for processing k-dimensional data that's very widely used. And the whole idea is that data clusters, particularly in high dimensions. And also one point to make for this class is that this algorithm was discovered by an undergraduate in an algorithms class. So that's John Bentley, who discovered this while an undergraduate at Stanford. So it's a simple idea but expert scientists were struggling with dealing with huge amounts of geometric data, and Bentley found this way to process it efficiently that's been widely used ever since. And in particular, just as another example, consider the idea of n-body simulation, which is a classic problem in physics. Where you've got n particles mutually affected by gravity, and basically the computation is based on computing the interacting force for each pair of particles. And so then there'd be mutual gravitational pull, and this is what happens with a large number of particles in a certain simulation, and people understand properties in the universe by coming up with doing these kinds of calculations and comparing against what's observed in space. Now, but the thing is, for each pair of particles, so if you have n particles and you have to do it for each pair, that's n squared. So the progress of scientific investigation is going to be affected by how quickly you can do this calculation for a large number of particles. There's a lot of particles out in the universe, and you can't do a quadratic calculation for large n. Another undergraduate in an algorithms class discovered this idea for n-body simulation, and that's Andrew Appel. And his idea was that if some particle is way away from some cluster of particles, we can treat that cluster as a single aggregate particle and not do the individual force calculation between our particle and every one of those in the aggregate, but use the center of mass, and you get a very accurate approximation to the n-body doing that. And the algorithm that he used is based on 3D trees with the n particles as nodes and storing the center of the mass of the subtree in each node. And then to compute the total force traversing the tree, you have all the information that you need to complete the n-body calculation, but in time much closer to n log n than to n squared. And that idea that you didn't need to take time proportional to n squared, but with a geometric algorithm like a 3D tree, you could get the time to n log n, that enabled all sorts of new scientific investigation. And it's an example of the use of algorithms to enable new research. Okay, next we're going to look at another extension of geometric algorithms to process slightly more complicated objects, and then we'll see an important application. And this is called interval search. So now, instead of points, our data is intervals. So this is, we'll start with one dimension as before, and right away I can see that it's a more complicated problem than we've been dealing with. So we want to support the following operations. We want to be able to insert an interval. So an interval is just a left endpoint, right endpoint of one-dimensional data, or points on the line. We want to be able to insert an interval, search for an interval, delete an interval, but the main thing is we want the interval intersection query. So given a query interval, we want to find all intervals in the data structure that overlap that interval, or find any interval. We'll start with that simpler problem. So how are we going to support that? So this is the API in Java code. We have intervals, so instead of one key we have two, which is the left and right endpoints of the interval for put and get, and then we have delete, and then we're going to have the intersects. And again, to simplify the code, we're going to make the non-degeneracy assumption that no two intervals have the same left endpoint. That's easy to fix, but we don't simplify the code. So now we'll look at a data structure called an interval search tree that helps to solve this problem. It's an extremely simple algorithm, but surprisingly complicated to understand, so we'll go slowly. So the first thing is, what we're going to do is use the left endpoint of each interval as the binary search tree key. So our nodes store intervals, but we only use the left endpoint as the key. So this is the binary search tree that's built from those 6 intervals in our example. 17, 19's at the root, so everybody with a left endpoint less than 17's to the left, and everybody with a left endpoint greater than 17's to the right, and so forth. So that's a binary search tree built from those intervals. So that's easy. Just build a binary search tree. Just use the left endpoint as the search key. But we're also, in each node of the tree, we're going to store not just the interval, but we're going to store the largest endpoint in the subtree rooted at that node. So at every node, we're going to store the maximum endpoint in the subtree rooted at that node. So at the root, the maximum endpoint, or the rightmost point covered by an interval, is 24. So we store 24 at the root, and of course at the right subtree. In the left subtree, the max endpoint is at 18. So that's what we store for the associated data with the node to the left of the root, and so forth. We're going to have to, that's data that we're going to have to maintain when we do an insert, and it's data that we'll use when we're doing an interval intersection search. So let's take a look at a insertion into an interval search tree with a demo. All right, so the insertion algorithm is pretty simple. We do the BST insertion, it's just that we have to do that update of the maximum in each node on the search path. So to insert 1622 in this tree, we use the left endpoint as the search key. 16 is the left endpoint of our insert interval. We compare that with 17 and therefore go left. Now 16 is bigger than 5, so we go right. Now 16 is bigger than 15, so we go right. And that's null, so that's where we insert our new interval. So now we're going to go back up the tree, and for every node that we encounter, it could be that our right endpoint of our interval is bigger than what was there, so we have to check all the way up the path the maximum in each node on the path. So we have to check each node to see if 22 is bigger, and for the 3 nodes to the left, it is bigger than 18. For the node at the root, it's not, that stays to be 24. So it's just binary tree insertion, but then after the insertion on the way up, we go ahead and check if the maximum that we have is bigger than the maximum there and update it if necessary. So easy to code. All right, so now about how do we do a search. So the search is definitely more complicated and kind of mysterious, but let's look at the rules for search in an interval search tree. All right, so now we're going to look to see if we have an intersection. We want to find just any interval that intersects this query interval 23, 25. We're not going to try to find them all. We'll get back to that in a minute. Try to find any interval that intersects our query interval. So let's see what we have to do. So first thing is, if at the root we have an intersection, then we're done. We just return. In this case, 2325 does not intersect 1719. So we have to go down the tree somewhere. So left subtree is null, go right, okay. Otherwise, we have to check whether the max endpoint in the left subtree is less than the low point in our interval. And it's easy to see, well, if that's the case, then we're not going to find an intersection in the left. The maximum endpoint in the left is 22, and we're looking for 23. We're not going to find anything there, so we just want to go right. So in this case, we'll go right. 22 to 23, no intersection on the left, so we go right. And now we do find an intersection. 2124 does intersect with 2325 because 23 is in the middle there. So we find an intersection. Now, on the other hand, let's say that we're looking for 1214. No intersection. All the algorithm says is that if you didn't go right, go left. So let's go left. In this case, so we weren't able to show that there was no intersection on the left, so we're going to go left. In this case, we compared 1214 to 58. So now we apply the same rules. Does it intersect? No, it doesn't intersect. Should we go left? Well, no, the maximum endpoint in the left node is 8, so we can't have an intersection there, so we're going to go right. Compare 8 to 12 and go right. So now does 1214 intersect 1518? It does not. So there's no intersection. So now what do? Should we go left? No, the max endpoint on the left is 10, so we shouldn't go left. We're going to go right. Does 1214 intersect 1622? It does not. Now the left endpoint's null, and so we're just going to go right, and there's no intersection. So in both cases, we just went along one path in the tree to determine whether or not there was an interval intersection. Let's look at one more example, 2123. Let's see, 21 through 23 to 1719. They do not intersect. So now what are we going to do next? We're going to compare the left subtree, and it's not. 22 falls within our interval, it's not less than ours. So there might be an intersection there. So we better go to the left. So we do go to the left. Now we compare against 5.8, and there's no intersection. So now we're going to go left or right. Well, we're going to go to the right because the max endpoint in the left subtree is 8 and our interval is 21, so no intersection on the left, so we're going to go right. Intersection 21, 23, 15, 18, they do not intersect, so now do we go left or right? Again, 10 is less than our left endpoint 21, so we better go to the right. And now 21, 23 does intersect 16, 22, so we return an intersection. Again, one path through the tree to determine an intersection. So from those rules, you can see that the amount of code required to implement this intersecting interval is extremely low. We just check for an intersection. If we find it, return. If left is null, we go right. Otherwise, if the max is less than low, we go right. Otherwise, we go left. It could hardly be simpler. A really amazingly simple and efficient algorithm. We should convince ourselves really that it always works, and so we'll spend just a moment on a short proof. So let's look at the cases that could happen. First thing is, if the search goes right, then there's no intersection in the left. And that's easy to convince ourselves of that just from what we did in the demo. Of course, if the left subtree is empty, there's no intersection there. But if the max endpoint in the left subtree is less than low, that means every interval in the left subtree has a max endpoint less than low, and so therefore it can't intersect. So if you go right, there's no intersection in the left. Any possible intersection would have to be in the right. And then the other point is that if you go left, then either there's an intersection there or there's no intersections at all. Let's suppose that there's no intersection, and that's equivalent to saying if there's no intersection in the left, then there's no intersection in the right. So let's look at if there's no intersection in the left. Since we went to the left, and then we've got low less than max. But for any interval in the right subtree, it's got to appear after low because since there's no intersections in the left subtree, high has got to be less than C, because they're sorted by left endpoint, and then that means that C's got to be less than A if A's in the right, so then therefore there can't be any intersection in the right either. No intersection in the left means no intersections at all, so those two cases is enough to show that this algorithm finds an intersection if there is one. And the other thing we can do with this is just use a red-black BST to guarantee that we solve this in time proportional to log n. So insert, find, delete, and find any interval that intersects all take time guaranteed proportional to log n. And if we want to find all intervals, we just have to run the algorithm for each interval that's until we come up against no intersection. So it'll take time proportional to r log n if there's r intervals that intersect. The theoretical best that you could possibly do would be r plus log n, but in practice r log n is quite efficient. This is an easy and very efficient algorithm to solve this interval search problem. And as we'll see, this algorithm is applicable to an important application that we'll see in a minute. To finish up, we're going to look at the rectangle intersection problem. That's got important practical applications and uses the techniques that we've been studying so far. And it's a simple generalization of our line intersection problem. So now we have a bunch of rectangles. They're all oriented horizontal or vertical. And what we need to do is find all the intersections in that set of rectangles. And again, n could be huge in applications, as we'll talk about in a second. And the naive brute force algorithm involves checking each pair of rectangles for intersections. And what we want is a more efficient algorithm than that, as usual. And again, to keep the code simple, we're going to assume that all the coordinates are distinct. We don't have any equal lines we have to worry about. Whether we consider rectangles that touch to be intersecting and so forth. So that's the problem, rectangle intersection search. And this is historically an extremely important problem. In the 1970s, when we switched to very large scale integration for computers, we were switching from a situation where we were wiring physical devices together to a situation where we were essentially drawing the computer. And there were machines that would take drawings and return, and from those drawings, like this, make physical things that implemented computers with different layers and different physical materials interacting in different ways. Some things are wires, and some things are switches that are used to implement memory bits and computer logic. But the key point about it is that designing a computer became a geometric problem. And so people to design new computers would make huge drawings that just showed the lines that corresponded to the materials that had to be created to make the computer. Now, it was very expensive. You didn't want to have any bugs when you're making a chip. And there were various rules about what you can do on these drawings. And basically, these rules had to do with doing this orthogonal rectangle intersection search. You can't have lines that come too close to other lines. Certain types of lines can't intersect. Need spacing between certain types of wires. And you wanted to, before you tried to make the physical circuit, to do this checking, which involved this orthogonal rectangle intersection search. And it was actually the case that the progress of faster and faster processors with more and more components was slowed because people were using the naive quadratic algorithm to do this design rule checking. And it's an example of Moore's law. As we built a faster computer, say in 1970X, we needed to check in rectangles. But now, maybe a year and a half later, you have a computer that's 2 times faster, but you also want to build a bigger computer so you have twice as many rectangles to check. So you have 2 n rectangles to check now, and your computer's twice as fast. So we get to use the faster and bigger computer to build faster and bigger circuits, but that doesn't help if you're using a quadratic algorithm. If you're using a quadratic algorithm and it takes you m days to check your design rules, and people were running these things on the order of days, then for the next computer it would take 2m days. It would take twice as long. And so people that were using quadratic algorithms were definitely held back. And it was Ed McWright at Xerox PARC who discovered interval search trees and the logarithmic algorithm that allowed us to sustain Moore's law and keep building bigger and bigger computers by changing this quadratic algorithm to a linear arithmetic algorithm. And let's see how it works. Really, it's a modification of the sweep-line algorithm that we looked at for intersecting lines, but now we're going to use that for intersecting rectangles. Rather than using range search as our basic operation, we're going to use interval search. So now, every time the line sweep hits a rectangle, that corresponds to an interval. If it's the left part of a rectangle, then we put that interval into our interval search tree. So in this case, we put on 0, and then we put on 1, and then we put on 2. And that'll give us now 3 rectangles on our sweep line. And so now the question is, when we hit a new rectangle, we want to do an interval search to, if we're at the left, to check which ones intersect. And the interval search tree algorithm is going to tell us which intersections there are right away. When we reach the right, then we remove integrals and so forth. But with the basic interval search tree algorithm and the sweep line process that we've talked about, you can get the orthogonal rectangle intersection search problem solved in time proportional to n log n plus r log n, where r is the number of intersections. And typically in design rule checking, you wouldn't expect too many intersections. So again, just as with line intersection search, using a priority queue or a sort is only n log n for processing the x coordinates. And because interval search trees take log n for every operation, the insert and delete intervals is n log n total, and the searches is n log n plus r log n. So the bottom line is that the sweep line algorithm takes this rectangle intersection problem and reduces it to 1D interval search, and we have an efficient algorithm for that problem, and that enables us to solve the problem in linear arithmetic time instead of quadratic time, and that definitely enabled new progress in technology, and it's a fine example of the importance of algorithmic technology. So here's our summary of applications of binary search trees for geometric problems. We started with one-dimensional range search and just used a regular binary search tree to compute ranks to get the answer. But that, as the basis, we were able to solve the two-dimensional line segment intersection search using the sweep line algorithm. Then we looked at range search and other operations using KD trees. Again, a modification of binary search trees. And then the interval search tree to solve the one-dimensional interval search problem, and then how that corresponds to the basic algorithm that you get to if you use the sweep line algorithm to solve rectangle intersection. Many of these problems are the basis for geometric processing of huge amounts of data that we see all over the web. And our basic search tree mentality and APIs and binary search tree data structure give us efficient solutions to these important practical problems. Welcome back. Today we're going to look at hashing, which is another approach to implementing symbol tables that can also be very effective in practical applications. Here's our summary where we left off with red-black BSTs, where we could get guaranteed logarithmic performance for a broad range of symbol table operations. And the question is, can we do better than that? Is logarithmic performance the best we can do? And the answer is that actually we can, but it's a different way of accessing the data, and also doesn't support ordered operations. But there's plenty of applications where the extra speed for search and insert that we can get this way is worthwhile. The basic plan is to think of the symbol table as really try to reduce the problem to being like an array. And what we do is use a function known as a hash function that takes the key, that our symbol table key, and reduces it to an integer, an array index. And we use that array index to store the key and the value in an array, maybe the value in a parallel array. Now, there's a lot of issues in doing this. First thing is we need to be able to compute the hash function. That is easy for some types of data, but it can get complicated for more complicated types of data. Then the other thing is that instead of doing compare tos, we're going to be doing equality tests. So we have to be sure we've got the method that we want for checking whether two keys are equal. All we're going to do is look in the table and try to see if the key that's there is equal to the key we're looking for. And then there's the problem of collision resolution, where since there are so many possible values for a typical data type, we're going to get the situation where two values hash to the same array index. And we need a collision resolution strategy to try to figure out what to do in that case. And these things are not difficult, but they're all worth articulating as separate issues that we have to deal with in order to get an effective symbol table implementation. Hashing really, at its core, is a classic space-time trade-off. If we had no limitation on space at all, then we could have a very huge array with space for every possible key and just use the key itself as an index. If our keys are 32-bit integer keys and we've got a table of size 2 to the 32nd, then we're just fine. If there were no time limitation at all, then I would just hash everything to the same place and then do sequential search. But sequential search can be slow if we have lots of keys. So what hashing is kind of in the real world, where we're trying to trade off this idea that we don't have unlimited space and we also don't have unlimited time, so we're trying to find something in between. So we'll look at hash functions, separate chaining, and then two collision resolution methods called separate chaining and linear probing. Now we'll look at the implementation of hash functions. So idealistically, what we'd like is to be able to take any key and uniformly scramble it to produce a table index. We have two requirements. One is that we have to be able to compute the thing efficiently in a reasonable amount of time. And the other is that it should be the case that every table index is equally likely for each key. Now, mathematicians and computer scientists have researched this problem in a lot of detail, and there's quite a bit known about it. But in practice, this is something that still we have to worry about somewhat. So, for example, let's suppose that our keys are phone numbers. Probably a bad idea to use the first 3 digits of the phone number as a hash function because so many phone numbers will have the same area code. And it's not equally likely that each phone number has the same first 3 digits. You have a better chance using the last 3 digits. But actually, in most cases, want to find a way to use all the data. Another example is Social Security numbers. Again, it's not too good to use the first 3 digits because they're associated with some geographic region, and it's better to try to use the last 3 digits. And the real practical challenge with hashing is that with developing a hash function is that every type of key needs a hash function, and you need a different approach for every key type. Now, for standard keys like integers and strings and doubles and so forth, we can count on the designers and implementers of Java to implement good hash functions. But if we're going to be implementing a symbol with our own types of data, we're going to have to worry about these things in order to get a hash function that's effective, that leads to an effective symbol table implementation. So hashing is widely used for systems programming and applications, so some conventions for hashing are built into Java. In particular, all Java classes inherit a method called hashcode, which returns a 32-bit int value. And it's a requirement that if x and y are equal, then their hashcode should be equal. So that's something that is a convention that's built into Java, and that enables the hashcode to be used for hashing. Also, of course, if they're not equal, then you'd like it to be that their hash codes are not equal, but you can't always get that. Now, the default implementation for hashing is the memory address of the object. For hashing an object is the memory address of an object. So that kind of meets these two requirements for Java. The one that it doesn't maybe meet is the idea that every table position should be equally likely. So usually we'll do some more work to try to make that one happen. As far as the algorithms go, as far as the rules go, you could always return 17. That's legal. It doesn't have this highly desirable attribute, but everything would compile. So you have to be a little careful that somebody isn't in there doing that. So Java has customized implementations for the standard data types that people would use for symbol table keys, and that's the sweet spot for hashing, where someone expert has done implementation of the hash code, and also your application does not need ordering. But for user-defined types, you're on your own, and we'll talk a little bit about how to implement hash codes. So here's the Java library implementations for a few standard types, and they are what they are, and what we'll do is with knowledge that that's what the hash code is, we'll do some extra work to try to get this extra property that every table position should seem to be equally likely. So if it's an integer, the hash code is supposed to be 32 bits, the integer is supposed to be 32 bits, so they just return the value. If it's a Boolean, they pick out a couple of particular values that they return. Hashing Boolean types, there's only 2 different values, so well, it's hard to think about what you really might want there. For double value, this is the code. They convert to 64-bit and XOR the most significant 32 bits with the least significant 32 bits. This illustrates something that you want to do if you have a lot of bits. You want to try to involve all the bits somehow in the hash function. And for strings, it kind of treats the string as a huge number and then really computes the value of that number, mod 32. It uses an arithmetic, a way of evaluating a polynomial or a number, so-called Horner's method, where for each digit you just multiply. So it treats it as a base 31 number, and to get to compute that whole number, you multiply 31 times what you have so far and add the next digit. And that's called Horner's rule, and if you're familiar with it, fine. If you're not, you can look at this little example and decide what it is. And again, it involves all the characters of the string in computing the hash function. And actually, since strings are immutable, what Java does is keep the hash value in an instance variable so it only gets computed once. And that is going to be very effective for performance in lots of applications. So once it computes the hash code, it stores it as an instance variable, and the next time you ask for the hash code of that string, it'll just provide it. And that works because strings are immutable. How about implementing a hash code for our own type of data? And so we might have our transaction type might have a couple of instance variables, a string, a date, and a double. And we need to compute a hash code, so return a 32-bit value. And again, we want to try to make use of all the pieces of data that we have, and we also want to make use of the hash code implementations for the types of data that we're using. So one thing to do is start out with some small prime number, and this kind of mimics Horner's method to just add in more data as we get it. So we pick some other small prime number, and for each field we multiply by 31 and then add the hash code for that field. So if it's a reference type, you just use the hash code. So who is a string, so string has a hash code method, so we add that in. And dates, when's a date, so we add that hash code, multiply by 31 and add that hash code in. Trying to take all the bits and scramble all the bits and use them. And for primitive types, take the wrapper type and use the hash code. So that's a simple example of implementing a hash code for our own type of data that might include several different types of instance variables. So that's the standard recipe. Use the 31x plus y rule to combine all the fields. If it's a primitive type, use the wrapper hash code. If the field's null, return 0. If it's a reference type, use that hash code and apply it recursively. And if you have an array, you have to apply it to each entry. Or actually, Java implements that in the its arrays library. So this recipe works pretty well in practice, and it's used in several in Java's libraries. Now, in theory, it's possible to do something that has the property that that all positions are equally likely. It's called universal hash functions. These things exist, but they're not so widely applied in practice. So the basic rule is if you're computing your own, try to use the whole key, but consult an expert if you're seeing some performance problems or you really want to be certain in some performance critical situation. Now, what we get back from the hash code is a int value that's between -2 to the 31st and 2 to the 31st minus 1. Now, what we need is, if we have a table of size m, an array of size m that we're going to use to store the keys, we need an int value between 0 and m minus 1. The value of m is maybe a power of 2, or sometimes we pick a prime because of the way that we normally would get the big hash code value down to be a number between 0 and m minus 1 is to just do mod m. And if m is a prime, then from math, modular arithmetic, we know that we're using all the bits in the number in that point too. Now, since the hash code can be negative, this doesn't quite work the way this arithmetic's implemented in Java, because it's 1 in a billion times. You really have to take the absolute value. You have to take the absolute value because otherwise it'd be negative, and you can't have a negative. You want it to be between 0 and m minus 1. But even if you take the absolute value, there's going to have minus 2 to the 31st is possible. So you have to just take the 31 bits. You get the hash code out, make it positive, and then mod m is the way to go. The math doesn't quite work out right. So anyway, that code down at the bottom is, you can use that as a template for what you might want to do. And that's what we do in order to get the hash code to be a number between 0 and m minus 1. And if m is prime, it gives us some comfort that we have some possibility of each table position appearing with equal likelihood. So that's our assumption, that each key is equally likely to hash to an integer between 0 and m minus 1. And this assumption, again, it's with work, it's possible to come close to this. Lots of researchers have done good work to show this. So we'll assume that as a starting point. And that allows us to model the situation with the so-called bins and balls model that directly relates the study of hash functions to classical probability theory. So we've got m bins. That's our corresponds to our hash table, and we got m balls, and we have some number of balls, however many keys we have, and we throw them uniformly at random into m bins. And these things are studied in classical combinatoric analysis. For example, there's the birthday problem, which how many balls do you throw before you find 2 hitting the same bin? When do you get the first collision? And the answer to that is it's about square root of pi m over 2. When does all the bins fill up? Well, that's called the coupon collector problem. After about m natural log m tosses, every bin has at least 1 ball. And those are just examples of classic results from combinatorial analysis that help us understand what happens when we do this, which is what we're doing with hashing. And we'll look at more advanced versions of these problems when we want to study hashing. In particular, it's known that after you've thrown m balls into the m bins, then the most loaded bin has about log m over log m balls. So that's going to help us get a handle on the performance of hashing algorithms when we get to the implementations. So this is just an example showing all the words in A Tale of Two Cities using the modular hashing function for strings, like the one that Java uses, and they're pretty uniformly distributed. That's the summary for hash functions. Next, we'll look at separate chaining, a collision resolution strategy that makes use of elementary linked lists. So what are we supposed to do when 2 different keys hash to the same index? The birthday problem tells us that we're going to have collisions. You need a quadratic amount of memory to avoid collisions. And the load balancing and coupon collector analysis tell us that the collisions are going to be evenly distributed among the table, around the table. So what we want to do is have an easy way to deal with collisions. And so the first way we'll look at is called separate chaining, and it's a very old idea going back to 1953. And the idea is just build a linked list for each of the table positions. So we'll have a table that's smaller than the number of keys that we have. The hash function will map each key to some integer. So in this case, we have a table of size 5. So the hash function will map any key. In this case, we'll use single letter keys. It'll map any key to an integer between 0 and 4. And then to do an insertion, we'll just keep a linked list at the table position corresponding to the hash value. So S hashes to position 2. It'll be on the linked list that first link is at position 2. And then E goes to 0 and A goes to 0. And for search, we're going to have to go to, if we're going to look at is C in this table, say, we're going to find the hash value for C, and we'll look down the list to see if we can find C. So we have to look through the whole list for search, but you only have to look through one list out of all the lists. Essentially, if you have M entries in the hash table and n keys, the length of the list you're going to have to look at is about n over m because they're evenly distributed. So that's a straightforward and simple scheme for implementing symbol tables with hashing. Now, we could use a iterable bag or some data structure like that and hide the linked list structure underneath, and that's a perfectly fine way to proceed in modern programming. This implementation directly implements the linked lists. Now, for a practical situation, we pick some value of m. You could make it so that the hash table itself grows once it gets really huge, and such hybrid methods are easy to implement, so we won't talk too much about that. We need to, just in terms of implementation details, our keys and values have to be objects because we can't have an array of generics. Since we're making an array of nodes, and node would have generics if we're used to key and value, so we have to make them objects, and then when we get things off, we're going to have to cast. This is the get procedure. So to look for a key in the hash table, we compute a hash value, and our hash function is pull out the system hash code, make it positive by anding off the sign bit, and then mod with m to get a number between 0 and m minus 1. So we pick that number I, and then we just go to that list, and this is the standard code for traversing a linked list. Start at the first node, as long as it's not null, go x equals x dot next, and if you find a key that's equal to the key you're looking for, return the value, and we have to cast it to value because of the generic array creation problem in Java. Otherwise, you return null. So that's not much code, and it's trivial code at that for doing an efficient symbol table search using hashing. And insertion is not much more difficult. If you do the same thing, and if you find a node with key equal to the key on the linked list, you reset the value and return. Otherwise, you make a new node and put it at the beginning of the linked list with this standard code. Replace st of I with a new node that links to the old st of I. So again, very little code to implement search and insert using hashing, and that's why it's so popular. And what about the analysis? Again, the standard probabilistic analysis of the balls and bins problem tells us a lot of information of what goes on. And again, if the uniform hashing assumption holds, the probability that the number of keys in a list is within a constant factor of n over m is extremely close to 1. So it means that we've divided the search cost, which would be n if we have a sequential search, by a factor of m. And in many applications, even setting m equals to 100 or 1,000 is going to be very effective, and that's why so many systems programmers use that. So number of probes for search and insert is proportional to n over m. Now, typically, what a programmer would do is try to figure on making m about equal to the number of keys divided by 5, say. So if you can't make m too large, you have too much space, and you'll have empty chains or short chains. And if you make m too small, then they're too long. You have to search through them all. So let's say n over 5, and then you get constant time searches and not much extra space. You have extra space for the links to implement the linked list, but the rest of the table is not much extra space. And those are typical parameters. If you want a full service symbol table, which is going to grow from small to huge and then back down to small again, then you'd want to use array resizing to make sure that m is always within a constant factor of n. But we'll leave that detail out for now. So that brings us to this summary. Where red-black trees, we were happy with log base 2 of n for search and insert. With separate chaining, you can really get it down to a constant number of operations for search and insert. So hashing's going to be preferred for short keys where the hash function's easy to compute and where we don't need ordered iteration or any of the ordered symbol table operations because it has really fast access to the symbol table. That's our first collision resolution method, hashing with separate chaining. Another popular collision resolution method is known as linear probing, and there's many different versions of hashing that are based on this idea. With linear probing, it's called open addressing, and it's also around the same time in the 50s. The idea is to just use an array instead of using space for the links in a linked list. Use that same space and just allocate an array. In this case, the size of the array is going to have to be bigger than the number of keys that we expect. And we use empty slots in the array to essentially terminate the length of the list that we have to search through when we're doing a insertion. So let's look at a demo of how it looks. So to hash, again, we do the same thing. We just map the key to an index. But in linear probing, to insert, what we do is we put it in position I if that's free. If not, we just look at I plus 1 and I plus 2 and wrap around to the beginning if we reach the end. And that's also very simple to implement, and it works well as long as the size of the array is significantly bigger than the number of keys. Let's look at a demo. So start with an empty table, insert S. Its hash value is 6. 6 is empty, so we put it there. Now we look at E. The hash of E is 10. We look at 10. It's empty, so we put E there. So at the beginning, we're going to be fine. A is 4. Empty, put it there. R is 14. Empty, put it there. So we're just essentially using the hash function as an array index. C is 5, that's empty, and we put it there. So H now, the hash value of H is 4. So now we look at 4, and that's occupied, so we can't put the H there. And then linear probing says just look at the next position, look at 5. That's still not empty, so we look at 6. We keep going till we find an empty place, and then we put H there. Now when we search, we're going to have to do the same thing. We're going to have to look at all those positions to look at H. The group of 4 contiguous keys in a table space there is called a cluster, and clearly we want to keep those clusters small. And we do that by just not putting too many keys into the table. So X hashes to 15, that's empty, so we put it there. M hashes to 1, that's empty, and we put it there. P hashes to 14, 14's occupied, 15's also occupied. Now we run off the end of the table and look in 0, and that's empty, so we put it there. L hashes to 6, 6 is occupied, we look at 7, 7's occupied, we look at 8, and we put it there. And so that's an example of inserting keys into a hash table. And now for search, we just do the same thing. We use the hash function to search for E. E's hash value is 10. So we look in 10, and there it is. So that's a search hit. If we're going to search for, say, L, L's hash value is 6. It's not there. So in order to look at every place in the table where L could be, we have to keep looking until we find an empty table position, or we find L itself. So now we look at 7, L's not there. We look at 8, L is there. That's a search hit. If we have a value that's not in the table, like K, well, we'll hash, and is it in position 5? No. 6, no. 7, no. 8, no. And we find an empty position. At that point, we can conclude that K is not in the table, because if K were in the table, it would be somewhere between its hash point 5 and that empty position 9. That's a search miss, and we return null. So that's a short demo of linear probing hashing. So here's a summary of linear probing hashing. To get started, we map a key to an integer between 0 and m-1, where m is the size of our array where we're storing the keys. To insert, we put the key value pair, use parallel arrays, a key in one array and a value in an array with the same index. And we put the entry at table index A if it's free. If not, you try I plus 1, I plus 2 until getting to an empty position. And for search, you do the same thing. You hash to the table position, and you look there and to the right to find the key, and you stop when you find an empty table position. Find the key or find an empty table position. Now, it's essential that the array size is greater than the number of key value pairs in. And for linear probing hashing, really the implementation needs to include array resizing whenever the hash table gets too full. Usually, as we'll see, it's a good idea to make sure that it stays at least half empty. Here's the implementation, and it's quite straightforward given the demo that we talked about. We use the same hash function. We use parallel arrays for the value and the keys, and we have to use uglycast because we can't have arrays of generics. Then let's do the search. So we just have a for loop starting at hash of key. And going until we get to a position that's null. As long as it's not null, we stay in the loop. And increment I mod m, so that's when I gets to the end. It's at position m-1, then it goes, next increment goes back to 0 to the left end of the table. And we just test for all the non-null keys. If it's equal, if it is, go ahead and return the associated value. And if you get to an empty position, then return null. And the implementation of put is similar. Find a position if it's that's equal, and then reset the key in the value. If the key's there, it just resets the value. If the key's not there, it puts a new entry in. So again, that's fairly little code to implement a fast symbol table and insert. Search and insert, but it's only going to be fast if the table size is set appropriately. In ancient times, memory was at quite a premium, and so people were very concerned in making sure that the hash table never got too empty. Remember, in the first computers, each bit was a physical thing, a magnetic core that somebody had to string a wire through. So the bits were really expensive, and people wanted to make sure that they were making best use of the memory. And just leaving empty positions around in a hash table or using links in a linked list did not seem like an appropriate use of space. And so there was quite a bit of effort devoted to figuring it out, how full we could get the hash table in linear probing and how close it could get to being full without sacrificing performance. And one way to think about what goes on is to just watch what happens when a hash table fills up. So here we're just, as it goes up, we're showing each key getting inserted and the number of probes of the table that are needed for the insertion. So J hashed to the same position at A, and it had to look for a while. And the one thing to notice as the table gets full is that, first of all, you have these clusters or these chains building. And so what's clear about that is that it means that the new hash is likely to hash into a big cluster. And not only that, once you have a big cluster and you hash into the middle of it, you've got a good chance that that cluster is going to get longer, or worse, that it's even going to merge with another big cluster. And so that's the situation as the table fills up. You get long clusters and they're likely to get longer. And the math bears that out. Now this was studied in detail by Knuth by Don Knuth in the 1960s. And actually, this problem, Knuth says, was really the origin of analysis of algorithms. Mathematicians were trying hard to understand this problem and were ready to give up. And he realized that you could use classical balls and bins type probabilistic analysis. Not an easy analysis, but we actually could make precise, accurate statements about the performance of this algorithm. And those statements could be borne out in practice because the hash functions approximate random, the math assumes random, and the formulas predict what actually happened in practice. And the way Knuth formulated the problem is a so-called parking problem. So what's happened is you're at a one-way street and you're looking for a parking place. And it's the idea is you start looking for a parking place at a particular time, say, okay, now I need a parking place. And what you're doing is linear probing hashing. If the current space is taken, you try the next space and the one after and so forth. And the question is, if every car starts looking for a place at a random time, that models the hash function, then how far do they have to go to look for a place? That's Knuth's parking problem. And he was able to show, and we'll talk just a little bit about this, that if there's only half of the parking spaces are occupied, then on average, half the people find it after one place and the other half have to look one extra. So that's the kind of performance that we want. But as it gets full, the displacement gets up to square root of pi m over 8, which is obviously much higher than we want. We don't want our searches to take that long. In that, actually, the analysis is an amazing function that goes back to the famous Ramanujan and other classical results from combinatorial analysis. What Knuth's theorem says is that under the uniform hashing assumption, the number of probes in a linear hash table of size m that is alpha percent full, so the number of keys is a fraction of m, is for a search miss half 1 plus 1 over alpha, and a search miss 1 plus 1 over 1 minus alpha squared. 1 minus alpha for the hit, 1 minus alpha squared for the insert. Now, as alpha gets close to 1, you can see these things are going to grow, and particularly the search miss is going to grow quite a bit. If it's 9/10 full, 1 over 1 minus alpha squared is 1 over 100. So it means there's going to be 50 probes for a search miss if it's 9/10 full. That's independent of n and m. Whereas if it's half full, then we get the nice numbers of only 3 halves for a hit and only 5 halves for a miss. And again, these formulas are nice approximate formulas, but Knuth, once he figured this out in 1963, tells the story is that at that time he decided to write his famous series of books on algorithms. And now there's 4 volumes out and more planned, and this is where all computer scientists go for detailed information on the performance of algorithms. So in summary, you can't have M too large. What we want to use nowadays is array resizing to make sure that the array is always about half full. And if we can keep the array about half full, then we get constant time performance for search hit and search miss. And linear probing is very attractive in this case. There's other things that we can do algorithmically to bring down the search time a little bit, like using another hash function rather than looking at the next entry, use another hash function to determine the stride that we're going to use, and that brings it down somewhat and allows us to keep the tables more full. But the bottom line is that now we have 2 methods that, under the uniform hashing assumption, can give us constant time search hit, insert, and delete for symbol table implementations where we don't need ordering and we've got a reasonable hash function. So that's a summary of linear probing, our second hash collision avoidance strategy. So let's just look at a little bit of the context of hashing in practical applications. As I mentioned, it's very widely used. So here's an example right from Java. The first implementation of Java 1.1, the designers found that the cost of computing the hash function for strings seemed to be excessive, particularly for long strings. And that was one of the main uses of hashing, was just to be able to do searching with string keys. And so what they decided in the first implementation was, let's just look at every 8th or 9th character. In that way, we don't have to spend a lot of time computing the hash function. So they had a hash function pretty much like the one that we use, except they'd compute a skip that would mean that they'd only look at about every 8th key, and they wouldn't have to do quite so much work performing the hash function. And that's definitely one thing to consider when using hashing, is that the cost of computing the hash function for a complicated key might exceed the cost of searching in using a simpler structure like a binary search tree. And anyway, for Java 1.1, what happened was that there was a huge potential for really bad collision patterns on typical data. So here's an example of typical data, which is a URL. All of these keys, which are totally different, would wind up having the same collision. And so client programs and system programs in the Java system were having terrible performance on their symbol table because of this shortcut in hashing. So this well illustrates that you need to use all of the data in the hash function. And sometimes when you do a closer analysis, the cost of the computing the hash function can mean that something like red-black trees will even outperform hashing even for just search and insert. So there's another thing about the uniform hashing assumption, is that it is an assumption, and if you're writing code where we have to have guaranteed performance, like when your aircraft is landing or you're controlling a nuclear reactor or somebody's pacemaker, if that assumption doesn't hold and you get bad performance, you're going to have disastrous consequences. So that's another reason to think about maybe paying a little extra and using the guarantee that you get with red-black search trees instead of hashing. And there's another surprising situation that happens in today's world. For example, Java publishes its hash functions. And so if you're trying to provide a service over the web, an adversary can learn your hash function and just send you data that causes a huge performance problem by just making all that data hashed to one particular item. And that's definitely something to worry about. And in the real world, you can nowadays find on the web particular sequences of keys that will cause particular services to crash. And again, that's a little harder to do with something like a red-black tree where we have performance guarantees. When you make an assumption, you better be sure, and you're depending on that assumption, you better be sure that it holds somehow. And this is different than, for example, for quicksort, when our assumption was we're going to create randomness and we're going to depend on that randomness. In this case, we're kind of hoping for randomness, and maybe that doesn't really always hold. So that's certainly something to be aware of when using hashing in practice. So here's just a simple example on hashing in Java. What we can do is it's pretty easy to find a family of strings that have the same hash code. For example, with just a little fooling around, or nowadays you can just look it up on the web, you can see that these 2-character keys both have the same hash code. And you just do the math, and that base 31 hash code will tell you that answer. Well, what that means is that actually, just like working in binary, you can combine those things in all possible ways, and you can get 2 to the n strings for any n of length 2n that all hash to the same value. And somebody's implemented a service in Java that uses a symbol table that takes string keys. You can cause that to crash in this way. A little bit scary for some systems designers, at least reason for pause in using hashing. Now, hashing also has an extremely important application in today's internet commerce. It's the concept of so-called one-way hash functions. Which means that we use it for secure, to try to have some secure fingerprints for use on the web. And there's been a lot of research done to develop functions that take keys as input and then produce values that look random in such a way that it's hard for someone else to find another key that collides with that. This technology is useful for storing passwords and digital fingerprints and things, but it's too expensive for use in a symbol table. So the bottom line is separate chaining versus linear probing as collision resolution methods. There's a number of considerations to take into account. Separate chaining is really easy to implement, both insert and delete. If performance degrades, it does so gracefully. And the clustering is maybe less of a problem if you have a bad hash function. Linear probing tends to make better use of space, and also it'll perform better for huge tables where caching is involved. And classic algorithm or computer science problems for people to think about is what do we do to delete in these two situations, and exactly how do we resize? And those are all at the level of exercises in the context of the kinds of algorithms that we've seen. And as I mentioned, there's been many improved versions of hashing that have been studied. I mentioned the two-probe or double hashing version. Another way to use two hash functions is just to hash to two positions and put the key in the shorter of the two chains. In that case, then the expected length of the longest chain will be log n, which is quite an improvement. You get constant time expected and log n worst case. Double hashing is the variant of linear probing where you just skip a variable amount, not one each time, and that pretty much wipes out clustering, but it is more difficult to implement delete for that one. In a new method relatively new method called cuckoo hashing, is another variant of linear probing where we hash a key to 2 positions and insert the key in either one. If occupied, you reinsert the displaced key into its alternative. It was in 1, each one can go to 2. And that one actually gives constant worst case time for search. That's another variation on the theme. And all of these things allow us to make better use of the memory, allow the table to become nearly full. Would have been very exciting to the researchers in the 1950s who cared so much about memory. Nowadays, a little extra memory is not something that people care about so much, and most people just go with the easy algorithm, except for really performance-critical applications. What about hash tables versus balanced search trees? Well, hash tables are really simple to code, usually, if you don't have to do the hash function. And if you don't have order in the keys at all, then you need the compare to implement balanced search tree. So you have to use hashing if you don't have comparison. And it'll probably be faster for simple keys to use hashing. It's a few arithmetic operations to do the hash versus log n compares for the balanced tree. And there's some better system support in Java for strings. That cache hash code means that you don't even have to compute the hash if your symbol table for strings is in an inner loop. On the other hand, balanced search trees have a much stronger performance guarantee. You don't have to assume anything. It's going to be less than log n compares, and it's got support for all those ordered ST operations, and compare to is a pretty easy and natural function to implement. So it's more flexible and more broadly useful. And actually the Java system and other systems include both, so that programmers can make use of either one in different situations. That's our context for hashing algorithms. Welcome back. Today we're going to look at some symbol table applications to give you some idea of how symbol tables might be used by client programs for practical problems. First one we'll look at seems even simpler than regular symbol tables, and that's about sets. So a mathematical set is just a collection of distinct keys. And so there's plenty of applications where we want to just be able to implement this really simple API. We want to be able to create an empty set. We want methods to add a key to the set and to check whether a given key is in the set or not, to remove a key and maybe return the number of keys in the set, and also have an iterator to iterate through keys in the set. This is simpler than symbol tables because it's got no associated value. It's a very simple API, but of course we want to be able to do these operations efficiently. How would we go ahead and implement that? Well, if you think about it for just a minute, you see that what you need to do is just remove all references to value from any of the symbol table implementations that we look at. The implementation is easy. Take one of our symbol table implementations and get rid of the code that refers to values. Okay, so let's look at a couple of applications where this set API might be useful in client programs. One thing that is very common is the idea of an exception filter. So the way we'll set that up is to think about having a list of files, a list of words in a file that are exceptional in some way. In this case, we'll have the file list.txt that has these 4 words in it: was, it, the, and of. So there's 2 complementary ways to look at this. One is so-called whitelisting, where we want to take the words in that file and then we have some other much bigger file, and what we want to do is print out all the occurrences of our exceptional words in our given file. Those are the ones that we care about, that we want to get through. So in this case, tinytail.txt, the first couple of words from Tale of Two Cities, and these words appear often. It was the of, it was the of. Another complementary approach is to think of these words as words that we don't want to ever see. They're blacklists, and we want to take them out of our source file. So a blacklist client would print out all the words in our source file, tinytail.txt, except was, it, the, and of. In this case, best times, worst times, and so forth. So that's an exception filter, and that's useful in lots of applications, such as the ones listed here. For example, you might have a spell checker where you want to identify misspelled words. So then your key would be a word or string, and in your exceptional list would be words that are in the dictionary. And you'd want to print out all the words that are not in the dictionary. That's an example of an exception filter. Or in a browser, you might want to mark your visited pages or block sites and so forth. Or like the one at the bottom, credit cards. Maybe you run a credit card company and you want to check for stolen cards. Then your keys would be numbers, and in your list might be kind of short, which would be the stolen cards that you know about, and you'd want to run a whitelist filter for those cards and print out in your long list of transactions whichever transactions have that stolen cards. So that's just a couple of examples of exception filters. What's the implementation of an exception filter? Here's a simple one using the set API that we just articulated. So we start by creating an empty set of strings. And again, since we don't have associated values, we just have the one generic for strings. And then create a new input stream from the first argument, so that's the name of the file that contains the exceptional words. And so this just reads those strings while the input string is not empty and then adds them to the set. So that now we have our set of exceptional words, and now from standard input we read words. As long as our set contains the word, we print it out. If it doesn't contain it, we don't print it out. So that's an example of a whitelist filter. And to implement blacklist, we just this call to contains, we just change that to a not. If it's not in the exceptional list, then we print it out. So that's a simple example of a filter using sets. Now let's look at a dictionary client, another very useful and common application of symbol tables. So in this case, we're going to write a client called lookup CSV that is going to take 3 arguments. The first will be a file name, a so-called comma-separated value file, and the next 2 arguments are integers, which will tell us what to treat as keys and values in the file. In this example, our CSV file relates URLs to IP addresses. So each line has a URL and an IP address, and they're separated by commas. And in general, a CSV file might have many fields separated by commas. So we number them 0, 1, and so forth, starting from the left. So what we are going to do with this client is specify with integers which field is the key and which is the value. So if we call this client with the second argument 0 and third argument 1, that means we want to use the URL, field 0 in the CSV file, as the key, and we want to use the IP address, that's field 1 in the CSV, as the value. We want to associate keys with values. So the client will build a symbol table that makes those associations for every line in the file, and this could be a huge file. And then if we want to look up the IP address associated with a given URL, we can just type in URLs and the client will return the IP address. It'll do the lookup. So adobe.com has got this IP address as shown at this line here in the table and so forth. Princeton.edu has this, and ebay.edu is not in the file. Now, on the other hand, we could, from this same file, we could build a symbol table where we treat the IP address as the key and the URL as the value. So in that case, it'll build a symbol table with IP addresses as keys, and we can type in an IP address and get the associated URL. So with one client, we can handle lookups of all kinds in CSV files. For example, here's another CSV file that from biology that deals with amino acids and codons and names. So in this case, the first field is 3 letters from a DNA sequence, which represents a codon, and certain codons have the names. That's the amino acid. So TCC is called serine and so forth. And that's an association that's well known to biologists. And then you can use this lookup CSV client to quickly get the name associated with any given codon. And that's just another simple example. This is a very general tool. Any CSV file, you can pick any field as the key and any other field as the value. So here's still another example where we might use for a class list, which has the person's year of graduation, last name, first name, precept name, and login name. And so in the first call over here, we might use the login name as the key and the first name as the value. So we type in somebody's login name, we get their first name. And again, with the same client, log in as key and get the section as a value. So all kinds of information processing that we might need to do for large amounts of data represented in comma-separated value files. This one client, which is based on a symbol table, will provide useful functionality. And here's the implementation. There's very little to it, given the symbol table API that we've articulated and the implementations that we have. So what do we do to get lookup CSV implemented? Well, first thing is to set up the input stream from the first argument, so that's our input file, and then get the numbers of the fields, so the key and the value, and now build a symbol table that associates strings with strings. Then there's a while loop where we just read a new line, in.read line, and then split according to comma into tokens in an array. And then the index in the array is going to be the fields that we're going to use. So the key is the string in the key field entry of the array, and the value is the string in the val field entry in the array, and we simply put that in the symbol table. So this while loop just builds the symbol table from the file. Then from standard input, we take queries, just read a string, check if the symbol table contains the string. If it doesn't, print not found, and if it does, print the value associated with the key. So a very small amount of code based on our symbol table implementation that gives us the dictionary functionality. Here's another simple client program for symbol tables related to indexing. Again, another common function that's easily handled by symbol tables. There's all kinds of cases where we just have a lot of information, maybe on our PC or all over the web, and we want to create an index that allows us to specify a search key and get all the associated information. And you've used programs like this on your computer in many instances, most likely. So more generally, here's the goal. So we're going to have a list of files that are specified, and then and maybe it's all files on the computer, or maybe it's specified in some other way. And what we want to do is create an index so that we can efficiently find all the files that contain a given query string. So in this small example, so our client is going to be called file index. And in this small example, say we're going to have 5 text files. And these are just pieces of literature. And so what we want to do is build an index from that set of text files. And then given a key, a string key, we want it to print out the files that might contain that key. So for example, the word freedom appears in the Magna Carta and in Moby Dick and in Tale of Two Cities, all 3 of them, but not in Tom Sawyer and not in Aesop's Fables. The word whale appears only in Moby Dick. The word lamb appears both in Tom Sawyer and Aesop Fables and so forth. So we're looking for a piece of information somewhere on a computer, and it'll give us the names of the files that contain that information. With a more complex user interface, this is very much what the spotlight or find function on your computer is doing. And a programmer might use the same program to find places where certain programming terms are used in a bunch of programs. So normally we have a bunch of .java files when we're working on an application, like these are all the ones associated with this lecture. So we might build an index from that set of files, and then we might wonder, well, where do we use the import statement? So we just search for import, and it'll tell us, look in those 3 files. Or did we use comparators anywhere here? And this index will tell us no. So again, a very general capability that's got lots and lots of applications and easy to implement with our symbol table API. And the idea is that what we're going to do is associate keys with values. Well, the key is the string we type. What's the value? Well, what we're going to use for value is a set of files, the files that contain the query string. So just given that high-level description, then the implementation is pretty direct. Here's the implementation of file index using our symbol table implementation. So now we're going to build a symbol table that associates string keys with sets of files. So this creates a new symbol table associating string keys with sets of files. So first thing we do as before is build the index. So we're going to take, this time we're going to take the list of file names from the command line. And for each file, we're going to create an input stream. We're going to read every word in the file. If the symbol table does not contain the word, we'll create a new set for that word and put that into the symbol table. And then we simply get the set associated with the key and add the new word to that set, the new file name to that set. So this one, for each word in the file, it'll add that file name to the corresponding set for that word. That's building a symbol table associating keys with sets of files. And then processing queries is the same as before. As long as standard in is not empty, we take a query and then simply print out the set of strings associated with that word, which is a list of file names. So again, our symbol table API gives a very easy way to implement this file indexing function, which is very widely useful. And similarly, maybe we want to build a book index, maybe for a real book or maybe for an e-book. Or more generally, people want to often pre-process text, maybe a huge amount of text, to support so-called concordance queries. So what you want to do is, given a word, you want to find all occurrences of that word along with the immediate context. And context just means a few words before and a few words after. So for example, in Tale of Two Cities, the word cities actually only appears in this one place, and this is the context that it appears, with the 4 words tongues of the two before and that were blended in after. The word majesty appears in 3 places, and there's the context. And while this is a very special case of what you're very familiar with in web searches, you type in a word and then you get places where that word appears in context. Again, our symbol table API provides for an easy way to implement this. This is a concordance client that does the job. Now what we want to do is read text, and we want to build an index for each word. So this is a Java construct for reading all the strings on an input stream, on standard input, and splitting them by blank space and putting them into array. So now all the words are in an array. on standard input. And then we're going to create a new symbol table that associates strings with sets of integers. And again, the string is the key, and the sets of integers are going to be the places in the array where the given word appears. So we go through all the words, pick out our key S, and again, if it's not there yet, we create a new set associated with that S, and then afterwards we go ahead and get that set and put the new index on that set. And then that allows us to process queries where we take a query and then get the set of indices associated with that query, and then we've left out the code where you print out the 9 words that you want, the 4 to the left and the 4 to the right. Again, quite useful and familiar functionality and very easy to implement with our symbol table client. As a final example of a symbol table client, we'll take a look at a mathematical application where we want to implement sparse vectors and matrices. So this is standard matrix vector multiplication that you learn in math, where we have a square matrix and a column vector, and we want to do a dot product of first row with the column vector to get the first entry in the result. So in this case, they're all 0 except for 0.04 times 0.9, which is 0.36. And then similarly, dot product of this with that column is 0.297, and so forth. So standard implementation of this is quite easy. We have a 2-dimensional matrix, 1-dimensional column vector for the multiplicand and the result. And then they get initialized in some way, but the main computation is a pair of nested for loops. For each row in the matrix, we have to go through each entry in the column vector and compute a running sum of, for that row in the matrix, the corresponding entry with the entry in the column, and keep the running sum, and then that's the result that we put in the result column vector for every value of I. And the key thing about this standard implementation, that it's 2 nested for loops that each run up to n, so that's n squared, or quadratic running time. And that's fine in typical applications when the matrix is small, or when there's lots of entries in the matrix. But the fact is that in many practical applications, the matrices are what's called sparse. Most of the entries are 0. And so symbol tables provide us with a way to provide a more efficient implementation of this process when we have lots of 0 entries. So in a typical thing, say maybe the matrix dimension would be 10,000, and maybe there'd only be 10 non-zero entries per row. Or even nowadays, you might have matrices that are even bigger, 10,000 by 10,000. If it was full, that'd be 100 million entries. So that's definitely going to be costly if you're doing this operation a lot. And the idea is to cut down on that cost by taking advantage of the idea that there's a lot of zeros. So let's start by just looking at vectors. The standard representation that we use for vector is to simply use a 1-dimensional array. We have constant time access to every element, but the space is proportional to n. So even if there's a lot of zeros, we still have to take the space to store them all. Instead, we're going to use a symbol table representation where our key is the index and the value is the entry, and we just use that for every non-zero entry in the vector. So this has got the same amount of information. It says that index 1 has got 0.36, index 5 also has 0.36, index 14 has 0.18, and so forth. but the space is proportional, instead of to n, it's just proportional to the number of non-zero entries, which again in typical applications may be way, way less. And so now we know we have a symbol table implementation that has efficient iterator, and also access is not bad. It's just that we're able to do it with way less space. So here's what the implementation of a sparse vector might look like. First thing is the representation is going to be a symbol table, and in this case we might as well use a hash table because the order in which we process things is not important. We just want to get at all the non-zero entries. The constructor is going to create in this symbol table just a new symbol table that associates integer indices with double values. So the put, which is to store a value associated with an index I, is just put into that hash table, associate key I with value x, associate an integer with a double. And get, returns 0 if the index key is not in the symbol table. As the whole point was, we don't represent zeros. Otherwise, it returns the value associated with the index. And the iterable just returns all the key to iterate. And the most important thing is that if we want to do a dot product with a vector, say, then the time that it takes is only proportional to the number of non-zero keys. The zero keys are going to be 0 in the dot product, so all we're going to do is take the ith entry of the vector and multiply it by whatever value we get for the non-zero entries. So it's a dot product that takes time proportional to the number of non-zero entries in the vector. And that's going to be important in the use of a matrix. So instead of using the standard matrix representation where every row of a matrix is an array, that's what a two-dimensional array is, and the space is proportional to n squared, now we're going to use a sparse matrix representation where each row of the matrix is a sparse vector. We can iterate through the elements in constant time, and with the hash table even get at them in near constant time. And then constant time in the average. But the space is only proportional to the number of non-zero elements, plus n for the extra symbol table overhead. So those are independent symbol table objects, but they allow us to have a much more efficient matrix multiplication method. So now, if we have a sparse matrix times a vector, our running time is going to be constant for each row, or proportional to the number of non-zero entries for each row, which means that the running time is going to be linear for a sparse matrix just by the use of a symbol table. And this clearly can make the difference between being able to address a huge problem. If we have a 10,000 by 10,000 matrix, we can get it done nearly instantly linear time versus 10,000 squared. If we don't run out of space, we might run out of time. But with the symbol table implementation, we can efficiently process huge sparse matrices.